leaving group is a substance which is bumped from the carbon nucleus. So as this comes in, it bumps out the iodine so that the carbon could be bonded only 4 times. So what are we left with? Well, we're left with CH3 bonded to the oxygen, which was bonded to the CH3. So this would be our organic product, our product containing carbon. Then we have iodine, which is floating around in solution, I-, because it withdrew electrons to itself, so it became I- floating in solution. And then now our spectator ion, which hasn't been involved in the reaction, floats around and starts to associate with the iodine via sort of ionic bonding because of the opposites attracting. But the sodium was not actively involved in the reaction in any sense of the word. So let's look at our organic product and name it. Anytime we have an alkyl group is an alkane, meaning a hydrocarbon minus 1 hydrogen. So this is not CH4, which would be methane. It's CH3, so it's methyl. So in general, we call these alkyl groups. So an alkyl group on one side, an alkyl group on the other, oxygen in the middle. That is the definition of an ether. And so this particular ether has a methyl on each side, so it's called dimethyl ether. If it had a methyl group on one side and an ethyl group on the other, you can call it methyl ethyl ether. So this is one of the ways that you can name ether compounds. So we just created an ether with this organic reaction, looking in particular at nucleophiles, leaving groups, and spectator ions. And also keeping in mind that when you look at a compound and you're not familiar with it, consider compounds that you are familiar with and see if you can make some relation there. We've seen the basics. Now let's look at some good appropriate groups that would represent good nucleophiles and leaving groups. So good nucleophiles, one of the great nucleophiles that you'll see over and over again in organic chemistry is the OH- group, the hydroxide anion. Other good nucleophiles include the cyano anion, that's carbon and nitrogen. There is also NH2-. There is NH3, which is ammonia. Ammonia, of course, would not be as strong as NH2 because NH2- has a formal negative charge. Therefore, as a nucleophile, something that's attracted to a carbon nucleus, which is delta positive, you want to have something as negative as possible. But nonetheless, NH3 is still a reasonably good nucleophile, but NH2- would be stronger because it has a formal negative charge, whereas in NH3, the nitrogen would just have a partial negative charge because nitrogen is to the right of hydrogen in the periodic table. Nitrogen, of course, has a lone pair of electrons, a free lone pair of electrons. So these are a few. Of course, if you have OH-, one would expect that you would have SH- because sulfur is just under oxygen in the periodic table and therefore has similar properties. There's also OR-, where R represents alkyl groups. For example, we just saw the example of sodium methoxide. And so the methyl group was in this particular position. So any OR- group would be a good nucleophile. So these are examples of good nucleophiles. And in terms of some examples of some good leaving groups, well, I think better than just looking at examples of good leaving groups is to look at what the trend is. For example, let's look at a halide like chloride. So we have chloride. Chloride is a halide. That means a halogen, which is the anion of that particular halogen, and halogens can be found in the 7th group of the periodic table. And so we have Cl- here. It is a much greater leaving group than OH minus. OH minus is not a good leaving group, which is indeed a much greater leaving group than CH3 minus. CH3 minus, which is a methyl group, essentially, this would be a horrible leaving group, a horrible leaving group. And so, and the reason that we can look at this and look at the trends is that in general, the trends of where we find a good or poor leaving group is based on the acidity. Meaning, if we were to add a hydrogen to these substances and we were to examine how acidic would that substance be, well, that would give us our trend in leaving groups. For example, if we add a hydrogen here, we have HCl. That's hydrochloric acid. This is water, and this would be methane, CH4. Clearly, HCl is a far greater acid than water is. Water is obviously not a great acid. It's neutral. And so HCl, however, is a very good acid. And therefore, HCl producing the chloride anion, it is a very good leaving group. Water, it's easier to take a hydrogen out of water because, of course, there is a water dissociation constant. There is some hydrogen cations being liberated. So it is possible, but it's just much, much, much less than HCl. It's barely comparable. But then CH4, it's even more difficult to remove a hydrogen from CH4 because it produces a very unstable anion, meaning CH3 minus. So this is very, very unlikely. And so the general trend of acidity helps us to know what would be good leaving groups. Obviously, therefore, you can be presented with a substance as a leaving group that perhaps you haven't seen very often, but you would be expected to know that it would be a good leaving group. For example, HSO4. You would expect HSO4 to be a great leaving group. Why? Because H2SO4 is a strong acid. That is, sulfuric acid is a strong acid. Here's another chemical reaction, and if you feel inclined to, you can pause here and try to come up with the product of this particular reaction, and then you can come back and we'll work it out. Now, if you look at this particular chemical, this kind of chemical is called an aldehyde. The reason it's called an aldehyde is because it has carbon double bonded to oxygen. The carbon is also bonded to a hydrogen. This configuration, no matter if this is a hydrogen or an R group up here, that is called an aldehyde. Usually for organic chemistry, for the MCAT exam, there are very few trivial names that you need to memorize. This happens to be one of them because this is a very famous compound. This is called formaldehyde. So it's an aldehyde called formaldehyde, and that's because it has two hydrogens which are attached to the carbon, which is attached to the oxygen. This is formaldehyde. This particular chemical, well, its name is a little bit easier to remember. It's, of course, you don't have to memorize it because it's not a trivial name. You can work it out. And this is methyl lithium. So we have methyl lithium and formaldehyde in a chemical reaction. So we start, as we do with all of the reactions, which is to assign the charges. So carbon and oxygen. Oxygen is to the right of carbon on the periodic table. Therefore, by definition, oxygen has more electronegativity. It attracts electrons to itself. Therefore, the oxygen will be a little bit negative, delta negative. The carbon will be delta positive. Over here, we have a CH3 group with lithium. Lithium is to the left of carbon on the periodic table. So lithium will be delta positive, and carbon is to the right in the periodic table. So carbon will be delta negative. Now, it's not often that carbon is delta negative. This is not common, in other words. And so it happens with alkyl lithiums that we get delta negative carbons, and not for any magical reason. It's simply because lithium is to the left on the periodic table. But there is another group of substances that can produce delta negative carbons. And why is this so special? Because a delta negative carbon can produce a carbon-carbon bond. Because usually carbon is delta positive, as in this example. And so if carbon is usually delta positive, if you can produce a delta negative carbon, then you can have a delta positive carbon being attracted to a delta negative carbon, or vice versa, and therefore you can get a carbon-carbon bond. And because carbon is the basis of organic chemistry, it is a very useful thing to be able to create bonds between carbons. So this happens with alkyl lithiums, and it also happens in a group of compounds which, instead of symbolized with lithium, consider that lithium is in the first group in the periodic table. So then lithium has an oxidation number of +1. Well, if you look in the periodic table, magnesium is in the second group of the periodic table. It has an oxidation number of +2. But if you put an X group, now in organic chemistry, X is a symbol for halides, meaning chloride, bromide, etc. So it's a symbol for the halides, which are the groups in the compounds in the seventh group in the periodic table. So in the seventh group in the periodic table, their oxidation number is -1. So magnesium +2, halide -1, overall oxidation number of +1, which is exactly like lithium, which is +1. So if we were to have an R group here, so any kind of alkyl group, for example, methyl group or ethyl group or propyl or whatever, MgX, this would indeed create delta positive here and a delta negative carbon nucleus. So therefore, this delta negative would be attracted to something which is delta positive. So you can create carbon-carbon bonds. This type of substance or reagent, is called a Grignard reagent. Grignard reagent. And that is simply that we have a magnesium and a halide attached to some kind of alkyl group, and therefore it generates a delta negative carbon in the same way that this lithium generated a delta negative carbon here. So back to our reaction. We have a delta negative here. Now, remembering that opposites attract. Also, remembering that a spectator ion are the ions found in the first and second group in the periodic table. So once we know that opposites attract and that there exist spectator ions, we know that this lithium, being in the first group of the periodic table, is not going to be actively engaged in a chemical reaction. So we block out the lithium. Well, we're only left with one possible reaction, and that is that the delta negative carbon is attracted to the delta positive carbon over there. It's the only possibility because these opposites attract. So then we have this carbon becoming the nucleophile. So this is the first step in the reaction. The first step in the reaction. So this carbon becomes the nucleophile, comes in, hits this carbon. Once again, this carbon can only be bonded to 4 different things. So if something else is coming in and bonding to it, one of these bonds must break. Which one? The weakest bond. Again, the carbon-hydrogen bond is pretty much equally shared. That's not going to break. This is not going to break. So definitely it's going to be in here. And the weakest of all these bonds is the pi bond in the double bond. That's the weakest. Because in general chemistry, we discussed that having multiple bonds will create a situation which is stronger than just having a single bond. However, the strongest of the bonds in multiple bonds is the first bond, the sigma bond. The bond between the p and the p orbitals, called a pi bond, between p and p is the pi bond. That bond would be the weakest of the bonds. So therefore, of these 4 bonds, when this carbon comes in and bonds to this carbon, the weakest bond would break, which would be the pi bond. So that breaks, and this electron pair comes out here. Therefore, we have CH3, bonded to this group here, which is CH2, which is bonded to oxygen. Then we have electron pair, which has been popped out. In other words, rewriting it, we see we have CH3, CH2O minus. So that would be the reaction. CH3 coming in here, bonded to the CH2, which is bonded to one oxygen. The electrons pop out here. And then we have, of course, lithium just floating in solution. So lithium will be floating in solution, and therefore there's the ionic bond, the relationship between these substances. So this would be the product. In terms of naming the product, very easy. Because after all, how would you name this product? You would call this a lithium hydroxide. So here we have lithium. This is the ethyl group. So we have lithium eth oxide. So this is lithium ethoxide. And that is the organic product of this particular reaction. Now let us look closer at the carbonyl group, which is this particular group, because it is so central to many reactions in organic chemistry. So what is so special about the carbonyl group? Well, there are many things. To begin with, we've seen that this is a polarized bond, meaning that the carbon, because of where it is placed on the periodic table, is delta positive, and the oxygen is delta negative. So it is a polarized bond. Also, we've seen that there is a sigma and a pi bond. There's a double bond, and they have different strengths in that double bond. We also know that because the oxygen wants to have electrons to itself, therefore we can draw resonance structures for this particular compound, in which we have carbon with the oxygen negatively charged, meaning the oxygen pulled electrons to itself. Of course, if you have a neutral compound overall, if the oxygen pulls electrons to itself, pulls an electron pair to itself, well, therefore, the carbon will be deficient in an electron pair. It would have lost electrons to the oxygen, and therefore the carbon would be positively charged. So here are two different ways that you can represent the carbonyl group, and these would be called resonance structures. When you can draw resonance structures for a compound, it means the compound has increased stability. So this is a stable compound. It's a stable bond. It's a stable, what we call functional group. And we call this functional group because a functional group somehow gives us information about what kind of reactions would be involved in that particular compound. The functional group is where the action is. In fact, quite commonly on the MCAT exam, they'll put this gigantic molecule in one of their passages, which is going to frighten off people who are not too comfortable with organic chemistry. But usually the problem is a joke, because what they'll do is they'll put in a few functional groups, like the carbonyl group being the main functional group found in organic chemistry, and because they will have a few functional groups, that's where the action will be. That's where the reactions will be occurring. And that you don't have to be as involved or see the importance as the things that are in between the functional groups. That's not as important as the functional groups themselves. So in terms of the importance of the carbonyl group as a functional group, there's the resonance, the polarization of the bond, and the stability. And because of all this, because this is a delta positive carbon, this is a very reactive site. Now we're going to look at the impact that chemicals can have by having groups attached to the carbonyl group. Let us look at this problem. The question is, which of these compounds would react fastest with NaCN? If you look at this particular compound, because there is a carbonyl group here, our functional group, there's a hydrogen on one side, an alkyl group on the other, this compound is called an aldehyde. Here we have two alkyl groups on either side of the carbonyl group. Therefore, because there's an R, C double bond O, R group on the other side, by definition, this group is called a ketone. So we have an aldehyde and a ketone. Which reacts fastest with NaCN? Well, first, we'll need to remind ourselves is what type of reaction would occur. We would say that the carbon, immediately, we'd say that the carbon here would be delta positive, the oxygen would be delta negative, and we would have the same thing here, delta positive, delta negative. NaCN, if you're not familiar with this particular compound, you consider compounds that you are familiar with, like NaOH, which is similar in structure of this compound. And so we know that in solution, this would become Na plus and Cn minus. Then we know that Na, sodium, would be a spectator ion. So it would just observe the reaction and associate with something at the end of the reaction. So we have Cn minus as being on our list of good nucleophiles. And plus, even if we didn't know that, we would know that it would be attracted to the carbon nucleus because there's no other choice. Sodium is out of the equation until the end, so we only have the negative charge. So this would be attracted to something positive. Clearly, the Cn minus would be attracted to the delta positive carbons. As an example of the reaction, the Cn minus would come down here. It would hit this carbon, bonding to the carbon, and then it would have to break the weakest bond. The weakest of all these bonds would be the pi bond, so the pi electrons would pop up to the oxygen. Therefore, the carbon would indeed have only 4 bonds. So this would be the expected reaction either here, and we'd expect the same reaction in here. So in terms of which would occur faster, well, we would have to consider, well, what is the difference between these two chemicals? The only difference is that this hydrogen is replaced with a CH3 group or methyl group. So how will that alter the speed of the reaction? Well, hydrogen is just a proton. So we have to imagine that this is a very small attachment to the carbon. I don't want to call it a substituent because really CH3 group is a substituent. Hydrogen is a small proton with its shell, its outer shell, but its outer shell relative to any other atom is going to be clearly the smallest. So it is going to be the small thing attached to this carbon, whereas CH3 group is going to be as big as the other side. So we have this CH3 group which has a certain size around the carbon. Now the Cn minus has to get access to this delta positive carbon in order to bond. Clearly, the access route is easier here because the hydrogen is so small than to get in here where there will be these two bulkier groups. So the faster reaction would be with the aldehyde as opposed to the ketone. Furthermore, this idea that this bulkiness has an effect that will slow down a reaction, we call that effect of bulkiness of a molecule steric hindrance. So that's because this bulk effect hinders the nucleophile from coming in, so we call that steric hindrance. But the truth about steric hindrance is that sure, we call it a bulk effect and so on, but it still comes down to the basics of organic chemistry. This bulk effect is really based on the fact that on the outer part of these substituents are electrons. And here is a substance which is indeed negatively charged. So not only does it have electrons on its outer part, but it is net negatively charged. And it is attracted to the carbon nucleus, but there are these electrons around here, which is going to impede the access to the carbon nucleus. Now we will look more precisely at electronic effects. So once again, the same question: which reacts fastest with NaCN? But now we're looking at chemicals that are both types of aldehydes, but the only difference between these two chemicals is this one has a bunch of fluorines attached to it, and this one has a methyl group. So now let's look specifically on how that will affect the reactivity of the carbonyl group. Once again, we know that CN- will be attracted to the delta positive carbons here and here. But which one would it be more attracted to? So for this, we have to look at the difference. And this is the fluorine groups that are attached to carbon. So we look on the periodic table. And on the periodic table, we see that fluorine is towards the top right of the periodic table in the 7th group. And we know that fluorine, therefore, is the most electronegative element on the periodic table. That means it attracts electrons to itself stronger than any other atom when it is in a molecular environment. So here it is in a molecule, and it's attached to the carbon, this carbon, and therefore fluorine is going to be really pulling electrons to itself, and there are 3 fluorines indeed. So these 3 fluorines are all going to be delta negative, and this carbon is going to be very seriously delta positive, because it's not just attached to one electronegative atom, it's attached to 3 of the most electronegative atom on the periodic table. So this carbon is going to be very delta positive. The carbon next to it, because this is very delta positive, what will it do to electrons? It will attract electrons to itself, because the more delta positive it is the more that it will attract electrons to itself, because opposites attract. So these electrons are going to be pushed even increasingly towards the CF3 group. Therefore, carbon, which was delta positive before, because we saw that carbonyl groups have delta positive carbons, because it was delta positive before, now it's even going to be more delta positive. It's as if by having this group here, which is drawing electrons to itself, it sort of souped up this carbon and made it even more delta positive than it was otherwise. Therefore, for CN-, this carbon will be even more attractive than this carbon. Just as in the previous example with the ketone, CN- will react with the ketone even though they're steric hindrance, but it just won't react as quickly or as frequently as it would with the aldehyde. Well, in this particular situation, this delta positive carbon is extremely attractive for the CN- nucleophile. So it definitely will come in here frequently, faster, but indeed it also will react with this delta positive carbon. Because it is delta positive, it must also react with that. Not as frequently, not as fast, but it definitely would react with that. There is something different about this reaction compared to the other reaction that we looked at with CN-, and that is that CN- definitely will come in here. It definitely will hit this carbon. The electrons will definitely pop up, just as in the previous example. The pi bond breaks and the electrons would pop up here. So this would occur. We have this being 1 and then this being 2, and the electrons pop up there. Normally, as in the previous example, electrons popped up, the electrons couldn't come back down because there was nothing else that would have been a good leaving group. Carbon-carbon bonds in the previous example, it's too strong to break when electrons come down. Carbon-hydrogen bond, it's too stable of a bond just to break like that. However, let's examine this particular bond. This carbon is delta positive. very delta positive, as we said before. This carbon is very delta positive. So what do you think about the stability of this carbon-carbon bond? It must be pretty weak, pretty unstable, because we have a delta positive carbon bonded to a delta positive carbon. That bond must be unstable. There must be some repulsion there. Therefore, when the Cn- comes in, hits the carbon, bounces the electrons up, now the Cn- is bonded to this carbon. The electrons up here on the oxygen have the option of coming back down, hitting this delta positive carbon, and knocking out this CF3 group as a leaving group because of the instability of this carbon-carbon bond. We will now look at the production of acetals and ketals. So here we have a chemical. This is an aldehyde, as we saw before, which means it has a carbonyl group, an R group to one side, and a hydrogen to the other side. This is ethanol. It is symbolized as ETOH. Its actual molecular formula is CH3CH2OH. So this is shorthand for ethanol. And this is an acid, H+. So if this was in solution, if you had to try to derive for yourself what would happen in this reaction, you would start by saying, okay, so we have delta positive carbon here, and we have delta negative oxygen. So that's our typical sort of electronics that we write when we think about a carbonyl group, which is the functional group for this aldehyde. Then we would look at the alcohol, ethanol, and we would say that, well, we have a delta negative oxygen there. Clearly the hydrogen would be delta positive. So that would be the electronics. And so we would suggest, knowing that, that OH minus, the hydroxide group, is on our list of very good nucleophiles. Clearly ROH is not as good a nucleophile as OH minus because OH is negatively charged. It has a formal negative charge. So clearly it would be more attracted to something that is positive as compared to ethanol, which has a partial negative charge. It's not as highly charged as the OH minus. So indeed it would be attracted to something that is partially positively charged, but not as quickly as, say, if OH minus was involved in this reaction. Nonetheless, we know that this delta negative charge would be attracted to this delta positive carbon. There would be this opposites attract that would happen in this chemical reaction. And if the delta negative charge came here and hit this carbon, we know that the carbon can only be bonded 4 times. So the weakest bond would break, and that would be the pi electrons, which would go up to the oxygen. So we know that that would occur. However, that does not occur very quickly because the oxygen is not formally negatively charged, but it does occur. How can we make it occur quicker? Well, if you look at the reaction, there is a hydrogen there, an H+. And there is some little rules of thumb that you will look at as we progress through different types of chemical reactions in organic chemistry. One of them is that when you look at a reaction, one of the things you should look for is what is the most highly charged species. The reason is, whatever chemical is most highly charged is most likely to react fastest. For example, in this reaction, we have H+, which has a formal charge. Because it has a clear formal charge, it is most likely that it will be involved first in the reaction, which means whatever there is that is negatively charged or partially negatively charged, the hydrogen H+ would be attracted to that very quickly because it has a formal charge on it. And so when we look at the reaction, we see that there is a delta negative oxygen that's there, and therefore this H+ would have some kind of attraction to that delta negative oxygen. And of all the possible things that can occur, H plus being attracted to a delta negative oxygen would be very high on that list and would occur very quickly. Now, if the H plus would be attracted to this oxygen, and of course, as I mentioned before, we really formally should always follow the flow of electrons. So even though we think of the H plus as being attracted to this, we really should draw the arrow in this direction, showing the movement of electrons. And the movement of electrons would be attracted to the H plus. Now, if the electrons, because it's delta negative, if it is attracted to the H plus, and I'll put a 1 here, meaning that's the first thing that occurs in the reaction. So as the electrons are being attracted to the H plus, the bond, the pi bond, actually breaks as the oxygen formally makes a bond with the hydrogen. Now, if the oxygen makes a bond with the hydrogen, because the hydrogen is so highly charged and therefore is the first thing in the reaction to react, as the oxygen makes the bond with the hydrogen, what would be the charge on the carbon? Well, it would be positive. Not just delta positive, formal positive charge on it. The reason is, as the electrons go up to bond with the hydrogen, then carbon only has 3 bonds. Now, when it had 4 bonds, it was neutral, but partially positive. But now that it releases its electrons, if carbon releases its electrons, therefore the carbon will be positively charged. Now, when the carbon is positively charged, that makes it so much more attractive for the ethanol to come in here, because it was delta negative and this was delta positive, and so the reaction would have occurred anyway. But now that the carbon becomes formally positive, this reaction occurs much faster. In other words, the hydrogen sort of juiced up the chemical to make it more attractive for the ethanol to come in and bond. So then what do we end up with? Well, we have our carbon bonded to the oxygen, which has bonded to the hydrogen. Then we have our other hydrogen on the side, and then we had ethanol that just came in. So ethanol just came in, ETOH. So it just came in and it bonded to carbon. So we have the OH group up here, which was formed when the hydrogen went in. And then we have the rest of our chemical, and then we have ETOH. Now, if oxygen from this oxygen comes in and bonds with the carbon, gives up its lone pair of electrons to the delta positive carbon, which became formally positively charged. When oxygen does that, gives up its electrons, then the charge on the oxygen becomes positive. If you have any problem remembering that, just think of the fact that when oxygen has just one bond to itself, example OH minus, then the charge on the oxygen is negative, formal negative charge. If oxygen has 2 bonds to itself, example H2O, then the oxygen is neutral. Indeed, it has a partial negative charge, but it has no formal charge because water is neutral. And then when you imagine 3 bonds to oxygen, H3O plus, then the oxygen has a positive charge because it gave up its lone pair of electrons. So here's an example. The ethanol gives up its lone pair of electrons. Oxygen has a positive charge. Does oxygen like to be positively charged? Certainly not. In fact, oxygen is a very electronegative element. On the periodic table, it's towards the right and towards the top of the periodic table. And therefore, it is a chemical, it's an atom that draws electrons to itself. So it wants to have electrons to itself. It does not like being positively charged. So once it gets in this situation, it's going to look around for electrons somewhere to draw to itself so that it could maintain at least its neutrality, preferably delta negative. So here, oxygen wants to draw electrons to itself, and the likely culprit will be the proton. In other words, it draws electrons away from the bond between oxygen and hydrogen, and then it kicks out the proton. It kicks out the H+, and therefore it remains ETO without the hydrogen. And so it kicks out the H+. Now you can imagine, because it kicks out the H+, Now it is neutral. We see a couple of important points. Number one, we started off with hydrogen as one of our reactants. H plus is produced in the reaction. Therefore, any chemical that we use in a chemical reaction, which is reproduced at the end of the reaction and helps the reaction to occur faster, as is the case here with H plus, that is our definition of a catalyst. So here H plus serves as a catalyst. It not only makes the reaction occur faster by juicing up this carbon, turning it into a formal positive charge, but it is also regenerated during the reaction. So H plus is a catalyst for this reaction. Second important point is this is our hemiacetal. You see, when you start with an aldehyde, you're going to end up producing an acetal. When you start with a ketone, you end up producing a ketal, using the same mechanism of reaction. The ketone, the only difference being that it would have an R group here instead of the H. So now we have our hemiacetal. Now we will continue the reaction and produce an acetal. So here we're going to continue the reaction with the same reactants, ETOH and H, with this chemical. Once again, we do the same thing. What is the most reactive chemical here? The most highly charged, again, would be the H plus. Where would H plus be attracted to? H plus will be attracted to something that's delta negative. For example, some of the H plus will be attracted to this oxygen right here. This oxygen, of course, is delta negative. So H plus being attracted to this oxygen, which is delta negative, because of opposites attract, it would form, well, this is OH, so adding H to OH makes H2O. H2O is water. Clearly, water would be a stable substance. So water is a great leaving group. If you can form water which is attached to a carbon nucleus, water would be happy to leave as a leaving group. So if this hydrogen comes in here, attacks the OH, makes water, it falls off as a leaving group, and then the charge on the carbon, once again, is positive, because carbon would only be bonded once, twice, 3 times. So it wouldn't be bonded 4 times. Water left as a leaving group, this carbon would have a formal positive charge. Because it's juiced up, because it's positively charged, it would be the most reactive thing in the vessel, and so the next event that would occur, once again, the second event being the delta negative ETOH, the oxygen being attracted to the positively charged carbon, it bonds, it kicks out its proton exactly like this one did, and then we end up with an acetal. So we have R, C, H, ETO, and then ETO. This is an acetal. The only difference between this and a ketal is that there would be an R group here, and it would have started that way at the beginning of the reaction. The important thing is to understand the steps during the reaction. The most charged substance acting quickest first, and then, because it's juiced up, the ethanol coming in and then reacting. And then it happens a second time where the H plus attacks the OH group, forming water, knocks off, then the ethanol comes in and reacts because of a formal positive charge on the carbon, finally producing the acetal. Now you might be asking, well, wait a second. If the H plus is attracted to something that's delta negative, and it attacked this oxygen, forming water, and fell off, why is it that the H plus did not attack this oxygen, which is also clearly a delta negative oxygen, because it's attached to carbon, and because of the periodic table, oxygen being to the right, carbon being to the left, oxygen clearly is going to be delta negative here. Why is it that the H plus doesn't attack this one? Well, based on electronics, if something makes sense, it probably happens. That's the great thing about organic chemistry, is that there's minimal memorization. Most of it has to make sense. And so yes, it is perfectly logical that the H plus would attach to this delta negative oxygen as well. And if it were to attach to this delta negative oxygen, well, that would just make ethanol. That ethanol, in theory, can fall off as a good leaving group, and then it would make this positively charged, and then the electrons from this oxygen might come back down, and then we end up exactly with our reactant. In other words, the arrows that I drew are actually two-sided arrows. The reaction may proceed to the right, as indicated, and as I've explained, but there's also logic to the possibility that the reaction could also go back to the left. And that even goes for the final chemical. Even with this final chemical, the H+, which is regenerated in the reaction because it's a catalyst, may indeed attack any of these delta negative oxygens, thus returning us to this compound, which could in turn, in theory, go back to the first compound. So these are all double-sided arrows because the electronics suggest that either reaction could occur. So once you understand the mechanism of reaction and just have the comfort that yes, if it's delta negative, if I've got a positive charge, then these things would be attracted to each other, and therefore this is the possible result of the reaction. And just by going through the reaction in that sense, then you would be able to understand this. Now we will look at another example of the production of an acetal or ketal. My question to you regarding this particular reaction is quite simple. The question is as follows: true or false? You may want to put this on pause and consider what your response would be. So let's work this out. First of all, let's look at this chemical. Here we have carbon bonded to oxygen, and the carbon has two R groups off to the side. So this compound is a ketone. It has 6 carbons in it, 1, 2, 3, 4, 5, 6. It's cyclical, so it's going to be called something cyclohexene, and it's a ketone, so it ends in -one. So this is called cyclohexanone. Here's another chemical, and it has 2 OH groups. When you have an OH group, it's an alcohol. When you have 2 OH groups, it's called a diol. So here we have a ketone plus a diol, and we have a catalyst H+. So what's the first thing that's going to happen in this reaction? Well, clearly the H+ will be attracted to something that is delta negative. So we have a delta negative carbon oxygen here. We have delta negative oxygens here because this oxygen is attached to a carbon. So this is delta negative, and this is delta negative. So here we have our first major lesson in terms of chemical reactions. You see, when this H+ is attracted to delta negative oxygen, and it has obviously several choices, when you look at an organic chemistry reaction, it is very important to look at the electronics in order to see what would be attracted to what. But sometimes, when you have all these choices, you have to look at what would be the stability of the product. In other words, that is going to help you to decide whether or not the reaction can occur, is whether or not the product is stable or not. Because if the product that you produce in your reaction is terribly unstable, then what's the chances that that would actually occur? It would be very, very low. So in this particular instance, if H+ was to attack an oxygen here, well, that would form water. And we said already that water is a great leaving group. So if it would attack this oxygen, it forms water, it leaves. But if the water was to leave, then the carbon, which is here, would be positively charged. Not just partially positively charged, it would have a formal positive charge because it lost its electrons, it lost the bond that it had with this oxygen. So this would fall off as water, it would be positively charged. That carbon would be called a primary carbon because the carbon here would have only one bond left to itself from an R group. If a carbon has one bond to it from an R group, it's called primary. 2 bonds from 2 R groups to the carbon, that's secondary. 3 bonds from 3 R groups to the carbon that's tertiary. If the water falls off and this is a positive charge on this carbon, that would be called a primary carbon, also called a primary carbocation, because it would be a positively charged carbon, so it's a primary carbocation. Primary carbocations are very unstable. So that's a line to remember. Tertiary carbocations are much more stable, much more stable. And of course, secondary carbocations are in between primary and tertiary carbocations. Some secondary carbocations being more stable than other secondary carbocations. But the point, the bottom line is, primary carbocations are very unstable. Tertiary carbocations, much more stable. So producing a primary carbocation would be very unstable, meaning that the hydrogen attacking either of these OH groups is a highly unlikely event because of the instability of the product. We will discuss primary and tertiary carbocations again shortly. Nonetheless, so we have a delta negative oxygen here, the H plus there, the most highly charged thing being the H plus, as opposed to other things in the reaction. Therefore, the delta negative oxygen, the lone pair electrons on this oxygen would be attracted to the H plus. That's breaking this bond, exactly like the previous reaction with the acetal, though now we're looking at a potential ketal being produced. So once the bond is broken because of the H plus, producing OH, the charge on this carbon would therefore be positively charged because the electrons were given up so that this oxygen can bond to OH. So let's look at that. So we have the oxygen here that would bond to the hydrogen. This bond would therefore be broken in order to allow the oxygen to bond to the hydrogen. This carbon therefore becomes positively charged, a formal positive charge on this carbon. And this carbon would be indeed called a secondary carbocation. It would have two R groups, one R group up here, one R group down here. In other words, group of alkanes that are bonded to this carbon, and therefore it's a secondary carbon, much more stable, much more stable than it would have been had a primary carbocation being produced. So we have our secondary carbocation there. What is the most charged thing now in the reaction? It would be right here. So it is going to want electrons, and electrons can be supplied from the diol because these are delta negative oxygens. So one of the oxygens, either one of these oxygens, would be attracted to this carbon like so, and it would bond. It would give up its electrons to the carbon, and therefore as it gives up its electrons to the carbon, the oxygen once again would become positively charged, a formal positive charge. It doesn't like that, so therefore it kicks out the proton, it kicks out the hydrogen. So then as a intermediate to this reaction, we're going to get this bonding here, kicking out its hydrogen. So the intermediate of the reaction would be as follows. We would have, I would draw it up like so. We would have obviously a little bit distorted, but nonetheless, we have the OH group here, and then we have the oxygen here, and then the OH of the diol. So you see that the oxygen from the diol comes in, bonds to the carbon, and then we have our OH group here. So this would be the intermediate of the reaction, and in fact, this is what we would call a hemiketal, halfway towards producing a ketal, even though this is a cyclical compound. So now, once again, because the acid has been regenerated, the H plus has been regenerated in the reaction, we have H plus floating around in solution. Once again, the H plus would be attracted to anything which is delta negative. We have delta negative here, we have delta negative here, we have delta negative there. So the hydrogen could be attracted to any one of these. Now, if the hydrogen attacked this, it would make water. This would fall off. Primary carbocation. Very unlikely. If the hydrogen were to attack this oxygen, well then it would just produce OH again here. That is our diol. So it would regenerate our diol. And then this can also be kicked out. The oxygen can make another double bond with the cyclical group here. And therefore, we regenerate our original reactants. So the arrows are double-sided. Indeed, the hydrogen may indeed attack this oxygen and then form the diol and then regenerate our original reactants. However, sometimes the hydrogen would attack this oxygen here, and therefore by attacking this oxygen here, forming water, falling off as a leaving group, and when this falls off as a leaving group, as water falls off, then the charge on the carbon here would be positive. So in other words, you would get this falling off here, we would have a positively charged carbon here, and because we have delta negative here, positive charge here on this carbon, well, of all the reactions in organic chemistry, among the fastest reactions would be an intramolecular reaction. In other words, if you were to have two chemicals that are floating around in solution, one positive, one negative, yes, they are going to be attracted to each other, and you'll have a reaction, and it would take a certain amount of time. But imagine if one chemical within itself had positive and negative charges, how fast that reaction would be. That would be extremely quick. So we have a delta negative oxygen right here. We have a positive charged carbon right there. So it's really juiced up. It's ready to react. So this would be an extremely fast reaction in which the lone pair electrons on the oxygen, because it's delta negative, is attracted to the positive charge here. Bang, it reacts. Knocks out the proton, and therefore, if you just use your imagination and twist this chemical a little bit, you end up with this as your final product. And so, classic situation for the MCAT exam, they love to take a reaction which you understand, which you know how the different chemicals come together in terms of acetals or ketals, and then they'll just take a chemical just a little different, a little bigger than you're used to seeing, or different shape or whatever, and therefore see if you can use your imagination, but use the same basic organic chemistry knowledge with the basic rules that we looked at. Most charged item or species reacts fastest, positive to negative, and primary and tertiary carbocations, etc. Just knowing the basic rules will allow you to do an innumerable number of reactions. Now let us continue and look at some tertiary and primary carbocations and their reactions in terms of nucleophilic substitution. We will now look at a whole classification of reactions called substitution reactions. Now these substitution reactions are divided into SN1 and SN2. And SN1 reactions stands for substitution nucleophilic first order. So these are nucleophilic substitution reactions, first order. First order means that the reaction depends on the concentration of one compound. So we're going to look and see why these are called nucleophilic substitution reactions and why they are first order reactions. First off, here we have a tertiary compound. And from before, you can know that the R groups stand for alkyl groups, and the X group stands for a halide. So we know that halides like chloride, bromide, and fluoride, these are chemicals that are very electronegative and draw electrons to themselves. And so they would be very happy to have this sort of reaction in which this dissociates. And so what we would get if this were to dissociate is we would get R, C, R, R, and this carbon, if this were to dissociate, would now be positively charged because it would give up its electrons to the more electronegative element, and then we would have plus X minus. So from what we discussed before, I said that tertiary compounds are much more stable than primary compounds. In fact, you can consider tertiary compounds as seriously relatively stable compounds. And so this would be called a tertiary carbocation. And this tertiary carbocation is quite stable. The reason is the following, and here is a statement to memorize, and that is that alkyl groups are somewhat electron donating. And it's just like that you should remember that statement. It's not that alkyl groups are very electron donating, because they're not. Alkyl groups are somewhat electron donating. And here is an example where that feature of alkyl groups is very important. We have 3 alkyl groups surrounding a carbon which is positively charged. Normally carbon would not want to be positively charged. It doesn't mind being partially positively charged, but to carry a positive charge on itself alone, it doesn't like that. However, if it's surrounded by 3 groups, and each one of these groups are contributing electrons to the carbon, it's like carbon has a fire, and each one of these groups are helping to quell the fire, to lower the heat, so that carbon can be as comfortable as possible in the situation where it's holding on to a positive charge. And so when carbon is surrounded by 3 alkyl groups in a tertiary carbocation, it is relatively stable. So this is an important point about the reaction, is that this dissociation will occur spontaneously because the tertiary carbocation is relatively stable. Now let's say, for example, there is an OH minus group in solution, which means they say there's sodium hydroxide or potassium hydroxide. In the MCAT, they're not going to necessarily put a juicy lone pair of electrons on an OH minus and say, go for it. They're going to say something like sodium hydroxide is in solution, but for you, sodium hydroxide should mean Na plus and OH minus. And Na plus is going to sit off to the side and do nothing because it's a spectator ion, and OH minus would be actively involved in the reaction because we know it is a good nucleophile. So when we see this situation, a good nucleophile, a positive charge, clearly this negative charge would be happy to go in here and attack the carbon. And so what we would end up with is R, carbon, R, and then OH. So this would be called, because it's an OH group attached to the carbon, it's an alcohol. Because there are 3 R groups, it's a tertiary alcohol. So this would be called a tertiary alcohol. Now, this is called nucleophilic substitution because at the beginning of the reaction we had an X group attached to the carbon. At the end of the reaction we have an OH group attached to the carbon. So there's been a substitution at the carbon nucleus from X, a halide, to OH, the nucleophile. So that's the first thing, nucleophilic substitution. The second issue is that of first order. The reason why it's called a first order reaction. And that is because this step here is a very slow step. This step here, OH minus, formal positive charge, attacking a formal positive charge, that happens very quickly. So this happens very quickly, but this goes very slowly. This is called the rate determining step. It is the slowest step in a series of steps for a particular reaction. That is called the rate determining step. In fact, every time I think of a rate determining step, I think of a wonderful program on television, family show, The Simpsons. Actually, I don't really believe that, but nonetheless, The Simpsons, there was this episode in which Bart was the only person in town that had the same blood type as Homer's boss. And Homer, trying to get in good with his boss, wanted to get a sample of blood from Bart because the boss was dying from some blood disease, which is in the made-up world of cartoon. Nonetheless, so Homer wanted to take some blood from Bart. So they went into an ambulance and they withdrew blood from Bart. And of course he faints because he didn't have enough blood left in him, but nonetheless, they withdrew the blood very quickly. They packaged it very quickly. It just took a few seconds. They passed it off to another ambulance very quickly. The ambulance went off to the hospital, just took a few seconds. Then once it got to the hospital, there was a porter waiting, took the blood, ran to the elevator, just took a few seconds, got to the elevator. Somebody was waiting in the elevator, took the blood, and started looking around the elevator, singing a song, whistling, and having forgot to press the button on the elevator in order to go to the proper floor. And so let us imagine the following. Let us imagine that every single step after taking the blood from Bart took a few seconds, and then the person in the elevator hung out there for half an hour. Then, when you were to discuss what was the rate of the reaction, how much time did it take to get the blood there, say the time took, whatever, 32 minutes or 33 minutes or whatever, but it took a half an hour for that person in the elevator. Well, what did the rate of the reaction depend on? It depended on the slowest step, because the rate of the reaction mostly depended on that slowest step. And this is the case here. This is the guy in the elevator who's hanging out, because even though a tertiary compound is stable, it's not a very quick reaction for this thing to just dissolve on its own. It's not fast. But OH minus, a nucleophile, a great nucleophile, going in and attacking something that has a formal positive charge, not just partially positive, that is extremely fast. So clearly this is the slowest step. This is the rate determining step in this reaction. Because it's the rate determining step, because the rate of the reaction depends on this compound, on what happens with this compound, this is a first order reaction, SN1. Nucleophilic substitution, first order. Depends on this, not on the OH minus. Furthermore, just as an interest's sake, you will see later that this chemical is too hindered, too bulky for an SN2 reaction to occur. Nonetheless, let's move on to an SN2 reaction and see how they occur. Now we will look at an SN2 reaction. So this is nucleophilic substitution, second order. Now the rate of the reaction would depend on two compounds. That's why it is a second order reaction. So first of all, if you look at the reaction that we're going to see, this is the identical reaction that we just did, except that instead of it being a tertiary carbon with 3 R groups, we see that 2 of the R groups have been replaced by 2 hydrogens, so that this carbon is considered to be a primary carbon. Because it's a primary carbon, when this is placed in solution, this X group does not just ionize. It doesn't just dissociate. And because it does not dissociate, because it would be a primary carbocation. And a primary carbocation, as we said earlier, is just too unstable. And the reason it won't happen is because the R group, being a little bit electron donating, somewhat electron, is just not enough to quell the fire of the positive charge. You need more R groups than just having one. So in reaction, we have this compound and the OH minus group, just like we had previously. And what would happen here is that, well, this carbon would be delta positive. This X group is delta negative, since it is a halide to the right of carbon in the periodic table. And so these electrons would be the first thing that would be attracted. So that's the first part of the reaction. I'll put a 1 here as being the first part of the reaction, as it is attracted to the carbon. And then carbon can only be bonded to 4 different things. The weakest bond must break. The bonds between carbon and hydrogen, carbon and carbon, are generally pretty much equally shared. But the bond between carbon and a halide is unequally shared. And not to mention, halides are on our list of good leaving groups. So when the OH minus comes in, hits the carbon, one of the bonds must break. It will be this one. It breaks. So that would be what happens. And the X group, the leaving group, leaves. And so then we would have the OH group coming in and bonding to the carbon. 2 things to show you about this. One thing is that I would like to show this to you in slow motion, as the OH group is coming in and hitting the carbon. So let's look at what we would call the transition state. So here are hydrogens. Here's another hydrogen. Here's an R group. So this is this part of the molecule, CH2R. and then here's the X group here. The OH minus group comes in from behind to knock up this out. See, the carbon is bonded here to the X group. In order for it to be dislodged, the OH minus group has to come in from behind and hit the carbon and knock out the X group. So as the OH group comes in and starts bonding to the carbon, the bond between the X group is being broken. So this compound here, as it's being written, which would be negatively charged because the OH minus group is coming in with its electrons, this compound is called a transition state, meaning this is what we're going to see before the final product, because this is what's happening as the OH group is just bonding, coming in, bonding, it's breaking off the X group. So it's as if we're watching what happens here in slow motion. This sort of occurs simultaneously, even though I've written 1 and 2 in terms of the sequence of events. The bond starts to break more or less simultaneously, and then the X group is popped out. And so the final reaction, what we have is RCH2. We will have an OH group here plus X minus. So here we have a primary alcohol as our product, and we have the X minus, which was kicked out. Now notice, we started with an X group at the carbon nucleus. We end up with an OH group, nucleophilic substitution. And the reaction depended on these two compounds. We have to have one coming in and one leaving. So it required these two chemicals in order for this reaction to occur, because this didn't just fall off. There was no rate determining step in which something just came apart and then something came in. No. This reaction required both of these compounds. SN2, nucleophilic substitution, second order. The rate of reaction depends on the concentration of both of these compounds, producing our primary alcohol. Next, we will look at the orientation of these chemicals. I'm now going to comment on the orientation of these chemicals. You see, this is the tertiary compound that we initially looked at for the SN1 reaction. And then it ionized, produced a tertiary carbocation, and then it was attacked by OH minus. However, when it ionized, it produced that tertiary carbocation. But what we didn't really look at is the fact that this is a three-dimensional compound. It's not just flat on a board. It really is a three-dimensional compound. And so if you can try to imagine it in 3 dimensions, because carbon is at the center of a tetrahedron, you would be able to imagine that, and a tetrahedron sort of being a pyramidal shaped structure with a triangle at the base, and then there's a top with the carbon in the middle. And so you have to imagine that when the OH minus attacks the carbon, and this is the positively charged carbon here, the OH minus, which will be making its attack, it can attack either here or on the other side. There is no reason why it should attack one side any more or less than the other. In other words, the orientation of the molecule in the end may have the OH group attached to the right side, which is what I showed on the board when we did it just moments ago, or it might be that the chemical actually has the OH minus attached to the left side, which is 50% probability. If all these R groups are the same, which they are according to the way I've written it, then there's a 50% probability that the OH group will attack on this side or attack on that side. In other words, it doesn't have to attack on the same side where the X group was lost, because the chemical is 3 dimensions, so it can come in on the other side. Well, if the OH group attacks on the right side, then we say that yes, it was nucleophilic substitution, and the chemical was not inverted. It was not inverted because it has the same orientation as the original chemical, with the OH group attached on the right side. If the OH group attached to the left side, then we say it's inverted, because the X group was on the right side at the beginning. So if you end the reaction and you have the substituent attached to the left side, which would be the case if it came in here, then we say that the molecule was inverted. So the molecule can be inverted or not inverted, and there's a 50% chance of each. If you have a mixture of compounds where half of them are inverted and half of them are not inverted, which would be the case in this reaction, we call that a racemic mixture. It's a racemic mixture. It's also called a racemate. So that would be called a racemic mixture or a racemate. Now for SN2 reactions in which the OH group, the OH minus group, enters by backside displacement according to the molecule that we looked at in slow motion, where the OH group has to come in from behind to hit the carbon and knock out the X group. Because it always comes from backside displacement in an SN2 reaction, whatever side the X group was on, the OH group, the new substituent, will be on the opposite side. Now, of course, when we did the reaction just moments ago, I kept the same orientation of the molecule only because that's the way we do it in shorthand. We don't usually write molecules with the substituent on the left, but that's not important for you to memorize. But the point is this, that in reality, when the substituent or the nucleophile comes in an SN2 reaction, there's always going to be an inversion of the molecule. So that means the actual final molecule will look like this with CH2R. So that the actual molecule will have the OH group on the opposite side of the chemical. And so that's important because that means that SN2 reactions produce molecules which are always inverted because of the backside displacement, whereas SN1 reactions can have molecules that are inverted and not inverted. And if there's an equal amount of each, then we call that a racemic mixture. Now we will look at carboxylic acids. So here's the functional group for carboxylic acids. It's a carbonyl group with an OH group. Carboxylic acids are the most acidic organic chemical. Now, we have to keep this in perspective. Yes, it is the most acidic organic chemical, but compared to inorganic chemicals, the organic acids basically are not very acidic. They're weak acids, but they're very important in organic chemistry. So when we talk about organic chemistry, these are the most acidic organic chemicals. Why are they so acidic? This in itself is a very common MCAT question. Why are carboxylic acids so acidic? And the reason is because of its gain in resonance energy. So remember, an acid, one of the definitions of an acid is that it is a proton donor. So we have to imagine if this carboxylic acid were to give up a proton, release a proton, what would be the result? What is the stability of the product? One of the points we made earlier. So the stability of the product, this is what we would get. We would get this. O minus, which is, of course, equivalent to writing this. And this is what's called resonance structures. Here are two equal structures we can write at the moment that the proton is delivered, and we're looking at the stability of the product. We get this anion. You may remember from high school, an anion, R negative, AN ion, R negative ion. So we have this anion being produced. And this anion, because it's called a carboxylic acid, this anion is called the carboxylate anion. You'll hear the word ate at the end of many types of anions. So this is called a carboxylate anion. So you see that there are two equal ways of writing this carboxylate anion. There's no reason why there should be a double bond up here and not down here, or vice versa. And as we saw in general chemistry, It is not the case that when you write resonance structures, two equal structures for a compound, it is not the case that it is resonating back and forth between these compounds. And in truth, there is no double bond here, there is no single bond, but rather, in truth, if we were to really write this the proper way, we would see that there is sort of delocalization of the electrons in the bond between the oxygens, so that there is no single bond or double bond in the carboxylate anion, but truly there's about a bond and a half for both of them at all times, because the electrons are delocalized. It is this, we call this a gain in resonance energy. Once it releases the protons, and you can have these two equal resonance structures that we can write for this carboxylate anion, we say there's a gain in resonance energy, it is more stable, therefore it is more apt to lose the proton. And therefore, that is why carboxylic acids are 10 to the 10 times more acidic than its native alcohol. Meaning, if there's an alcohol with the same number of carbons in it, compared to a carboxylic acid, the acid is 10 to the 10 times more acidic, which is really an incredible number. And the reason for that difference is because of the gain in resonance energy when the carboxylic acid loses a proton. The next thing we'll look at is what can influence the acidity of a carboxylic acid. My question to you is straightforward. Which of these two compounds is more acidic? You may want to pause and consider your response. Well, first of all, if you look at this particular compound with two carbons, and it is a carboxylic acid because of this functional group, this is a famous carboxylic acid called acetic acid, found in, of course, vinegar. This here is different, and the only difference is that we have an X group here. There is a halide, therefore, which is present here. So therefore, all we need to do is to look at what the presence of this halide would do to change things in this chemical. Then we would know which of these two would be more acidic. Well, we know that a halide is delta negative, and we know that it is drawing electrons to itself. So it's pulling electrons to itself. So this compound, compared to this compound, would be a compound that would love to have electrons in the compound. Well, how could it get more electrons in the compound if it kicked out a proton? In other words, if it were to release this proton and have the formal negative charge like the carboxylate anion, which we just looked at, then that would be able to satisfy one of the desires of an electronegative atom. By adding an electronegative atom, it is going to increase the acidity of this compound because it is more desirable for it to release a proton. Furthermore, consider the following. What is the charge on this carbon? It would be delta positive because it's attached to a delta negative element. Then the charge on this carbon here is also delta positive because it's attached to delta negative elements. Well, we have two delta positive carbons which are attached to each other. What do you think about the stability of the neutral molecule? Very unstable. There are two delta positive things that are attached to each other. And we know that opposites attract, like charges repel. So this neutral molecule is very unstable. But if it were to kick out the proton and get a negative charge, well, we know that we have this CH2 here, we have the carbon here. We know that this would create a situation where we have an O minus, and we know that this creates a resonance structure in which the electrons are delocalized, meaning this delta positive carbon, its positivity will be reduced by the proximity of the electrons which are moving up and down the system, reducing the positive charge, reducing the repulsion between these two carbons. Therefore, this compound is more acidic, definitely, than acetic acid for two reasons. One is that the neutral form of the compound is unstable, and because the anion has increased stability. We are now going to look at the tetrahedral intermediate. This particular compound is called an ester. The functional group of an ester is a carbon which is double bonded to an oxygen, and that same carbon is bonded to an OR group. So this is the functional group of an ester. It happens to have as a substituent a benzene ring. We will look at benzene rings in greater detail later. But this is a benzene ring, and when the benzene ring is a substituent, it is called a aryl group, or more commonly a phenyl group. Because it's called also a phenyl group, it's sometimes symbolized as pH as for a phenyl group. So I'm going to stop drawing this because I have difficulty drawing, and I will put a pH every time the phenyl group comes up. Nonetheless, so here's the reaction with NaOH and alcohol. So if you were to see this reaction, hopefully by now, the first thing that you would say is, okay, if this is in reaction, we have Na plus OH minus. And then right off the bat, you would say, sodium is just going to hang around. It's a spectator ion. It's not getting involved in the reaction until the very, very, very end. Then there's OH minus, great nucleophile, and it is fully charged. Then there is alcohol in solution, ETOH. The oxygen is delta negative. However, if something's going to be reactive in this reaction, it's going to most likely be the thing which is most highly charged, and that's the OH minus. In other words, the delta negative charge on the oxygen here is no match for the formal negative charge on the oxygen here. Therefore, this would be most reactive. And in terms of looking here, well, we have delta negative oxygens, and then clearly this carbon here, which is attached to not other than two oxygens, one here and one there, this carbon here must be very delta positive because of oxygen withdrawing electrons being more delta negative in two spots. So this negative charge will be attracted from the OH minus to this delta positive carbon, hitting this delta positive carbon and therefore breaking the weakest bond, which would be here, knocking it up like so. So then we have OH minus attacking here, attached to this carbon, and then electrons being knocked up this way. So our intermediate would look something like this. It would be our phenyl group here, and then this would be attached to our carbon, the oxygen, knocked up its electrons. Then we have down here the OH group, which just attached, and then we have the OCH3 group over here. And so this is what is called the tetrahedral intermediate. First of all, it's the intermediate in the reaction because the reaction is not over. And second of all, carbon is in the center of a tetrahedron. And all that means is that carbon has indeed 4 bonds. Anytime carbon has 4 bonds, it is in the center of a tetrahedron. So here is our tetrahedral intermediate. A tetrahedral intermediate is extremely unstable. Therefore, a reaction is going to occur very quickly. There's too much oxygen around here, too many delta negative competing factors, all of them pulling electrons to himself. But then carbon is delta positive. It's very delta positive, on top of which there's a lone pair of electrons right there. And we said before, molecular reactions happen very quickly in comparison with intermolecular reactions. So here we have a negative charge. Here we have a delta positive carbon. Clearly, this is going to be a very quick reaction in which this is going to want to come down and hit this carbon as quickly as possible. But if it were to come back down, somebody's got to go. Well, will it be the phenyl group? This is a carbon-carbon bond. Very strong. Carbon-carbon bonds are very strong because it's equally shared. But here are two bonds which are unequally shared because oxygen is drawing electrons to itself. So basically, both of these are not good leaving groups. As opposed to halides, which we saw before, are excellent leaving groups and would be the first to go. Both of these are not good leaving groups, but of the two, the best of a bad bunch would be the OCH3 group, which would be forced to leave, and so we would have the electrons come down, the OCH3 group would leave, and then we get our phenyl group attached to the carbon. Now it's double bonded because the electrons have come down and attached to the carbon, and this is attached to the OH group. Then we have plus OCH3, and this is negatively charged. Actually, there was once an MCAT question very similar to this one, and it asked what was the result of a particular reaction, and then they had as a possible answer something similar to this as a possible answer. And so I'm sure many students felt great that they had accomplished the problem, they'd gone through all the steps, delta negative, delta positive, everything, and then they were finished and they were happy, and then they didn't get it right because the reaction is not over. Because once you see this reaction as it is, you should be able to look at this part of the reaction and recognize what this is. This is a carboxylic acid. So this is a carboxylic acid, which we know is a proton donor. And this is a compound which would love to have a proton because it has its negative charge. It's not particularly stable compound. It would love to have a proton. It is a proton acceptor, and therefore it is a base. And you may remember from general chemistry that whenever you have an acid plus a base, you get a salt and a neutral compound. So this is an acid plus a base. So our salt would be the product after this proton is given off. We get pH, C, double bond to the oxygen, O minus, and sodium floating in solution. So that brings us our salt, Na plus, and then this is plus HOCH3. So this is our neutral compound, which is methanol. And here is our salt. So we have an acid plus a base, gives you a salt plus a neutral compound. So we've come to the final conclusion of this particular reaction. But the whole reaction is based on electronics and very basic rules of organic chemistry. We are now going to look at amides. The functional group for an amide is the carbon double bonded to the oxygen with the carbon also bonded to the nitrogen. There are a couple of features which are very important to remember about amides. To begin with, the nitrogen, as we know, when the nitrogen has 3 bonds, it has a lone pair of electrons. Now, when we look at the resonance structures, remembering by looking at the periodic table that oxygen being to the right and high up, and oxygen is more electronegative than nitrogen. Nitrogen is electronegative, but oxygen is more electronegative. Therefore, oxygen will draw electrons to itself. So as oxygen draws electrons to itself, we can envision these lone pair electrons in the nitrogen being attracted to this delta positive carbon, these electrons going into this bond, forming a double bond between the carbon and nitrogen, then breaking the pi electrons up here and sending these up to the oxygen, and oxygen is very happy with that because it gets these lone pair of electrons. So then we can imagine that one of the resonance structures that we can write for this compound would be R bonded to carbon, oxygen with its lone pair, double bonded with the nitrogen, and then we have R prime, R double prime. So we can imagine that this is one of the resonance structures that could be suggested for this particular compound. Now, of course, this would be negatively charged, and then this would be positively charged because it gave up its electrons, and the overall molecule was neutral to begin with. Well, as we know, these two compounds are not resonating back and forth. There's actually some sort of way in which those lone pair electrons are actually delocalized between the oxygen and the nitrogen. So if we were to just draw that, R prime and R double prime, then we would write that this is sort of a bond here, but this is delocalized electrons going up like this, where this is, very delta negative, and this is a delta positive nitrogen because it's giving up its lone pair of electrons into this bond where it's sort of delocalized along this area. Well, a couple of things to say. First of all, when we started organic chemistry, we talked about conformation, and that is free rotation about single bonds or sigma bonds. And so we would have expected that there would be free rotation between the carbon and nitrogen. However, we don't get to see that in this compound. There is restricted rotation. It means it's possible that there could be rotation, but it is very difficult to rotate among the carbon-nitrogen bond because it's not a simple single bond, because the electrons from the nitrogen are partly delocalized, and so it's not a simple single bond, and therefore there's not free rotation here. So that's one important point to remember about amides. The second important point to remember about amides is that the lone pair electron on the nitrogen is not available for bonding as it usually would be. For example, when you look at ammonia, NH3, which has lone pair electrons, we have NH3 like this. It has a lone pair electron. When we add a proton, H+, the proton adds to those lone pair electrons, and that produces NH4+. So this is the ammonium ion, and that's produced as a result of the lone pair electrons on the nitrogen. However, the lone pair electrons on the nitrogen of an amide are not available for bonding as you would get in most compounds with nitrogen, because the lone pair is involved in this delocalization. Now we will look at a common type of MCAT question based on this concept. So my question to you is straightforward. Which of these following chemicals is nitrogen serving as the strongest base? So in which of these chemicals is nitrogen serving as the strongest base? Perhaps you may want to pause and consider what you would provide as a response. So let's work it out. Here clearly is an amide. It's carbon double bonded to oxygen where the carbon is bonded to a nitrogen. That is the functional group. Amides, as we've seen already, the nitrogen is not available for bonding. So what's the importance of that? Well, if they're asking where does nitrogen serve as the best base, well, one of our definitions of base is that a base is a proton acceptor. So if you have something which is going to accept a proton, which is positively charged, clearly the nitrogen must be negatively charged, or at least partially negatively charged. So we would be looking for the nitrogen, which has the greatest partial negative charge. The more the partial negative charge is, the more it would attract a proton, the stronger base it would be. In other words, we take their question, then we translate it into language which is practical so that we can look for something on a practical basis. The most delta negative nitrogen, which is obviously a much more simple concept than just thinking, well, what's the strongest base? Okay, we're looking for the most delta negative nitrogen. Well, we've already seen that the nitrogen in an amide is delta positive because its lone pair electrons is involved in a resonance structure or delocalization of the electrons. And so this would be a decidedly poor base. It would be very poor at attracting a proton to that nitrogen. So this A is definitely out of the question. Then we have ammonia, and we know ammonia has a lone pair of electrons, and therefore it would be very attractive for a proton to land on ammonia, producing NH4, the ammonium cation. So yes, definitely ammonia would be a very good base. So then we have this compound. We have a methyl group, which is an R group, attached to the nitrogen. In what way will this affect the delta negative aspect of this nitrogen? Well, because there's a methyl group attached to it, and we know by definition alkyl groups are somewhat electron donating, meaning that compared to just having a hydrogen, because there's this alkyl group, it is somewhat electron donating. That means it will make this nitrogen even more delta negative than this one. And then here we have a nitrogen with two methyl groups attached to it. That is two alkyl groups attached, both of them being somewhat electron donating, somewhat donating electrons to this nitrogen. Therefore, this nitrogen indeed would be the most delta negative of them all because of the alkyl groups, which are inducing it to be even more delta negative than it would be in ammonia. Therefore, the correct answer would certainly be D. The two categories of reaction mechanisms which you must understand are substitutions and elimination reactions. Now, we've looked at substitution reactions. Now we're going to discuss elimination reactions. So we start with an E1 reaction, which again would be elimination first order. So the rate of the reaction will depend on the concentration of one compound. So here we have a compound. It's cyclical. There are 6 carbons, 1, 2, 3, 4, 5, 6 carbons, and it's an alcohol. So it would be called cyclohexanol. And there is an acidic solution which is heated. This is the symbol for heat or energy being provided to the reaction. Of course, I put an H plus there, but once again, on the MCAT exam, they're not going to put an arrow and put a nice H plus with a juicy positive charge on it, making it very easy for you to know what would happen next. They might say sulfuric acid. They might say polyphosphoric acid, hydrochloric acid, or any number of acids. But in organic chemistry, when you hear the word acid, you should have a Pavlovian response in which right away you think of H plus, because that is going to be the thing which is most reactive in that vessel, is going to be the H plus in the acid. That is what you have to keep an eye on. So here we have H plus. It is the most reactive thing. We have OH here, which the oxygen is going to be delta negative, of course, because it's attached to a carbon, which itself would be delta positive. So the electrons here would be attracted to the H plus. That would form water. Water is a great leaving group, which we've said already, and therefore that would fall off as water. Then we would have our cyclical compound with its 6 carbons, and because this falls off as water, taking along with it the electrons, because when it comes in, this H plus comes in, the charge on the oxygen will therefore become positive, because oxygen will give up its electrons to H plus in order to bond with the hydrogen, and therefore oxygen will, because it's positively charged, it will withdraw electrons somewhere. It pulls it from here, forming water, falling off as a great leaving group, and therefore the carbon here would have a positive charge, a formal positive charge. This would be called a secondary carbocation. It's secondary because this carbon has two R groups attached to it, and it is a carbocation because it's a positively charged carbon cation. So this is a carbocation. Now, there's no nucleophile around. There's no OH minus to jump in here and so on. So carbon is going to be looking around for electrons to draw to itself. And we know that in these other carbons, there must be a couple of hydrogens, because there must be the number of hydrogens necessary for there to be 4 bonds to each of these carbons. So this carbon must have 2 hydrogens. Indeed, this carbon must have 2 hydrogens. Well, let's look at one of those hydrogens. One of those hydrogens here would be attached to this carbon. Of course, there's another hydrogen also attached to the carbon. But for the purpose of this reaction, we'll just look at one of them. This positively charged carbon wants electrons. It looks around and it starts to pull electrons from the neighboring hydrogen. So it withdraws these electrons to itself because of the attraction of these negative electrons to this positive charge, kicking out the protein. So kicking out the hydrogen. So then we have the hydrogen being lost here. We have the OH group, which was lost at the beginning. So we have these 2 groups which are lost or eliminated from the reaction. That's why it's called an elimination reaction. And then our final product, as these electrons bond here, forming a double bond, a bond between this carbon and this carbon here. Therefore, we get the cyclical structure, and we have a double bond here. As a result of the fact that we lost the OH group, it was eliminated. We eliminated the H group, all within the same compound. The hydrogen which was used here was kicked out here, so it's regenerated as a catalyst for the reaction. It was not used up in the reaction. The rate of the reaction depends on the concentration of this compound. One compound, elimination, first order. We end up with an alkene. This particular alkene, which has a double bond, of course, all alkenes have a double bond. This particular alkene would be called cyclohexene because there are 6 carbons, so it's cyclohexene. So this was all produced by elimination, first order. Now let us look at another E1 reaction. Let us look at this compound. This compound would be called, well, there are 4 carbons, 1, 2, 3, 4 carbons. So it would be called bute. It's an alcohol, so it would be called butanol. And then we must indicate where the alcohol group or OH group is attached. So it's attached at the second carbon. So this compound would be called 2-butanol. So they can say there's 2-butanol in an acidic solution. Right away, this is what you would write. So we've got H+, the most charged substance there. It's going to be attracted to the oxygen here, delta negative. It will create water. It will fall off. It produces the intermediate, which would look like this. So I'm just not writing the hydrogens, but this is essentially what the intermediate would be. We would call this intermediate, by the way, 2-butyl, because it's missing a hydrogen at the carbon position, the second carbon, so it's called 2-butyl. And this compound, this alkyl group, an alkyl group is simply an alkane minus a hydrogen. So this compound is used very often on the MCAT exam because from this compound you can do all types of reactions, including substitution reactions, elimination reactions, different orders of reactions, etc., etc. So this is very commonly discussed on the exam, this 2-butyl compound. So here we've created it. This is an elimination first order. This is the first part of the reaction. But here is where it becomes a little bit more interesting, and that is because we saw already that the positively charged carbon, here is a secondary carbocation, the positively charged carbon will withdraw electrons to itself, forming a double bond, and it would take electrons from neighboring hydrogens. And we know there's a couple of hydrogens here, we know there's 3 hydrogens here. And the question, of course, is where will it choose to pull electrons to itself? And what happens is that it preferentially chooses electrons from this carbon to come in and to form the double bond. So it preferentially does that. So basically from this reaction, we have two possible products. One product in which it chooses to take hydrogens from here. This product would look like this. It would have this, it would have its double bond between these two carbons, and then you just add the number of hydrogens necessary. And this particular product would be called 2-butene. It ends in -ene because it's an alkene. 2 indicates the lowest carbon where the double bond is attached. So it's 1, 2, that's where the double bond is attached. It's 2-butene. The second possibility of a product would be if the carbon withdrew electrons from a hydrogen on the right side here and bonded with that here. And therefore, we would have, as a second possibility of a product, we would have carbon, single bond, carbon, single bond to another carbon, and then this one would be double bond. And so here, again, we would have butene, but the lowest carbon, which has the double bond, is the number 1 carbon. So this compound would be called 1-butene, while this is 2-butene. 1-butene would be considered to be the minor product. 2-butene would be the major product. Why, you ask? And the reason is because this product is called di-substituted, meaning the functional group is the carbon-carbon double bond. This is the functional group for this particular compound. And at the functional group, there are 2 alkyl groups attached. One on the right, one on the left. 2 alkyl groups. So it's called a di-substituted compound. It has 2 substituents attached at the functional group. It's di-substituted. Here we have the double bond, the functional group, and there is only 1 alkyl group. It happens to be ethyl. It happens to have 2 carbons, but it doesn't matter. There's only 1 alkyl group attached to the double bond. Therefore, it is mono-substituted. Well, when there's more substituents, it helps to stabilize the double bond. And therefore, this compound is more stable because it is di-substituted than this compound, which is mono-substituted. And therefore, this compound, 2-butene, would be the major product. Now let us look at E2 reactions. We will now look at elimination second order. So that's an E2 reaction. It is called elimination because in the original organic chemical, we will see that a couple of atoms will be eliminated, and that will reduce it into a double bond. Then it's called second order because this time the rate of the reaction will depend on the concentration of 2 compounds and their interactions. So this particular compound, well, we have 1, 2, 3, 4 carbons, so it's bute. It's an alkane, it's a hydrocarbon. And we have bromine at the second carbon position. So this is 2-bromobutane. This is a very popular MCAT chemical as well because there are many different types of reactions that can occur using this particular chemical. So that's 2-bromobutane. Here we have potassium with a base. Now, if that base happened to be OH minus as a base, then I think you would say, as your first suggestion as what would happen in this reaction, would be that this carbon is delta positive, that's delta negative. So if this was OH minus, then the OH minus would be attracted to the delta positive carbon, hit this carbon, knock out the bromine, and there would be a transition state in which when the OH minus is coming in, the bond with the bromine is being broken. Therefore, OH minus has to come in from backside displacement. That would create a secondary alcohol, 2-butanol. The molecule would be inverted because the OH minus would have to come in from behind to knock out the bromine. So I believe that at this point, that's what you would suggest if this base was OH minus, and that would be the most likely scenario. However, if this was a big, bulky base, and it was a huge base, therefore it wouldn't be so small and nimble like OH minus to be able to come in here and bond, because don't forget there's a CH3 group here, there's an ethyl group here, they occupy a certain space, so it has to be a particular size to be able to get in here and to knock that carbon and to knock out the bromine. But if it was a large, bulky base, for example, consider the following. Instead of OH minus, consider O, C, CH3, CH3, CH3 minus, as opposed to just OH minus. Clearly, this is a big, bulky base, and you should be able to easily name this base. There are 4 carbons, 1, 2, 3, 4. So you know the word but is going to be in there somewhere. And this is a tertiary carbon because there are 3 R groups attached to it. So we know the word tert or T, just the letter T, would be included in this. So there's a but and then there's the O minus. Well, we know that this is called hydroxide. This is the hydroxide. So this is called tert but oxide. So tert butoxide or T-butoxide. So this is a very big, bulky base. And a big base is not going to want to engage in a nucleophilic reaction, which would be very easy for a OH minus. A big base, and bases are substances which like to attract or to take on a proton for itself. So it would like a proton. It doesn't want to do a nucleophilic reaction for it. So because it's big and bulky, it will preferentially take primary hydrogens. In other words, it would preferentially take, see, this is a primary carbon position. So this, because it only has 1 R group attached to it, this has hydrogens here. So the big bulky base would like to just pluck the hydrogens, sort of like grapes or something, and it would rather take them where they're easiest to take. So it would rather take them right from here. And if this big bulky base was to take a hydrogen from this carbon, what would be the charge on the carbon? It would be negatively charged. Because if you take a proton, if the base takes a proton away, then the charge on the carbon would be negatively charged. And this carbon over here is delta positive. So if this is negatively charged, and this is delta positive, there would be a great force of reaction because it's an intramolecular reaction. So this negative charge would quickly knock and hit this delta positive carbon because of the opposites attracting. And then this carbon can only be bonded 4 times, so somebody's got to leave, so this bromine would leave. So the negative side would come in here, bond here, and then the bromine would leave. So then we would have as a major product carbon, 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 double bond to carbon. So this, in fact, as our major product, would be a 1-butene. So in other words, it occurs in such a fashion that this is mono-substituted. Why? Because of the mechanism of reaction. It's not as if we had a choice that it could go this way, it could go that way, and it doesn't really matter, so it only depends on the stability of the product. No, this time it really did matter, the mechanism of reaction, because it's a big bulky base. It's very easy for it to pluck off hydrogens over here, and then we have this reaction. Now you might wonder, would it pluck off hydrogens from this carbon over here? No, because if it took a hydrogen from this carbon, we would have a primary carbanion, which is a negatively charged carbon. So it's a primary position carbon. But the problem is that once this carbon is negatively charged, it can't do anything with its negative charge. It can't give it off somewhere. It would be sitting there with a negative charge. It can't give it to this carbon because this carbon doesn't have a leaving group. It has a couple of hydrogens. So it would be stuck with a primary carbanion. Extraordinarily unstable compound. So that would not occur. Can this big bulky base take some hydrogens from this secondary position? and in which case, if it took it from the secondary condition position, this negative charge could bond, make a double bond between these two carbons and knock out the bromine. Indeed, it can do that. It wouldn't do it very often because it's much easier to take it from the primary carbon. So, but every so often it might take one or two from this particular position, and therefore we would have this as our product. We'd have carbon, carbon, then double bond, carbon, carbon, because the double bond would form between here and bromine would be kicked out. Either way, these are elimination, second order reactions, and producing either 1-butene, which would be our major product in this case, or 2-butene. There's also a hydrogen on this carbon right here. Is it possible that this big bulky base would pull off a hydrogen from this carbon? No way. Once again, it's the same reason as for this particular position, and that is that, or similar reason, because you would have a secondary carbanion and there would be nothing to do with the negative charge. You couldn't get rid of it because this carbon has a leaving group, but it can't dish off the extra electrons to one of its neighboring carbons, and therefore it would be stuck with this extra set of electrons. So that would not occur for this hydrogen to be removed, nor for the hydrogens over here to be removed. Those are extremely improbable events. But to produce this and this is very probable, and this is less probable. Now that we've seen how to make an alkene, we will now look at reactions with alkenes. And so here is an alkene because there's a double bond to the carbon. And so, well, let's name it. This alkene, the longest chain, has 1, 2, 3 carbons. So it would start with prop, end with ene, so it's a propene. And then at the second carbon, there is a methyl group. So this would be called 2-methylpropene. And this is an alkene plus an acid. So the alkene, as its functional group, it is the double bond. It is the most reactive site in the alkene. The reason is this is an electron-dense center. So here is an acid, HBr, could be HCl or whatever. Now, as soon as you see the acid, you should be thinking of H plus and Br minus. H plus is something which is going to be very attracted to electrons. And in fact, when we looked at our definitions, our basic definitions for organic chemistry, that was our definition of an electrophile. An electrophile is something which seeks electrons. It is literally electron-loving. So hydrogen is electron-loving. And here is an electron-dense center. So hydrogen will add to the double bond, and therefore it will add to either this carbon or this carbon. The question, of course, is which one will it add to preferentially? Well, if hydrogen were to add to this carbon, then it would withdraw electrons to this carbon so that it could add here. Therefore, this carbon would end up being positively charged. If this carbon is positively charged, therefore we would have a primary carbocation, and we've already seen that that's very unstable. However, if the hydrogen were to add to this carbon, withdrawing electrons in this direction, therefore breaking the bond and withdrawing in this direction so the hydrogen can add to this carbon would become positively charged. And if this carbon becomes positively charged, well, therefore, we would have a tertiary carbocation, and obviously that it would be stable. So if we have the tertiary carbocation, that would be stable. That is the most likely reaction. So we would have CH3, we'd have carbon, we'd have CH3, we'd have CH3 here because the hydrogen added to it. This would be positively charged. And then because Br minus would be floating around in solution, not up to anything much, but it would see a positive charge, and therefore it would bond to this. And so then we would have a bond like so. And this would be our product. This product which occurred using the most stable intermediate would be called a Markovnikov product. This would be called our Markovnikov product because it did come through the most stable mechanism. The anti-Markovnikov product would be the product that would occur if the H plus had added to this carbon at the beginning of the reaction, creating a primary carbocation, not very probable, and then the Br minus adds to that. So then our anti-Markovnikov product would be carbon here, CH3, the carbon would have had the hydrogen add to it, then we'd have our CH2, and this is where the bromine would end up adding because that's where the positive charge would end up. So this would be our anti-Markovnikov product. This would be our Markovnikov product. Now, Markovnikov himself defined a Markovnikov product as follows. It is a product that occurs when you have an alkene plus an acid. The hydrogen would add to the least substituted carbon preferentially. So that's Markovnikov's definition. The hydrogen would add to the least substituted carbon preferentially. So in this particular situation, this carbon has 3 substituents attached to it, 3 ligands, and this carbon, well, it just has 1 because the hydrogens are not considered to be substituents. And so this one has the least substituents compared to this particular carbon. So that's one way of looking at it. But students don't memorize it that way. Most students memorize it. But Markovnikov's rule is that the hydrogen adds to where most of its buddies are. In other words, hydrogen will add to the carbon with the most hydrogens, and that is exactly the least substituted carbon. So this hydrogen would preferentially add to this carbon because this carbon has 2 hydrogens attached to it, whereas this carbon has no hydrogens attached to it. So this hydrogen would preferentially add to this carbon. So then preferentially, because it adds to this carbon, producing CH3, this carbon becomes positively charged. The Br lands in there and bonds here. So this is the Markovnikov product. We will now look at another mechanism of reaction involving an alkene. So here we have 3 carbons, so this must be propene. And this is in solution. Now, on the MCAT exam, as I've mentioned already, they're not going to put a nice H plus on an arrow and water over here, making it clear what's going to react with what. But they may say something like, propene is in an aqueous acidic solution, and blah, 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 and give you a bunch of other information which is irrelevant. As soon as you hear propene, you write it down. Aqueous, water, solution, which is acidic, proton, that's what you think of. Then you look at what is the most reactive thing in the substance. It'll be the most charged element or species, and this is H plus. So we have the double bond, which is here. So that's going to break up as it's attracted to the positive charge, because this is the electron-dense center. And once again, where does the proton preferentially add? Well, you can use Markovnikov's rule, saying the least substituted carbon, which would be this carbon, because this carbon, compared to this carbon has this substituent, which is extra, and this carbon does not. Or you can just use the student's rule, which is hydrogen will add where its buddies are preferentially, and so it has 2 friends here, it only has 1 here, so the hydrogen would rather add to this carbon. So then you would get a secondary carbocation. So you would have 2-propyl, you can call it 2-propyl, as your intermediate. And then you would have this delta negative oxygen with its lone pair of electrons, and therefore this is the most charged species at this point. This is going to be attracted to it, as opposites attract, to the carbon. When oxygen gives up its electrons to the carbon, the oxygen would be positively charged. It will have 3 bonds. When it's positively charged, it will want to draw electrons to itself because oxygen is an electronegative atom. And so it will draw electrons, it will kick out one of its hydrogens, a proton, thus it regenerates the catalyst of the reaction. And then we would end up with this as our product, which is OH group attached to the carbon, and then this carbon. So this would be called a secondary alcohol. You can also call it 2-propanol, and this would be our product. Now this would be called our Markovnikov product, as it occurred through the most stable mechanism with the hydrogen adding to the least substituted carbon. Had, for whatever reason, the hydrogen added to this carbon and created a primary carbocation as an intermediate, then what would happen is the OH group would attack this carbon and the OH group would add to that carbon, and therefore we would have as a product carbon, 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 OH. And so this product would be a primary alcohol. It would be called 1-propanol, and this product would be called an anti-Markovnikov product. So this is our Markovnikov product, this is our anti-Markovnikov product. Now, it is important to understand mechanisms of reactions, because even when we say that something is improbable to occur, that means that it still occurs, but it's unlikely. And the MCAT can actually play with that. In other words, they can say, in this, which of the following is the product? If you look at the answers, if you have the major product and the minor product as possible answers, obviously you choose the major product, because in the MCAT they ask you to answer with the best answer. What is the best answer to the question? And so if you have a choice between a major product and a minor product, then you choose the major product. However, sometimes on the MCAT exam, what they'll do is they'll ask you a question on organic chemistry and the major product is not even among the possible answers. The only thing that would be there among the possible answers sometimes would be the minor product. In other words, they want to know whether or not you know the two possibilities for a given reaction. And so here you can clearly see how you can have one or the other reaction. Even though you know that one of the reactions is improbable, you know that it is possible to have an anti-Markovnikov product. So if you had a choice between what is the correct answer, you would go with the Markovnikov product. If the Markovnikov product is not an option, then you take the anti-Markovnikov product as your answer on the exam. Finally, something in life which is truly free. Free radicals. Free radicals are in so many different aspects of human life. Everything from taking life, from giving life. In fact, free radicals are found, they can be created by ultraviolet light in the skin, in the cells, and these free radicals, they're so highly reactive, so unstable, they can actually cause permanent damage to DNA and therefore cause skin cancer. Just like it can take life, it can give life. It has been found that free radicals are used by sperm in order to blow a hole in the envelope of the egg in the act of fertilization. Free radicals are also found in your breakfast cereal. A large hindered free radical called BHT is found in the packaging of most breakfast cereals. It sort of just hangs around in the packaging, waiting for free radicals to be formed in the cereal itself. Now, free radicals in the cereal will change the cereal, and therefore it will change the taste. It's what we call staleness. And so by having this free radical, hindered free radical around the cereal, it's able to mop up the free radicals that are formed in the cereal, and it's able to keep the cereal fresh for a longer period of time. So how do you make a free radical? Here is a substance. As we know, X stands for a halide, so this could be Cl2 or Br2 or whatever. And here we have HF. And from your knowledge of physics, you should immediately recognize HF as energy, because of course E equals HF. So we can represent energy, light energy, as HF over the arrow. So when this substance is exposed to light energy, we can create a free radical. And the free radical is going to be symbolized by X dot. So we have 2 here, so this would be 2X dot. So this is a new substance. It's not X negative, which we've seen before, which when we see a negative or a plus, a formal charge on a substance, we know that represents an electron pair, either an extra electron pair when it's negative, or when it's positive, it's missing an electron pair. But when we have X dot, that means a single, unpaired electron. That is a very unstable situation. So these compounds are highly reactive because they're unstable. So this particular step, when we take a compound which has no free radical, and then we apply energy and we create free radicals, this is called the chain initiation. Once we have a free radical, many different things can occur. One of the possibilities is that we can get propagation of these free radicals, meaning a domino effect where one free radical creates another, etc. For example, let's say that we had an organic chemical. This organic chemical will symbolize as RH. So it's like an alkane. So it's RH. So there's just an H hydrogen which is attached to the particular alkyl group forming an alkane. Now if you were to add a free radical which we have just created, this free radical being so unstable will just tear one of the atoms off the alkane or off the organic chemical. Obviously this is going to change the organic chemical from its original form. So this will just tear it right off, and then what we would have is we would have R as a free radical, and then we would have plus HX, which would be the new compound, as the X group tore the H off and left an unpaired electron on the R group. Likewise, this R group, which has now been created, which is a free radical, if it is exposed to the original compound that we have, this R group can therefore rip that off, and we produce another chemical plus another free radical. Therefore, our free radical has been regenerated. And then we've changed the compound. Whatever compound we had originally has changed. In nature, when chemicals and molecules are exposed to energy, the sunlight, many of these types of molecules and substances can deteriorate, can rot, and there's many of these processes are caused by free radicals which tear apart organic chemicals and therefore change the original substance. The fact that we start with a free radical, we end with a free radical, these kinds of steps are called chain propagation steps. So we have the initiation up here, we have the chain propagation over here, and then in the third of the possibility of steps that could occur with free radicals, we can have free radicals, one plus another, producing new compounds. So this would be called a chain termination step, in which you have a free radical plus a free radical creating the end of a chain. And of course, there are many different possibilities of these free radicals that could be added to each other, creating a chain termination. So these are the different ways in which free radicals can be generated, can be propagated, and can be terminated. We are now going to look at a series of reactions called redox reactions. Redox reactions are reduction or oxidation reactions. You do not need to memorize the mechanisms for these reactions for the MCAT exam. So unfortunately, unlike what we've been looking at throughout the organic chemistry, this is a section where you sort of need to memorize what happens during an oxidation or during a reduction in terms of what types of products you would expect. Some students like to memorize that during an oxidation, it's like adding oxygens. But that has to be specified, and you'll see how. Some students like to memorize that reductions it's like adding hydrogens, and we'll specify and see how shortly. First, a couple of examples. Here is KMNO4. KMNO4 is a very popular oxidizing agent. It can be used in two different ways, either under mild conditions. Mild conditions means neutral pH and mild temperature. Or KMNO4 can be used under abrasive conditions with OH minus and heat, symbolized by delta. So these are different conditions. There is an oxidizing agent called CrO3, and CrO3 is a mild oxidizing agent, and therefore it could replace KMNO4 as an oxidizing agent in many different reactions. Nonetheless, KMNO4 is the most popular oxidizing agent that is used. This particular compound, you should consider naming these compounds before I mention them, but this one has 5 carbons, and there is a double bond here, so this would be called cyclopentene. So when it is oxidized under mild conditions, the product would be as follows. Now, this triangle, of course, is a solid triangle, so that means that it's coming out of the plane, and this is oxidized in this way. And then in behind, we would have some hydrogens, which we don't even really need to draw. But nonetheless, just to be more specific, here we see our product. This is the way it would be oxidized. What is interesting about KMNO4 and the way that it oxidizes on the same side of the molecule. Meaning, if you note here, both of these OH groups, which are a product of the reaction because KMNO4 oxidized, remember, some people remember it as though oxygens are added as a result of oxidation. Therefore, but both of them are added on the same side of the molecule, meaning both of them are above the plane of the molecule indicated by these solid triangles. If you should consider how you would name this particular compound. This compound would be called, it would be a diol because there are 2 OH groups. It would be called cis because both the OH groups are on the same side. It's not trans where one OH group is on one side and the other is behind the molecule. So it would be 1,2-cis pentane diol. Over here we have KMNO4 under abrasive conditions, and this would be, of course, cyclohexene. And under abrasive conditions, KMNO4, instead of just oxidizing up to a diol, it actually breaks the ring. So the ring is broken, and we get COOH. And the same thing up here, COOH. So we see that the ring is broken. The carbons are not only oxidized with an OH group, they're oxidized with a carbon with a double bond oxygen. So that's 2 levels up. There's this level, there's a level with the OH, and then there's the level with the COOH, which is the second level up under abrasive conditions. COOH you should recognize as being the functional group for organic acids. And so this functional group for this particular organic acid, because there's 2 organic acids, just like this is called a diol because there's 2 alcohol groups, there are 2 acid groups, so this is called a diacid. This particular compound happens to be called adipic acid, but that you would not have to memorize. Here is another important oxidation reaction for the MCAT exam. Here we have O3. O3 is ozone, and therefore this type of oxidation reaction is called ozonolysis. Once again, the mechanism does not need to be memorized, but what you need to know are the expected products, because this is a common MCAT question. So here we have a particular compound, and if we had to name it, we'd say 1, 2, 3, 4 carbons in the longest chain, and it would be 2-butene, and there's a methyl group at the second carbon, so we would call this 2-methyl-2-butene, and this is plus ozone. And in the reaction mechanism, there's also a reducing agent which is used. When ozone is applied to a double bond, ozone breaks the bond and applies oxygens on each side of the bond. In other words, this becomes CH3 carbon double bonded to oxygen to hydrogen. Then we have oxygen double bonded to carbon, CH3, CH3. In other words, just take a look at this chemical as it stands. This is broken, and then an oxygen is inserted for both carbons, and these are separate chemicals. So you see that this is the same carbon, CH3, CH3, hydrogen, hydrogen. There's an oxygen now at the double bond. Oxygen at the double bond here to the carbon CH3, CH3. That's all you need to memorize, is that in ozonolysis, it is as if it breaks the double bond, places oxygens on either side for both of the chemicals. The way that they like to play with this on the MCAT exam is that they would show you the original chemical, say it's an ozone reaction, and ask you what the possible products are, but they will not necessarily line up the product exactly like this so that you can just look at the original product and see that it just follows perfect geometry. No, what they would do is they would take one of these chemicals at least and just turn it around. It is the identical chemical, but they just take one and turn it around so that you have to use at least your imagination for 2 steps. One step, which is to insert the oxygens and separate, and then you have to look for a product that looks like what you created, but sometimes that means that you have to turn or twist or whatever, and in order to find the actual product. We will now look at more reduction oxidation reactions. Here is a very important redox series. First of all, up here we have an organic chemical. This is clearly an alcohol with the OH group. This group clearly is an aldehyde because it has carbon double bonds to oxygen, and this is to a hydrogen. And this is clearly an acid because we have a carbon to an OH group and carbon double bonded to the oxygen. So this is a series of redox. And thinking about one of the ways that you could memorize oxidation and reduction in terms of organic chemistry, that oxidation is like adding oxygens or losing hydrogens. For example, so we have this carbon has 2 hydrogens attached to it, and there is a single bond to the oxygen. So we go up here, and this carbon has 1 hydrogen attached, so it lost a hydrogen. So it's being oxidized because it loses hydrogens, and it gains an oxygen because here it only had a single bond to the oxygen. Now it has a double bond to the oxygen. So this is further oxidized as compared to this compound. Here we have 1 hydrogen attached to the carbon. Here we have no hydrogens attached to the carbon, so we lost a hydrogen again, further oxidized. Here we have one oxygen attached to the carbon. Here we have 2 oxygens attached to the carbon, further oxidized once again. Then going in reverse, we see that going from here to here, it's as if you added hydrogen to this, you made water, it fell off, then you added a second hydrogen to attach to the carbon, you made the aldehyde. Let's say we continue to add hydrogens. We add another hydrogen, it goes to this, we form an OH group, then we add another hydrogen to this carbon, so it's CH2, then we get back to this compound. So some students like to memorize it as adding hydrogens is going to be reduction, adding oxygens or losing hydrogens, that is oxidation. Now, in terms of the compounds that will permit us to do this, if you wanted to just do a mild oxidation, so you're going in this direction and it's a mild oxidation, then you would use CrO3, which is a compound which I've already mentioned. So this is a mild oxidation, or you can use KMnO4 under very mild conditions just to do mild oxidation. But if you wanted to do a great big oxidation and you wanted to go straight from the alcohol to the acid, well then you would use KMnO4 but under abrasive conditions. That will allow you to go straight on up to the acid. Now if you wanted to do the reverse, you wanted to add hydrogens or reduce these compounds, well, if you wanted to do a mild reduction, you would use a mild reducing agent like NaBH4. NaBH4 is sodium borohydride. Now you may remember from general chemistry that a hydride is an unusual substance because it's the exception to the rule of all hydrogens have an oxidation number of +1. In a hydride, the oxidation number for hydrogen is -1, and that's exceptional. So you can imagine that just in theory, if you had a -1 hydrogen, a hydrogen that had a -1 charge, that would be extremely attracted to the delta positive carbon, and therefore that negative hydrogen would be attracted to the carbon and it would hit this carbon, and theoretically another hydrogen can fall off as water, and then you would have a hydrogen attached to the carbon producing the aldehyde. So a mild reducing agent is sodium borohydride. Don't forget that you don't need to know the mechanism of the reaction for these reducing agents or the oxidation agents. I'm just suggesting some ideas to you that may make it more easy for you to memorize. Now, however, if you wanted to do a great reduction, you wanted to go from the acid all the way up to the alcohol, the opposite of KMnO4, then you need a strong reducing agent, and that agent is lithium aluminum hydride. Lithium, LiAlH4, lithium aluminum hydride, a strong reducing agent, KMnO4, a strong oxidation agent, and sodium borohydride and CrO3, these are milder agents, and KMnO4 can sometimes be used under mild conditions, as we have already seen. Aromatic rings are so stable. You're supposed to ask, how stable are they? Well, aromatic rings are so stable that under abrasive conditions with KMnO4, KMnO4 cannot break the ring. It cannot break the ring, like we saw for the previous example of a cyclical alkene in which KMnO4 broke the ring and created a diacid. Well, with an aromatic ring, KMnO4 cannot break the ring. And so all it can do, even under abrasive conditions, is it can oxidize whatever substituent the compound happens to have. Aromatic rings are so stable that even under radical conditions, and certainly you should immediately recognize this as being radical conditions, and free radicals are very unstable, very reactive substances. Even under radical conditions, the free radical cannot add to the ring. The free radical can, of course, react with whatever substituent is on the ring, but it doesn't add to the ring. So these aromatic compounds, like the benzene ring, are very, very stable. And of course, you need to know what is the reason for their stability. And the reason for their stability is resonance energy. If we were to write the aromatic compound benzene and we were to draw in the double bonds, you would see that there are two equal structures that can be written for the benzene ring. There is no reason why the benzene ring should be one of these structures any more than the other. So these are two equal structures that we can write for this compound. And as we've already seen in general chemistry and also in organic chemistry, that the reality in resonance structures is not that it is resonating between these two possible molecules, but the reality is that there is some sort of molecule in between where the electrons are actually delocalized in the molecule. There is no true double bond. There is no true single bond. The electrons are delocalized in the molecule. By having electrons delocalized in a molecule, it increases the stability of the molecule. And therefore, by having two different resonance structures that we can write for the molecule, it means there's an enhanced stability. And that is why, even under very reactive conditions, the benzene ring is not broken. An aromatic ring is not broken under these particular conditions. So obviously, like an alkene, like the double bond in an alkene, which is the electron-dense center for the alkene, the reactive part of the alkene. If we were to look at the benzene ring, we see that there are electrons. They are delocalized, but there are electrons. So if you had to imagine what type of substance would finally add to this ring, what could we potentially add to an aromatic ring, you would have to have a compound which was extremely desirous to have electrons, and therefore would be so attracted to those electrons that it could finally enter the ring and make a bond. And so something that really wanted electrons, of course, would be defined as an electrophile, something that is electron-loving. That is an electrophile. So we would have to generate a powerful, not a normal electrophile, but a powerful electrophile in order to successfully add to an aromatic ring. An example of a powerful electrophile would be the following. Br2, if it were to be added to iron, an iron-based compound like FeBr3, this particular type of compound is equivalent to having Br plus. Now, we've already seen that halides are very electronegative. They're in the 7th group in the periodic table. They're towards the right. They're among the most electronegative compounds on the periodic table. And therefore, the idea of generating a bromine with a positive charge is incredible, because it's something it's a compound that likes electrons so much. We always see bromine as being negatively charged, Br minus, or it's neutral in a compound, but it's partially negatively charged because it's electronegative and it's drawing electrons to itself. So the idea that you can create a compound that would generate a species that is similar to Br positive, that is a tremendous achievement in itself. But the fact that you have this Br positive means that it would be highly desirous of electrons. It would really, really, really want to have electrons. So this would be a super powerful electrophile. So there are certain ways in order to be able to create powerful electrophiles that would indeed add to the ring, and therefore you would have a compound like this added to the ring as a result of creating a powerful electrophile. Now, once we've used powerful electrophiles to add to the ring, some of the interesting parts of the benzene ring or other aromatic rings is what happens afterwards. In other words, once you've added something to a ring, in what way does it affect the activity of the ring? That's what we're going to look at next. We will now look at how substituents affect the reactivity of the ring. Before we start looking at that, I would like to make a note about nomenclature. Normally, when you add a substituent to the ring, the substituent will be at position number 1. So you would name this carbon 1, this one would be 2, 3, 4, 5, 6. And that's how you would number them. However, it's not necessary to do that. There are formal words that can be applied to the various positions. For example, if you have a substituent attached to this carbon, the position which is opposite to the carbon is called the para position. So this is position number 1, 2, 3, 4, which is actually called the para position. The positions on the side, here and here, which are positions number 2 and number 6, those positions are called the ortho position. So those are on the side, those are the ortho positions. And then between the ortho and the para positions are the meta positions here and here. Okay, so let's say that we have an electron donating group which is attached. Now we will look at examples of electron donating groups in a few moments. But first, let's just take for granted that we have a group here that can donate electrons to the ring. So if it can, in theory, donate electrons to the ring, let's look at the potential resonance structures that would occur as a result. So if it were to donate electrons to the ring, bang, it gives electrons to the ring, creates a double bond here, but wait, this already had a double bond at this carbon, so there would be 5 bonds. So clearly, if this creates a double bond here, this bond has to break. So it breaks and it comes out here as electrons. So because this donated electrons to the ring, and because it donated electrons, its charge would therefore be positively charged. It breaks this bond, the electrons pop out here. Now let's say that the electrons want to join into the ring again. And so these electrons start to come back in here to form a double bond in this position. Well, if it were to create a double bond here, this double bond would have to break and these electrons would have to come out, and they would come out in this position. And so on and so forth. So if these electrons were to come back here to try to join the ring here, this bond would have to break and then come out in this position. In other words, if you were to add an electron donating group to the ring, you would have a situation in which here is our electron donating group up here, and then here is our ring. What would happen is that we would have our bonds here, and what we would get is we would have these positions as being partially negative, partially negative, partially negative. Therefore, because they're partially negative, because these are resonance structures that we can write, various resonance structures that we can write as these negative charges are moving in the ring, and therefore they're really delocalized over the ring, and on average the electron negative donating group ends up being delta positive, and then on average these particular positions end up being delta negative. And so what we say is that these positions are the ortho and para positions. Now imagine that you're a strong electrophile. Okay, so this is our electrophile, like Br positive or something like that. You're a strong electrophile and you had to add to the ring. And you had a choice of adding anywhere you wanted to. Where would you preferentially add to the ring? Clearly, you would preferentially add at the positions which have partial negative charges, which would be the ortho-para positions. In other words, when an electron donating group is added to the benzene ring, we say that it activates the ring. It makes the ring more reactive than it was before, and it directs the electrophiles to the ortho and para positions. However, all these things are statistical, and that's important to keep in mind because on the MCAT exam they can play with you on this. Obviously, the position which would be preferable to be added would be the para position because these compounds, substituents, they have electrons around them, and you can use either the idea of a steric hindrance, or you can use the idea of electron repulsion, electron shell repulsion, and wanting to stay as far away from the other substituent as possible, and therefore the para position would be the most desirable position to add. Then there would be the ortho position, and one might expect that perhaps 70% would add to this position, and perhaps 29% would add to the ortho positions. But indeed, some 1% may add to the meta positions. So a small percentage would add to the meta positions, but it would still occur. So that's important to remember, that even when it activates the ring, even though it's an ortho-para director, when you have an electron donating group, even though these things are all true, organic chemistry is statistical, and therefore if there is a reaction which is logical to occur, even though it's improbable, even though it doesn't happen often, if it's logical to occur, then it would occur. And sometimes on the MCAT exam, they will play on this and say, what are the possible products? And then people will think, oh, ortho-para director, so the possible products must be the ortho and para. And one of the answers is also meta. Well, then that is one of the possible answers, because ortho, para, and meta would be possible, though statistically the great majority would be ortho and para. Clearly, this ring is more reactive than just the benzene ring. If you had a benzene ring without the electron donating group, then you wouldn't have these delta negative positions. You would just have the benzene ring and it would be neutral, and you'd have your delocalized electrons. And therefore, the electrophile could add anywhere in any position. There's no reason for it to add in one position any more than another, because there's nothing attached to the ring yet. But if there is something attached to the ring, if it happens to be an electron donating group, then it not only directs to the ortho and para positions, but it activates the ring. It makes the ring more reactive than it would have been had there been nothing attached to the ring. We will now look at what happens with an electron withdrawing group attached to the ring. Here we have the benzene ring, but now there is an electron withdrawing group attached. Let's see what happens. So this electron withdrawing group clearly withdraws electrons to itself. It's pulling electrons to itself. So we can draw a series of resonance structures that will illustrate that point. So if it pulls electrons to itself, it can pull the electrons from this double bond to itself, creating a double bond here. Therefore, its charge will be negatively charged because it pulled electrons to itself. And because this bond went away, the carbon that used to have electrons here has now lost those electrons, so its charge will be a formal positive charge. Because there's a positive charge here, and there are electrons here, then we can imagine that these electrons would be attracted to this positive charge, bond here, creating the double bond in this position, therefore releasing electrons from this position, and then this position becomes positive. Once again, the electrons here would be attracted to this positive charge here at this carbon. These electrons would come down here, bond here, therefore taking away this positive charge. But because it withdrew electrons from up here, this position would become positive. In summary, if we look at our benzene ring, clearly every time I draw a benzene ring, it's going to look a little bit different. But anyway, when we draw a benzene ring with our electron withdrawing group at the top, what indeed happens is that overall, because these electrons are really delocalized, it's not as if there's ever really a positive charge here or a positive charge there. These are just different ways we can illustrate what's happening, because these are resonance structures, and therefore it's really delocalization of electrons. Well, this electron withdrawing group will be delta negative, and this position, the ortho position, would be delta positive. This would be delta positive, and then the para position would also be delta positive. This represents what we looked at here on the left. Now imagine, once again, we have our electrophile, our powerful electrophile that wants electrons. Where would it preferentially add? Would it like to add at the ortho positions? Certainly not, because we know like charges repel. So it would preferentially add to the meta positions, which is the best of a poor bunch of options. You see, when we had the electron donating group, we actually had the option of delta negative positions. And delta negative positions are very attractive for something that's highly positively charged. But here, we don't have any delta negative positions. So we have positions here which are not any better than just a regular benzene ring that didn't have anything attached to it. So the electrophile can certainly add at these meta positions. But look at these positions, these ortho-para positions, how extremely unattractive for something that's positively charged. Obviously, these positions are less attractive than if it was a benzene ring with nothing attached to it. So by having the electron withdrawing group, by pulling electrons away from the ring, it deactivates the ring. It makes the ring less reactive than it would have been had it just been a plain old benzene ring with nothing attached. And so electron withdrawing groups deactivate the ring, electron donating groups activate the ring. And electron donating groups are ortho-para directors, and electron withdrawing groups are meta directors. And once again, it is statistical. The likelihood is the strongest that the electrophile will add at the meta positions, but it does not mean that 100% will add at the meta positions with no addition at the ortho-para positions. Certainly there will be additions at the other positions, but the great majority would be at the meta positions. Now that we've looked at what would happen if we added an electron donating group or an electron withdrawing group to the ring, let us look at examples of electron donating groups and electron withdrawing groups. Now we're going to look at these groups and see whether or not you would categorize them as electron donating groups or electron withdrawing groups. So first, imagine that this group was attached to a benzene ring, and consider what you would regard for these three different groups if they were attached to a benzene ring. You may want to pause now and consider how you would respond. Clearly, oxygen with a negative charge has an extra electron pair ready to donate into the ring. So this has an extra electron pair. It is clearly an electron donating group. Here we have electronegative element up here, and therefore this carbon, as we know, because it's a carbonyl group, this carbon is going to be delta positive. A delta positive carbon clearly cannot be engaged in electron donating, especially when it has an oxygen on the other side withdrawing electrons to itself. So therefore this delta positive carbon is going to do what to electrons? It's going to attract electrons because it's delta positive. So this delta positive carbon would be considered to be an electron withdrawing group, particularly because of the presence of the oxygen up here. And then here we have a delta negative group, and once again, because this is delta negative, it has extra electron pairs, as we know oxygen has, and it can donate that extra electron pair into the ring and in order to serve as an electron donating group. In fact, when you have an OH group attached to the benzene ring, its name is then changed to a phenol. That's PHENOL. That's a phenol when the OH group is attached to the benzene ring. And we discussed earlier that one of the considerations you must have in terms of thinking about whether or not something would be a good acid or not is to also look at what the product would be. And if a phenol gives up its hydrogen and has an O- group, well, we just mentioned that could be electron donating as well. And therefore, this can donate electrons into the ring with all the resonance structures that we looked at already. And that means by having these resonance structures, it increases stability. Therefore, phenols are much more acidic than one would consider when comparing it to their relative alcohols, because phenols have a ring where it can contribute those lone pair of electrons and create this resonance structure. And that is the reason for the increased acidity of phenol. And of course, that would be a expected MCAT question that would come up from time to time. So now we've looked at many different mechanisms of reactions. We've looked at other types of organic chemistry reactions. And it's all been quite fun, but is it all true? How do we know for sure that the chemicals actually look like what we think they look like, or at least remotely appear to be the way we draw them out to be? And are these mechanisms actually occurring the way we think they are occurring? Well, that is the purpose of spectroscopy. Spectroscopy includes many different techniques in order to more clearly demonstrate what the organic chemical actually looks like. For example, there is a technique called X-ray crystallography. In the technique X-ray crystallography, a sample of whatever organic chemical is purified, then it is crystallized. In its crystalline form, the chemical has a regular array, and therefore you can take X-rays and send the X-rays through it. And of course, we know from physics, X-rays is a form of electromagnetic radiation. And if you send the X-rays through this crystal, then the X-rays will interfere with each other. And again, from physics, you may remember the issue of diffraction and diffraction patterns, as in the Young slit experiment. So these X-rays will interfere with each other and create diffraction patterns. These diffraction patterns are then analyzed. And because of the interference, because you can analyze the data, you would be able to determine what the shape of the chemical must have been in order to create certain patterns. And of course, the most famous organic chemical of all time was discovered in this way, and that is DNA. There was a woman from England who worked out, who created all the data through the experiments of X-ray crystallography, and then of course Watson and Crick interpreted the data and was able to determine the shape of DNA. Now, in order to do X-ray crystallography, you need a considerable amount of pure substance. Then a technique developed called infrared spectroscopy. And in infrared spectroscopy, the amount of substance that you require is much less. And here, once again, you take the sample, you send infrared rays through the sample, and then some of these rays will be absorbed by the sample. That would be the absorbance. And some of the rays would go straight through the sample. That would be the transmittance. So you can look at the transmittance, and then you would be able to determine what areas or parts of the infrared spectrum was absorbed by the particular substance. And that provides information regarding functional groups. And that is very important to memorize. And that is that infrared spectroscopy provides information regarding functional groups. And the units in which infrared spectroscopy is calculated, it's called the wave number, and the units is in centimeters to the -1. Now, if you look in the gold standard, it's chapter 14, you will find a list of many different functional groups and exactly what infrared spectroscopy units are associated with those functional groups. And you are responsible, according to the MCAT, to know those different values. Now, just from experience, I can say that there's at least 2 values that you must memorize. And that is the number 1700. And 1700 would be the absorbance for the carbonyl group. So we know, of course, the carbonyl group being C double bond oxygen. The other number to memorize is 3300, and that is the absorbance for the OH group. Now we know in organic chemistry, the most common functional groups that we see in chemicals is the carbonyl group and hydroxide. So these definitely are numbers to memorize. The other ones, if you have brain space, if you have the time to memorize these extra functional groups, then you should do so. But these would be the most commonly found on the MCAT exam, and so definitely these ones should be memorized. It should also be kept in mind that these values are approximations. In other words, when there is a carbonyl group, the value might be anywhere from 1600 to 1800, with 1700 being an approximation. And same thing with the OH group, hydroxyl group, it might be 3200 to 3400, in and around those values, with 3300 being an approximation. In other words, these are good values, good approximations to memorize for the MCAT exam. Next, of course, will be nuclear magnetic resonance. Nuclear magnetic resonance is a form of spectroscopy, and what it does is allows us to know the number and types of hydrogens in a substance. I say specifically hydrogens because the NMR for the MCAT exam is proton NMR. In other words, it's an NMR that is only focusing on the numbers and types of hydrogens found in a compound. So we will look at an example of an NMR and we will work out the details. We will now look at the nuclear magnetic resonance for ethanol. So here is ethanol, it's an alcohol, and this is the nuclear magnetic resonance. So this is the graph that we would get after ethanol was analyzed. So we have this graph. We have at 0 a particular peak at 0. Well, that's just the peak for a substance called TMS. And that sort of is the 0 for the graph. So when you see this peak at 0, you just ignore it because it's really the other peaks that need to be analyzed in order to determine or provide us information at least regarding the substance that we are analyzing. So the first thing that we do when we look at an NMR is to look at the number of groups of lines. The other way of saying it is the number of groups of peaks. So that ignoring this peak here, there's a group of peaks here in the graph. There's a group of peaks here, which is actually 1, and then there's a group over here. So there's 1, 2, 3. The number of groups of peaks is equal to the number of environments that hydrogen will be found in. For example, there are 3 groups of peaks here, and then when we look at the chemical, there's 3 places where hydrogen can live. It's either hydrogen is attached to oxygen, that's one place hydrogen can live. Hydrogen can be attached to the carbon in the middle. There happens to be 2 hydrogens attached to the carbon in the middle, but both of those hydrogen share the same environment, meaning that if you're a hydrogen on this carbon, you've got an oxygen to the left and you've got a carbon to the right. So it doesn't matter if you're hydrogen number 1 or hydrogen number 2, you're experiencing the same environment. So those are 2 different environments for hydrogen, and then there's the third environment. You're a hydrogen that lives at the end of the molecule attached to a carbon. And so there are 3 hydrogens in that environment, but that's only one environment. So the 3 groups of lines indicate that there is 3 separate environments for hydrogen to live in. So that's the first thing we do. How many groups of lines? So we've established that. Now what we can do is we look at the number of peaks in each set. And the number of peaks in this part of the curve will be equal to the number of hydrogens in adjacent atoms plus 1. So the number of peaks, you can write down that peaks will be equal to n plus 1, where n is the number of hydrogens in adjacent atoms. For example, over here, there are 4 peaks, 1, 2, 3, 4. So that means that 4 is going to be equal to n plus 1. Therefore, n is going to be equal to 3. So here n will equal to 3. And that means the number of hydrogens in the adjacent atom to this particular set of hydrogens, the number of hydrogens in the adjacent atom will be 3. Here, the number in the adjacent atom will be 0, because 1 will equal to n plus 1. Here, the number will be 2. The next thing we want to know is the area under the curve. When we look at the area under the curve, there are many ways that this could be calculated. In a worst case scenario, which they would very unlikely have on the MCAT exam, is that this would be placed on graph paper with very fine boxes, and you would have to count the number of boxes underneath the curve. That would be extremely unlikely for them to do that on the MCAT exam, because it would be obviously too mean to do that. Anyway, the more likely things that they can do is that they can put these regression numbers here, and these numbers, what they will do is they indicate to us already the relative area under the curve. That means that the relative area underneath this curve compared to this, compared to that, is that this is 1 to 2 to 3. There's another way that they can do it, and that's to draw a regression curve above the curve. So to draw another curve. And what they would do is that the curve, the other curve, would have steps on it. And this would end up going up way up here. But just to give you the idea, there would be steps on the curve above. This would be called a regression curve. And the reason why these steps are placed is that the height on each step would provide us with the relative areas under each curve. So instead of counting boxes, if they did not provide you with these numbers, then they would provide you with these steps, and then you would know that whatever height this step is, that we can regard that as 1 unit. And this step can fit into this step twice. So then it would be 1 to 2. And then this step can fit into this other step 3 times. So then it would be 1 to 3. And then we would be able to write 2 to 1 to 3 exactly as though they originally wrote those numbers. So it's either the height of the regression curve, which is like a series of steps above the main curve, or there will be numbers that will actually be placed there. Now, the relative areas under the curve is very important because it provides us with the relative number of hydrogens in the compound. So the fact that we have 2 to 1 to 3 means that in our compound there is relatively 2 to 1 to 3 hydrogens. And indeed, when we look at the compound ethanol, we see that there's 2 hydrogens here, 1 in this environment and 3 in this environment. We know that there's 3 environments because there's 3 sets of lines. We know that there must be 1 to 2 to 3 hydrogens in these 3 environments because of the relative areas underneath the curves, 1 to 2 to 3. And finally, we can say exactly how many hydrogens there are in the nearest neighbor based on the n value. So we know that wherever there is relatively 2 hydrogens, which clearly is here, its nearest neighbors have a total of 3 hydrogens attached. So you see this carbon here, it has relatively 2 hydrogens. Its nearest neighbor has 3 hydrogens. The place where there is relatively 3 hydrogens would be here. Where there's relatively 3 hydrogens, its nearest neighbor must have n equal to 2 hydrogens. So there's relatively 3 hydrogens, and indeed, its nearest neighbor here has exactly 2 hydrogens. The only thing to remember is that when you have an electronegative group like oxygen or sulfur in the substance, what it does is it serves as a barrier. In other words, it does not permit this hydrogen to know that it has neighbors on the other side, nor does it permit the hydrogens on this side to know that it has neighbors on the other side. You can imagine it as being a barrier. Therefore, the place in the molecule where there is relatively 1 hydrogen, which has to be this hydrogen here, its nearest neighbor has, well, no hydrogens. Because as far as this hydrogen is concerned, it has no nearest neighbor with hydrogens. So this seems very clear. Let's look at a completely different example like propane. So propane, we know that to be CH3, CH2, CH3. It's a alkane hydrocarbon with all single bonds and starts with prop, so there are 3 carbons. So this is propane. So the first thing you'd say is how many environments are there in the molecule? Well, it's either you're a hydrogen in the middle of the molecule or you're hydrogen at the end of the molecule. After all, if you're a hydrogen over here, you experience the same environment as a hydrogen here. Meaning a hydrogen here, it's next to a CH2 group and there's no electronegative element near it. And here it's the same thing. So we would expect that in our NMR, we would have 2 groups of lines. Okay, so then what would be the relative areas underneath these peaks? Well, the relative areas underneath the peaks would give us the relative number of hydrogens. So it's either you're a hydrogen in this environment or you're at the end. So there's 2 hydrogens in this environment. There's 6 hydrogens at the end. So the relative area would be 2 to 6 or 1 to 3. So we know that the relative area underneath the curves, when we write it, there's going to be a 1 and there's going to be a 3 that we can write, or there will be a regression curve above the curve and the relative heights of the steps will be 1 to 3. Then we want to know, well, how many peaks are there underneath the curve? So if you're in this environment, meaning you're at the end of the molecule, your nearest neighbor would have 2 hydrogens. Therefore, there would be 3 peaks. So we have our 3 peaks where there is relatively 3 hydrogens, meaning at the ends of the molecule. Then let us look at the CH2, where we have relatively 1 hydrogen, which means 2 hydrogens. And where we have relatively 1 hydrogen, its nearest neighbor has, there's 3 on the right, there's 3 more hydrogens on the left, so it has 6 hydrogens as nearest neighbors. Therefore, n is going to be 6. Therefore, the number of peaks in this curve would be 7. So there would be 1, 2, 3, 4, 5, 6, 7 peaks on this curve. Obviously, this is, and then at 0, there will be our TMS as our 0. Obviously, this is not drawn to scale, but at least this provides you the idea behind it. How many peaks under the curve, what is the relative areas underneath the curve, and this allows you to, in order to work out simple NMRs, because for the MCAT exam, the NMR is always going to be simple, and if it's more complicated than you were expecting it to be, then it's likely that you can solve the problem by other means, and they're just trying to trick you a little bit. Now, we've already done a review of substitution and elimination reactions. So we're going to do an extra bonus review of these 2 types of reactions only because they're so popular on the MCAT exam. Also, we're going to look at this particular chemical, which is 2-bromobutane, because it is so popular on the MCAT exam. It is a chemical that comes up very often on the test, either this particular chemical or some sort of derivation of it, which is very close to it. The reason why it's so popular is because we can get all the different elimination and substitution reactions occurring with this very chemical. For example, let's say that 2-bromobutane was in solution. One of the things that could happen is that 2-bromobutane can dissolve. It can dissociate. And it could dissociate into the 2-butyl component, meaning the Br falls off, so we have Br negative, and then we would have a positive charge at this particular carbon. That would be called 2-butyl. And so if there was a 2-butyl, then what could happen is that because this is positively charged, it can draw electrons either from the left or from the right. But we saw that if it had the choice to draw electrons from the left or from the right, kicking out a proton, that it would preferably choose from the left in order to have a di-substituted product. So that is one mechanism of reaction which would produce carbon, carbon, double bond, carbon, carbon. Therefore, the bromine would have been eliminated. The hydrogen that was here would have been eliminated. So that would be called an elimination reaction. The rate of the reaction only depended on this substance. So that would be an E1 reaction. So that is an E1 reaction. This would be the major product, the di-substituted product, and the minor product would be the monosubstituted product, also called 1-butene. So this one is called 2-butene, which is the major product. That's the E1 product. Now let's imagine that this was again in solution, but the solution contained a base like KOH or NaOH. So there's some OH minus that's floating around. Well, let's say again that this in solution dissociated. So again, Br minus falls off. We've got a positive charge here. It's 2-butyl. Then, if there's OH minus that's floating around, the OH minus will come in here in a nucleophilic reaction because it's OH minus, it's negatively charged. This is positively charged, so there'd be a great force of attraction, and so the OH minus would come in here and bond to this. So there's another possibility, which would be carbon, 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 then an OH group, or whatever nucleophile happened to be in solution, and then bonded to carbon. So this would be 2-butanol. This product would have occurred by nucleophilic substitution because you started with a bromine group, you ended up with an OH group, so there's been a substitution at the carbon nucleus from Br to OH. So it's nucleophilic substitution. The rate of the reaction would have depended upon the step in which this dissociated. Therefore, the longest step was this dissociating into the 2-butyl group and the bromide anion. So when it dissociated, that took a long time. But if OH minus is in solution and there's a positive charge there, then the reaction would occur very, very quickly. So the rate determining step, the slowest step was the dissociation here. And because that was the slowest step, the rate of the reaction depends upon the first step. Therefore, this is nucleophilic substitution, first order. So this would be SN1. So here are two different types of reactions that can occur with the same compound. Now let's continue. Let's imagine again that there was NaOH in solution. If there was NaOH in solution, well, we can imagine something else occurring as well. Na plus, OH minus seeing this, well, this is delta positive carbon because it's attached to bromine, which is more electronegative, which is towards the right on the periodic table. So this is delta positive. OH minus would be attracted to this. OH minus would come in here, hit this carbon, and knock out the bromine. And therefore, one of the possible products of this reaction would be carbon, 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 then OH group, which would have to come in from behind, backside displacement, meaning that all the molecules will end up being inverted, OH, carbon. So we again have 2-butanol, or a secondary alcohol, as our product. The reaction would have depended on two compounds, the nucleophile coming in and hitting the original compound, and knocking out the bromine. So there's two compounds that are dependent on this reaction. Therefore, this particular rate of reaction mechanism would be called SN2. It's nucleophilic substitution because bromine has been substituted here and OH has replaced it. It's second order because it depended on this and the concentration of KOH or NaOH or whatever nucleophile that was used. Again, let us imagine that we have this compound and we have a strong base. We could have a base like NaOH or KOH, but it would be more clear if we had a big, bulky base, sort of like what we saw before, potassium tert butoxide, which is a big, bulky base, which would preferably take primary hydrogens away from this compound. And so if we had a big, bulky base or a base that was strong enough that could withdraw hydrogens from these positions, either from this carbon or from this carbon, then what would happen is that you would pull off a hydrogen with your strong base, because the strong base wants hydrogens. So you'd pull off your hydrogen, you'd end up with a negative charge here. This is delta positive, so the negative charge would come in here, form a double bond, and knock out the bromine. So here we would have, as a product, carbon, 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 double bond to carbon. And that would be our final product. So we would have the elimination of the bromine, elimination of a hydrogen here, so therefore it would be called an elimination reaction. It's second order because it would depend on the original base that was present, the concentration of that, and it would depend on the concentration of this original compound. So this reaction mechanism would be called E2. So here, using the same initial compound, we can get SN1, SN2, E1, or E2 reactions. And you don't have to worry about, oh my goodness, which one will it do? Will it do this more? You don't have to worry about that. The importance is that you understand the mechanisms of these different reactions, because they're going to guide you into one or the other of the reactions, either by saying certain key words, like, for example, we know that there's going to be an inverted reaction. If you know there's an inverted reaction, it must have gone through the SN2 mechanism. If you know an alkene was created, you know it must be elimination 1 or 2. And then if you know that, that in the reaction mechanism, a racemic mixture was produced, or a racemate, then you know that it must have occurred via the SN1 mechanism, because as we've seen previously, in the SN1 mechanism, when this dissociates and you have the 2-butyl, the OH group can add to either side. It doesn't matter which side it will end up adding. And as far as it's concerned, it could do so equally. And if it were to do so equally, then it would produce a racemate or a racemic mixture, which we see in SN1 mechanisms. So generally speaking, they will guide you in one way or the other. Of course, if you had NaOH with this reaction, the first thing that you're going to think of is going to be an SN2 reaction. You'll think of OH minus coming in here, hitting the carbon and knocking it out. But all these other mechanisms are also valid reactions, even if NaOH is in the reaction mechanism. And so what happens is there's a certain probability of each occurring. But the important thing is for you to understand, at least, that these different mechanisms are possible, and to keep your mind open during the problem, and to watch and see which direction are they pushing me into, and then you would be able to solve the organic chemistry mechanism. Welcome. I'm Dr. Ferdinand. Physics has to be one of the most fascinating sciences, and the reason is because it explains so much about our universe. The physics for the MCAT exam is at the introductory college or university level, and so the equations and the concepts are quite basic, but it is very important to understand the information. It will allow you to ace this part of the exam, because it is a part of the exam that many students do not prepare adequately for. All the equations that we discuss will need to be memorized. That is very important, and that is a basic part of your learning. Now, the plan is that we're going to start by talking about the atom, because it is the most basic structure of our universe. And then we're going to talk about aspects of the atom, which are electrons, and their motion, which is electricity. Then we'll go on to talk about waves and light, problem solving. First, the atom. Now, it's important to say that we're going to discuss more details about the atom in general chemistry when it comes to electronic structure and the shape of atoms and molecules. But for the moment, it would suffice to say that the basic atom is a structure containing a nucleus, and the nucleus has neutrons and protons. Neutrons being, of course, neutral particles, and protons being positive particles. Around the atom is a cloud of electrons. Electrons having a much smaller mass than either neutrons or protons, and having the opposite charge of a proton, an electron being negatively charged. Now, you would have to imagine that if you have an atom with its positively charged nucleus, negatively charged electron cloud, and opposites attract. And therefore there is a lot of energy, a lot of force involved with this atom. We call that an electronic force. Within the atom, there are a number of protons, and these protons are being held together. And imagine if opposites attract and like charges repel, then these protons, which are within the nucleus, repelling each other, must be kept together by a very powerful force, which is the nuclear force. Of all the forces of nature, nuclear forces are among the strongest. In fact, gravity is one of the weakest forces in nature. You may think it's strong because it's keeping you sitting in your seat right now, but it takes something as large as the Earth with all its weight in order to keep you in your position. So gravity is considered to be a very weak force. Electronic forces are much stronger, and nuclear forces are much stronger still. So in atomic physics, which is the first thing that we will review for the MCAT exam, keep in mind that the aim is to harness the energy or force of the nucleus, which is extremely powerful. And once that energy is released, that energy could be used to do other things. Now, there are three important particles to consider that are released from a nuclear reaction: alpha particles, beta particles, and gamma rays. An alpha particle is a helium nucleus. So right off the bat, you can consider that as being positive and having considerable mass compared to the other particles which I will describe. The second particle, a beta particle, which is really more precisely called a beta negative particle, but nonetheless, if it's on the MCAT and they say beta particle, it is an electron. An electron has a much smaller mass, of course, than a helium nucleus, and it has a negative charge. And finally, gamma rays. Gamma rays are also released from nuclear reactions, and gamma rays have no mass whatsoever and no charge whatsoever, since they are a form of electromagnetic radiation, or light. You are now looking at the alpha decay of uranium-238. First off, you see here uranium-238. We have the superscript 238. The superscript represents the atomic mass number. The atomic mass number is the whole number closest to the atomic mass. Then we have the subscript 92. The subscript is the Z value. The Z value defines the element. It is equal to the number of protons. and the number of protons is equal to the atomic number of the element. There are three essential things to remember about alpha decay. To begin with, in alpha decay, we have the release of an alpha particle. And an alpha particle is defined as the helium nucleus, which is helium-4 So once you see that helium-4 has been released in the reaction, you know that you have an alpha decay. So that's the first thing you must know. The second thing is that notice that everything adds up, meaning that we have 238 going to 234 plus 4. We have 92 going to 90 plus 2. So it's very straightforward. The third thing for you to recognize is the importance of the Z value. And that is that the number of protons defines an element. If you change the number of protons, then you've changed the element. If you've changed the number of neutrons, it's the same element. Change the number of electrons, it's the same element. It's the number of protons that defines the element. If you were to calculate the number of neutrons in this element, you would simply take the 238 minus the 92, and that would equal the number of neutrons. And that goes for any element. Incidentally, the name of this particular element is thorium, but that is not important for the MCAT exam. We are now about to look at beta decay. You are now looking at the beta decay of carbon-14. Now, if you try to understand the idea behind beta decay, it is thus, that a neutron is decaying into a proton plus an electron. First, let us look to see if this equation is balanced. First, let's examine whether it's electronically balanced. On the left-hand side of the equation, we have a neutral particle. It's a neutron. On the right-hand side of the equation, we have a proton, which is positively charged, and an electron, which is negatively charged. So, both the left and the right side of these equations is essentially neutral. What about mass? Well, a neutron is slightly heavier than a proton, and an electron has a negligible mass. In other words, the left side of this equation is heavier than the right side of the equation. So what happens to the mass when we go from left to right? It's converted to energy according to the most famous equation of all time, which is E equals mc squared, in which mass is converted into energy. This is the energy used in nuclear reactions. So let's look at carbon-14 and how, in fact, a neutron is going to disappear and become a proton and an electron. Well, if we look at the left-hand side of the equation, we have carbon-14, atomic number 6, which means it has 6 protons. If we wanted to calculate the number of neutrons for carbon-14, 14 minus 6, so we end up with 8 neutrons. On the right-hand side of the equation, we have nitrogen. Why? Because the number of protons changed from 6 to 7. Therefore, immediately you must change the element. So nitrogen, 14 minus 7, we have 7 neutrons. And then, of course, we have the electron. The electron which is being liberated is indeed called a beta particle. So this is beta decay. We have 8 neutrons on the left-hand side of the equation, 7 on the right. 1 neutron disappeared. Where'd it go? It went into producing a proton. We have 6 protons on the left-hand side, 7 protons on the right. And the electron, which is liberated as a beta particle. It's very interesting because this is the way that nuclear reactions work. And so, what you can do, you can imagine taking compounds which nuclei will decay, releasing energy, put these compounds underwater, and the energy released by these compounds will heat the water. The water will form steam, and the steam will rise. You create turbines that will take the steam, and the turbines start turning as the steam rises. The turbines are connected to generators, and those generators, of course, produce electricity. And so by harvesting the energy of the nucleus, we're able to create electricity. Here's a common MCAT question. Element A40 has a half-life of about 10 years. How much A40 is left from a pure sample after 30 years? First, we have to discuss what the definition of half-life is. So a half-life is the amount of time after which half of your sample has decayed. So if you have a half-life of 10 years, it means that after 10 years, you will have 50% of the material left from a pure sample. So 10 years has gone by, you have half, or 50%. Another 10 years go by, a total of 20 years, you have half of that, or 25%. Another 10 years go by for a total of 30 years, and you have half of the 25%, or 12.5%. The other way of calculating this is by using the equation 1/2 to the power of n, where n represents the number of half-lives. So here, with a half-life of 10 years, and we're talking about a period of 30 years, so there's been 3 half-lives, 3 times 10, 30, 3 half-lives, so we're talking about 1/2 to the power of 3, which is 2 to the power of 3, which gives us 8, or 1/8. So 1/8, which is equivalent to 12.5%. A couple of little things about the MCAT, however. They don't tend to use precise numbers because they want you to be relaxed enough with your understanding of the concepts that you will be able to estimate when necessary. For example, they may put, instead of 30 years, 29 years. So it's not a stretch to estimate the 29 years as 30 years, which is able to give us a more rounded result in terms of the number of half-lives. So do expect that sometimes you may have to estimate. Of course, the equation for half-lives is quite similar to the equation for doubling time. Quite commonly on the MCAT, they'll ask a question about bacterial replication in the biology section. And instead of talking about half-lives, they'll talk about doubling time, which is just 2 to the power of n, which n represents the number of times that the bacteria will double. Now, we have reviewed the 4 most important aspects of atomic physics for the MCAT exam. The most commonly asked questions are alpha decay, beta decay, gamma rays, and incidentally, in terms of gamma rays, all they want you to know is that it doesn't have mass and it has no charge. And fourthly, half-lives. Now that we've looked at atomic physics, we're going to go from the atom to the movement of its electrons, which is electricity. We are now moving on to electricity. However, because many of the equations that are important in electricity and which you must memorize are very similar to the equations for gravitation, we're going to look at the equations side by side for 2 reasons. One, it will be more easy for you to memorize the 2 sets of equations, and secondly, you'll be able to see parallels between the 2 sets of equations. So first, electricity. F is equal to QE, one of the most fundamental equations. That is, the force in an electric field is equal to Q, the point charge, times E, the electric field. The relevant equation in gravitation is F is equal to mg. That is to say that F, the force in a gravitation field, is equal to m, the mass in the field, times g, the acceleration due to gravity. So you can see the similarity of these equations. Now, the most fundamental equations in motion comes from Newton's second law. And Newton's second law is that force is equal to ma, which is force is equal to mass times acceleration. So let's look at a derivation of that law. That is to say that acceleration is equal to force over m. And from the first equation, we see that F is equal to QE. So therefore, acceleration is equal to QE over m. In other words, the acceleration in an electric field is equal to the force over mass, that's Newton's second law, which is equal to QE over m. So this provides you the acceleration in an electric field. The acceleration in a gravitation field, we do the same thing. A is equal to F over m, which is equal to mg over m. Well, the m's cancel, and we just end up with g. In other words, we get the trivial result. And that is that when we have the acceleration in a gravitational field, that is simply equal to the acceleration due to gravity. Continuing with our comparisons of gravitation versus electricity equations, we will look at a couple of laws which, again, you must memorize. The first is Coulomb's law. And in Coulomb's law, we have the force in an electric field is equal to K Q1 Q2 over R squared. K is Coulomb's constant. Q1, Q2 are the 2-point charges involved. R is the distance between the point charges. Be very careful. On the MCAT, they will provide you with extra information that you do not require to solve a problem. You can bet they're going to provide you with information such as the radius of something. But this has nothing to do with the radius of anything. This happens to be the distance between the 2-point charges. In gravitation, the relevant equation is Newton's law of gravity. And it is that the force in the gravitational field is given by G, which is the gravitational constant, M1, M2, the two masses involved, and R, which is the distance between the center of mass of the two masses. Again, it has nothing to do with the radius. So notice how these two equations are remarkably similar. Both of them include the constants. Now realize that from what we mentioned about earlier, about how the forces of nuclear forces, electrical forces, gravitational forces are so different, clearly the constant for electricity would be a much greater number than the constant for gravitation, which is a much weaker force. Also, in terms of the MCAT exam, you don't have to worry about memorizing the constants K or G. They would be provided in the exam itself. But the structure of the equation is very important. They would rarely ask you to actually calculate something based on this, but a very common type of question would be to say something of the order of, if you have an electric field and there is a force in the electric field, what happens to the force if you double one of the charges? Well, if you double one of the charges, you would double the force because it's a direct relationship. Other typical questions is, what would happen to the force if you doubled the distance between the point charges or between the masses? It would be the same thing. It's an inverse square relationship. If you double the distance, 2 times r, then the 2 is squared, it creates 4. So if you double the distance, then the force will be 1/4. If you triple the distance, the force would be 1/9, which is 3 squared. So those would be typical manipulations that they would ask for the MCAT exam. Now, let's talk about work. We're going to talk about work in much more detail later in this series. But just in general, you could remember work as being force times distance. That's a very loose description of work, but it's comfortable for what we need to deal with now. And we'll talk about it in more detail later. So work is force times distance. So let us look at what the work is done in an electric field. Well, let's look at an electric field. First, I will draw some electric field lines. Here are some electric field lines. The understanding is that electric field lines are always drawn away from a positive charge. That's the standard. So it's as if there was a positive charge higher up, and therefore this is being drawn away from the positive charge. Clearly, if you were to put a negative charge here, because the positive charge must be up there, if you put a negative charge here, then that negative charge would be attracted to the positive charge, because opposites attract, and it would move in that direction. But let's imagine that we put a positive charge here. So positive Q. Well, like charges would repel, and this positive charge would be pushed away. But we want to push this charge towards the positive charge. We want to move it in this direction. If we move it in this direction, that will require work. That would require a force to push it in the opposite direction of the electric field. If we were to push this charge a distance delta y, then we can calculate the work done. Work being force times distance, and the force we saw earlier in electric field is QE. So work is force times distance delta y. So the work in an electric field is given by QE delta y. To be more precise, the QE is the absolute value. In other words, it doesn't matter what the charge is on the Q, whether it's positive or negative, if you are pushing it against the field, whatever the field may be, and you are doing work, work is given by the force times the distance. Well, let's look at what the work would be in a gravitation field. So in a gravitation field, let's imagine that we have an object. Here's our object, and it's on this surface. And this object is brought a distance delta y. Just very, 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 very slowly, it's brought a distance delta y against the gravitation field. Because imagine, gravity is working this way. Gravity is going to be pushing things down towards the center of the Earth. So we are taking an object and we are bringing it up. That's against the field. It's equivalent to moving the positive charge against an electric field. So as we're moving this way, we have work is equal to force times distance. The force, we said earlier, equivalent to QE, is mg. Of course, we'll be seeing a little later what we usually, the word we usually use for this is simply the weight of the object. So we have mg, and it's moving a distance delta y. So there we have work is force times distance. So now we've compared the equations for electricity and gravitation. All these equations must be memorized. Most importantly, you should understand any derivations that we've done, and to imagine, as I've mentioned, the different ways that these equations can be used. Now we're going to look at electricity more specifically. Electricity flows in circuits. And so we will look at the elements of circuits. The fundamentals include capacitors, resistors, and batteries. First, let us examine capacitors. The symbol for capacitance is C, capital C. The units for capacitance is the farad. The equation which you must memorize is the following. Q is equal to CV. Q, the charge, is equal to C, the capacitance, times V, the voltage. More specifically, Q, the charge, is in units of coulombs. So anytime we discuss Q, it's in units of coulombs. Notice that before, when we talked about Coulomb's law, we used a small case Q. And this is a larger Q. It's referring to charge, but it's only that the small case Q is referring to minute elements. So these are very small particles, thus they have small charges, whereas this Q refers to the total charge. Is equal to C, the capacitance, times V, the voltage. Voltage is in units of volts. And C, of course, in farads. We will look at a capacitor momentarily. Resistors. Resistors certainly resist the flow of current. Resistors come as a symbol R and the units ohms, also symbolized with the Greek letter omega. In terms of resistors, they are symbolized by what can only be described as a squiggly line. So this is the symbol for a resistor. Resistors can be hooked up in a couple of different ways. One is when they're hooked up one after another. Because one is after another, it is called in series. So if this resistor is R1 and this resistor is R2, if you want to calculate the total resistance of resistors in series, well then the R total would be equal to R1 plus R2. Resistors can also be hooked up like so. This would be called in parallel. If you wanted to calculate the total resistance across these resistors, it would be provided by the following equation. 1 over R total is equal to 1 over R1 plus 1 over R2. I have two things to say about this. First, common mistake that students make is to forget that this is the reciprocal of R total. So they'll put R total is equal to 1 over R1 plus 1 over R2. And then they make the mistake that way. So that's one way to make a mistake. The other thing is that you do have to practice this. Whenever you see this question, among the materials that you will be getting with this course, is very important for you to actually practice it longhand. Never use a calculator when you're practicing for the MCAT exam. There's no calculator on the MCAT, and you must practice your longhand calculations. It's a very important part of your preparation, because when you start getting, say, 1 over 3 and 1 over 17 as your fractions, then you have to find a common denominator and then use your basic algebra. Of course it sounds simple, but when you're nervous and you're pressed for time, that's when people make mistakes because they're not used to using their basic high school algebra. So very important to calculate out longhand. One other thing to mention about this is if you see something like this on the MCAT exam, it is not time to get nervous, because clearly This is simply resistors in parallel, identical to this, only that one of the wires is a little longer here and one of the other wires are a little longer there. That has no impact on your calculations. What the MCAT loves to do is take something that you're familiar with, that you've seen before, alter it slightly, and see whether or not you're able to adapt. And of course here, that would be no problem. Next, we'll talk about battery. The battery is given in units of volts. There are many other ways to symbolize the battery. Not just V, but also EMF. EMF stands for the electromotive force. It is the same thing to designate a battery. And the units, once again, is volts. Sometimes EMF is symbolized by the Greek letter epsilon, which is capital E. There are two equations that absolutely must be memorized, which are relevant to the voltage in a circuit. The first is V is equal to IR. That is, V, the voltage, is equal to I, the current, times R, the resistance. Current is in the units of amperes. We already said that V, the voltage, is volts, R is in ohms, I is in amperes. 1 ampere is equivalent to a coulomb per second. In other words, because current refers to the movement of charge, therefore the definition of an ampere is the amount of charge which moves past a point per second. The second equation that must be memorized is P is equal to IV. That is, P, the power, which is given in units of watts, is equal to I, the current, times V, the voltage. These two equations must be memorized. It's almost guaranteed that at some point on the MCAT exam, there will be an equation that is based just on the use of these equations. So let us look at a basic circuit. We will start with this circuit in order to explain certain concepts. First off, we have two parallel lines. Two parallel lines in a circuit represents a capacitor. Now, if you were to take a capacitor and you were to place an insulator in the capacitor, then it is now called a dielectric. That is by definition. It would be then called a dielectric. So we also have in our circuit a resistor and finally a battery. So a battery is symbolized by two uneven parallel lines. The larger part or terminal is always defined as positive. The smaller terminal, negative. So anytime you see a battery, this is the first thing you can do to start labeling your circuit. Current is defined as the movement of positive charge. This is one of these 19th century errors that was started because people were trying to consider what is electricity. And initially, well, basically they had to guess. It's either the movement of positive charges or it's the movement of negative charges, because it is the movement of charge. And based on certain assumptions, it was thought that it was the movement of positive charges. We now know that electricity is the movement of electrons. And therefore, electrons being negative, that means that electricity is the movement of negative charges. But because of this essentially 19th century error, we are stuck with the definition that current is the movement of positive charges. And using this definition, we can still solve all problems with regards to circuits. So, when looking at the battery, after defining your terminals, we know where current would be emanating from. Current must be coming from the positive terminal. So we can say right away that here is our current, symbolized in this manner. Current I is leaving the positive terminal, coming along the wire, going up to this point here. This point would be called a junction. It's a point in the circuit where the current can go two different ways. Current can come along here and meet a resistor, which will resist its movement. Some current can come along here to the capacitor, and then the current would charge the capacitor. The current comes along here, positive charges here, and it starts to charge the capacitor. This terminal of the capacitor would start to become positive, this terminal of the capacitor negative. Now, would the opposites attract? Clearly, opposites attract. But the purpose of a capacitor is to store and separate charges. Therefore, these charges will not meet because the capacitor stores and separates the charges. So, when the battery is hooked up, the current will move in this way, charging the capacitor. Some of it current will complete the circuit and come along through the resistor, through the resistance in the resistor. Now, what happens is that when the battery is hooked up, the charge is going into the capacitor. If we were to stop the battery, if we were to unhook it, disconnect it, well then the charge in the capacitor would be released, thus discharging the capacitor along this long route here. It cannot go across here because that's the purpose of the capacitor, to separate the charge. Instead, it would come across in this manner as opposites are being attracted to each other. Now, what would be the purpose of this? There are many purposes for this. First of all, it has to do with current itself. There are two types of current that we use. One is direct current, and the other is alternating current. Direct current provides a continuous level of current. Alternating current provides current that comes and goes, comes and goes. Thus, it is alternating. There are two important points to make with regards to the difference between alternating currents and direct currents. To begin with, a direct current, because it's steady and it's always there, compared to an alternating current which comes and goes, comes and goes, clearly the direct current will have a value which would be greater than the alternating current. And this can be calculated. In fact, when we talk about the alternating current, we don't talk just about the current level, we talk about the root mean square current. So we have I, RMS. That's the root mean square current. And that is equal to the maximal current divided by root 2. And of course, the value for root 2 is something that you should have memorized, which is 1.4. So the root mean squared is equal to the maximum current divided by root 2. Whenever we talk about batteries, you may have batteries for many household items. We're talking about direct current. That is current that is continually coming from the battery. When we talk about, for example, the current that comes to your home, when you plug something into the wall, that is alternating current. That is the way current is delivered to homes and businesses. that alternating current, we can calculate the precise current, which is the current, but root mean square. One more thing to say about capacitors and the current that comes from it in terms of the value. When you have current going into sensitive equipment, for example, your computer, if the current was always alternating on and off, that could be disruptive for your equipment. So that's why you'll have capacitors in the computer. It will steady the current. For example, when the current is on for this alternating current, it will run your computer and it will charge your capacitors in the computer. Then when the current goes away, your capacitors will discharge. Therefore, they will now run the computer. Then when the alternating current returns, it will recharge your capacitors and it will run your computer. So we see the value of the capacitor, charging it, and then it can release its charge, continuing to supply current to the circuit. The actual ability of the capacitor to separate and store charge depends on the separation of the plates, and it also depends on the size of the plates. You are actually thinking with a capacitor. This is a rather symbolic cartoon of a neuron or a nerve cell in your brain. And what we'll look at in more detail in biology is that in a neuron, the outer part of the cell, the exterior part of the cell's membrane, is positively charged. The interior part of the membrane is negatively charged. And so clearly, just by looking at this, that is what a capacitor is. It separates and stores charge. So the membrane is a capacitor, and it has a voltage associated with it, Vm, which is the voltage across the membrane. So the capacitor separates and stores charge, and so when, depending on certain elements that we'll look at in biology, when the capacitor discharges itself, it will send a signal along the neuron. So now you see the importance of a capacitor and how a circuit can work with a resistor and a battery. Now we're going to look at a more complex circuit, and we'll solve it. And by solving it, you will be able to solve any circuit they provide for the MCAT exam. We will now look at a complex enough circuit such that by understanding the concepts involved in solving this circuit and knowing the equations, you will be able to solve essentially any circuit that they give you for the MCAT exam. The first thing to do when presented with the circuit is to label it. So we can see that there are two batteries, noted because of the parallel lines which are uneven. So we can label the batteries as epsilon 1 and epsilon 2. Epsilon representing the EMF of the battery, which is the voltage of the battery. There are 3 resistors, and so we will label them as well, and we'll give them original names such as R1, R2, and R3. So those represent our 3 resistors and our 2 batteries. So let's examine what will happen when this circuit is connected. Well, we have our positive terminal here, negative terminal there, positive terminal here, negative there, the larger terminal always being positive. And as we said before, current emanates from the positive terminal. So coming from the terminal will be the current, which we will designate as I. Because this current is coming from epsilon 1, we'll call this current I1. So I1, the current is coming from the terminal, passes through the resistor R1, and then comes here to this point. This point we'll call point A. Coming from the other terminal, epsilon 2, will also be a current, which we'll designate as I2. And this current coming from the positive terminal, coming along through the resistor R2, also gets to the junction at A. So we have I1 coming across this direction, I2 coming across this direction, hitting at this junction. So now we're going to have a new current coming through here, coming through this wire, because the two currents are coming from here. We have a new current coming through this wire. We'll call that current I3. As I3 comes down here, it hits another junction. This junction is B. Then we're going to have a current coming through this wire and a current coming through that wire. Now, I would like you to consider for a moment, you can put me on pause, but consider for a moment, what would be the name of the current running through this wire? The current would have to be I1, and this current would have to be I2. And the reason for this is simple. The battery, which is generating the current, has a certain amount of current emanating from it and returning to it. The battery itself remains neutral. You can't buy in a store a positively charged battery or a negatively charged battery. A battery has positive and negative charges within it, but an equal amount of positive and negative charges. You can't buy a positively charged battery. And so the battery maintains its neutrality. So the current that leaves is the current that returns. We're going to look at that in more detail when we study electrochemistry in the general chemistry section of this series. But for now, it is quite clear that the battery must remain neutral. So now we've labeled the currents. There are only two laws that you must know in order to solve any of the circuits they can provide. These two laws are Kirchhoff's laws. Kirchhoff has two laws. The laws are, number one, the sum of current is equal to 0 at a junction. Law number two, the sum of voltage changes is equal to 0, and that is in a loop. With these two laws, you can solve any of the circuits that are provided to you. Let's start examining the first of Kirchhoff's laws. Sum of current is equal to 0 at a junction. First, we need to define a junction, which we mentioned before, which is an area where the current can have two different ways or possible routes. So these junctions would be twice in this circuit, which is at A and at B. So we have a junction here at A and a junction at B. The next thing we need to do is to define directions. When you do gravitational problems, at the beginning of the problem you need to define a direction for gravity. You say, for example, everything that's going down is negative. So then you know that if something is going up, it's got to be positive, and if something's going down, it's negative. You define it as such. In the same manner, we can define everything that goes into a junction as being positive and everything that's leaving a junction as negative. By sticking to this definition, then we will be able to solve the problems. So for example, at junction A, We have a current I1, which is arriving at the junction. We have current I2, which is arriving at the junction. So we will say I1 and I2 are positive. So we have I1 plus I2, both of them being positive. We have I3 leaving the junction. So then we will call I3 negative. Minus I3 is equal to 0. At the second junction, we have I3 arriving at the junction. Positive, because it's arriving. Then we have I2 leaving the junction. We have I1 leaving the junction. So I1 and I2 are negative. Minus I1 minus I2. And that's equal to 0. Both of these equations are saying the same thing. By simple math, you see in both of these equations, it is saying that I3 is equal to I1 plus I2. You may be looking at this and saying, well, that's common sense. And it does make perfect sense, because examine what is happening here. We have I1 coming into the junction, I2 coming into the junction, I3 leaving. Clearly, I1 plus I2 must equal I3. And that is exactly what the equation is saying. Now, how could the MCAT trick you with such a basic concept of all the current coming into the junction must be equaling all the current that's leaving the junction? We'll examine this question. The currents and directions are as shown. What is the current that travels in wire P? You may want to take a moment and pause and consider what the answer would be based on Kirchhoff's first law. If we look at the currents, we have 2 amperes, an amp being the unit of current, 12 amperes here. Both of these are currents that are moving towards the junction. Here we have 7 amperes and 7 amperes moving away from the junction, arrows pointing away from the junction. So if we define everything as, and then we have wire P, we don't know if that's going towards the junction or away from the junction. We don't know. But we do know that Kirchhoff's law tells us that the sum of currents are going to equal to 0 in the junction. So we have 12 going into the junction, so that's positive. 2 going into the junction, positive. We have 7 leaving the junction, negative 7. Another 7 leaving the junction, negative 7. And then we have wire P, and all that is going to equal to 0. Well, 12 plus 12 is 14. Minus 7 minus 7, that's minus 14. So we have 14 minus 14, well, that's 0. So then P is equal to 0. The current in wire P is equal to 0. So the amount of current that goes into the junction is already equal to the amount of current leaving the junction. So that means there must be no current going through wire P. So all they do is take something that you already know, change the angles or change the way it looks to see whether or not you truly understand the concept. Well, now let us look at Kirchhoff's second law. Kirchhoff's second law is that the sum of voltage changes is equal to 0 in a loop. So first we'll need to look at what is a loop. A loop we will define as any enclosed area of wire. For example, this area here would be called a loop. This area here is also a loop. In fact, this area here is also a loop. In order to solve any problems that they would present, we would only need to examine 2 loops. So we're just going to choose 2 loops and look at how we can solve problems. We'll look at this loop, which we will call Roman numeral 1, and this loop, which we will call Roman numeral 2. Just like in gravitation, where you need to define the direction of positive or negative, just like when we looked at the first Kirchhoff's law and we had to define the direction of currents being positive or negative, indeed here we need to do the same. So we need to say what direction going around a loop will be positive or negative. You choose whatever you wish, it's arbitrary, but then you stick to it. For example, we can say that moving this way around the loop, so moving in this way around the loop, would be positive. So let's be consistent. So moving this way around this loop would also be called positive. So now let's move around the loop and watch the sum of voltage changes in order to resolve Kirchhoff's second law. So here we leave epsilon 1 and we're going around the circuit in this direction, and we have our first voltage change. What is our first voltage change? Well, we saw from our electricity equations, the fundamental equations include P equals IV and V is equal to IR. And so we have our first voltage change, which will be V is equal to IR. In other words, I1 R1. That's our first voltage change, I1 R1. And notice that the direction of positivity being this way, as we're going around the circuit, I1 is in the direction of positivity. So it's a positive I1 R1. Now as we're going along the circuit in our loop, I1 R1, we come down here, and we go through the second voltage change, V equals IR, so this is I3 R3. And that's positive because I3 is in the direction of positivity. So we come around here, I3 R3, and then we enter the battery at the negative terminal. Many students find that it is easiest to remember this such. That is, that when you enter the negative terminal of the battery, then the value for your voltage is negative. When you enter the positive terminal of the battery, then the value is positive. So as you come along and you enter the negative terminal, we have negative epsilon 1, which is equal to 0. So the sum of voltage changes is equal to 0. Now let's look at our second loop. That was our first loop. Let's look at the second loop. In the second loop, again, we will go around in this direction. Now, as we go around in the direction of positivity, we find our first voltage change. But notice that I3 is going downwards, but positivity is upwards. So we have our first voltage change, which would be negative I3 R3, because the current is going in the opposite direction as to what we defined as being the positive direction. So here we go. Continuing in the positive direction, we come across in this way, and we have our second voltage change. As I2 is moving in this direction, we're moving in the opposite direction. So our second voltage change will be negative I2 R2. And then as we're going around the circuit, we enter the positive terminal of the battery, which is positive epsilon 2. And all that is equal to 0. So the sum of voltage changes is equal to 0. Using these equations, you would be able to solve whatever problem they're going to provide to you. Just understanding these basic laws, Kirchhoff's laws, the first and second laws, sum of current changes, sum of voltage changes, and also the basic equations that we looked at, which are the equations for resistance in parallel and series, voltage, V equals IR, P equals IV, and the equation for capacitance, which is Q is equal to CV. That is the end of electricity. We are now going to move on to waves, light, and optics. We will now examine waves, light, and optics. We will begin our discussion with waves. First, a definition. Waves are an energy transfer by periodic disturbances of a material medium. The exception is electromagnetic waves. Electromagnetic waves transfer without a material medium. For example, light. Light can transfer throughout space without having a material medium. There are two types of waves. There are transverse waves and longitudinal waves. In a transverse wave, disturbed particles vibrate perpendicular to the advance of the wavefront. In a longitudinal wave, disturbed particles vibrate in the same direction of the advancing wavefront. So let's look at some examples. An example of a transverse wave, let's imagine it's spring break and you're going to Cancun, you're hanging out at the beach, and you're thinking of what else? Physics. So you're looking at the water on the beach and you see that there are waves. And the waves, you notice, are advancing onto the beach. Let's imagine that a bug lands on the water. So you see a bug that lands on the water and is right here at the surface of the water. Well, as the waves are advancing onto the beach, what do you notice about the bug? Is the bug moving towards the beach, or is the bug going up and down on the surface of the water? Good experiment to try, and you will notice that the bug goes up and down on the surface of the water. It does not move towards the beach. Therefore, we have a wave that is advancing in this direction, yet the disturbed particles on the wave are moving up and down. Thus, the disturbed particles are moving in a perpendicular direction to the advancing wavefront. That's the definition of a transverse wave. Another classic example of a transverse wave is if you could imagine a student taking a rope and attaching it to a wall. If the rope is attached to the wall and the person goes like this or flicks the rope, then what will happen is that you will see a wave moving towards the wall. So there's an advancing wavefront towards the wall. But clearly, the whole rope doesn't move towards the wall because you're still holding on to one end of the rope. Therefore, the wavefront moves towards the wall, but the disturbed particles, which are the parts of the rope, actually just go up and down. Transverse wave. Now let's look at a longitudinal wave. And this is where the disturbed particles move in the same direction of the advancing wavefront. And the classic example of this is sound. In fact, there was a film some years ago called Back to the Future Part 2. And in it, Michael J. Fox stands in front of a huge speaker. And a speaker is just a classic shape of something that could create a longitudinal wave, because the speaker is shaped sort of like a cone and pushes in this direction. And as it pushes, it disturbs particles in the air in the same direction of the wavefront which advances. And so in the film, Michael J. Fox stands in front of a massive speaker, puts on a guitar, and then plays his guitar and goes flying backwards, which is an exaggeration of the movement of particles in the same direction of the advancing wavefront. there are a couple of consequences of sound being something that disturbs particles in the same direction of the advancing wavefront. Here are some important consequences. First, there is no sound in a vacuum. That is to say that if you were to take a container and remove all particles from the container, and you were to put an alarm clock in it, say those old-fashioned metal alarm clocks that bang and ring and so on, and you were to put that into a vacuum, which means a container which is evacuated of all particles, then the alarm clock would go off and you would see it motioning, that it was actually going off. You would not hear anything. And that is because there's no particles around it to transmit the wave. So there can be no sound in a vacuum. Another consequence is that solids are better transmitters of sound than, for example, gases or liquids. Why? Because obviously a solid is something that is more dense, and therefore it has more particles that will vibrate in the same direction of the advancing wavefront. Classic example is, for example, a train. If a train is approaching, you will be able to hear it, obviously, that the train is approaching. But before you can hear it through the air, if you put your ear to the tracks, you will actually be able to hear the sound approaching long before someone could hear the sound of the train just from the air. Because the transmission of the sound through the solid, the tracks, will be much more acute than it would be through the air. Obviously, I am not recommending that you try this experiment. Third thing is that the velocity of the wave increases as the temperature increases. This is sort of like kinetic energy. Kinetic energy, one would expect, increases with temperature, the movement of particles. So as the kinetic energy increases, the particles are more mobile and therefore can transmit your sound wave much more capably. So as the temperature increases, so will the velocity of wave. Now let us look at a structural wave and some of its characteristics. We are now about to look at some important characteristics of waves. This is the crest of a wave, and this is the valley. Over here, the height of the wave is called the amplitude. The amplitude of a wave is related to intensity. Intensity represents, for a sound wave, loudness. And for light, which is a form of electromagnetic radiation or wave, intensity represents brightness. So this is the amplitude. Here is a wavelength, which is the length, of course, of one wave. Now, one wavelength is also defined as the distance between two crests or the distance between two valleys. It could also be represented in this manner. The wavelength is related to the frequency of the wave, which we'll talk about in a moment. In terms of frequency, however, when there are two waves passing through the same medium with the same frequency, they form a standing wave, which is represented in this manner. A standing wave has different aspects of it. One of the aspects is there are portions of the standing wave that does not move. These areas here of a standing wave which do not move is called the nodes. The part of a standing wave that has maximal motion, here and here, these are called the antinodes. They have maximal motion, which means they will move up and down in this manner. When two waves pass through the same medium, they can interfere with each other in many ways. the most important things are constructive and destructive interference. Thus we have constructive and destructive forms of interference. Let's imagine that there are two waves that are moving exactly in phase. So here are two waves that are exactly in phase. These waves would lead to maximal constructive interference. Thus we have constructive and destructive forms of interference. Let's imagine that there are two waves that are completely in phase. These two waves would lead to a maximal constructive interference. What is very important to notice is that each point on the wave is added to the other wave. Thus, the resulting wave has a greater amplitude. And of course, as we mentioned before, that refers to intensity, loudness, or brightness, depending on what type of wave we're talking about. So the amplitude is much, much greater. However, notice that the wavelength is unchanged. So constructive interference leads to an addition of the amplitude, but no change in the wavelength. Now let us look at destructive interference. For maximal destructive interference, we need two waves which are exactly out of phase. So these two waves are exactly out of phase. So if we were to add each point to the other wave, then we would get this, which is a flat line, nothing at all. In other words, for maximal destructive interference, you would either have no sound or no light, as examples. In fact, this is one of the things that was used in order to develop stealth-type technologies, and that is to create something that is able to listen for loud sounds and create wavelengths which are opposite in phase. And then throwing out these wavelengths would lead to two sounds which are loud but exactly out of phase, creating no sound at all. So you can imagine how this could be used for airplanes. Now here is another consequence of interference, but now for light. Diffraction. Diffraction is defined as the bending of light around corners. And there is actually an experiment which is often done in first-year college courses, which is able to demonstrate diffraction and patterns caused by diffraction. It's called the Young slit experiments. And the reason it's called a slit experiment is because a dark glass piece is taken and fine slits are made in the glass. The slits are so thin that they are of the order of the wavelength of light. So let's imagine that we have a slit here. We're super magnifying it, and this is of the order of wavelength of light. Now let's imagine that light is on the other side of the board, and this board is completely black, and there's only this one slit where light can come and illuminate where we are. What we would see, if this slit is really, really tiny, is that light would be coming through as waves. So you can imagine that because of the shape of a wave, some of the light will appear to bend around the corner. Where the experiment becomes very interesting is that many slits are placed in this glass. And therefore, as light comes out, the light is going to start to interfere. When light interferes constructively, it will create a bright band of light. Where the light will interfere destructively, there will be simply darkness. And so, in the young slit experiment, which provides evidence not just for diffraction, which is light bending around corner, but also shows evidence of interference of waves, you would see bright bands, dark bands, and also other shades of gray where there might be different levels of interference between the different waves. Now let's look at some equations that you absolutely must memorize. Now we're going to look at a few equations that you absolutely must memorize. Let's begin with a definition. First, frequency. Frequency is defined as the number of waves passing a point per second. The units is hertz. First equation. Frequency is equal to 1 over t, where t is the period of the wave. Because the period of the wave is simply the inverse of frequency, clearly the period of the wave is the number of seconds required for one wave to pass or oscillate. Second equation, beat frequency. And that's simply equal to the difference in frequencies. Now, to explain beat frequency, I would have to give some notes, and I must say that as a courtesy to my friends, I never sing in public. But I so much want you to understand this concept that I will demonstrate what beat frequency is. A beat frequency is often seen by musicians, and what they would do is they would play two notes that are very similar in order to tune their instrument. Classically, it's a stringed instrument like a guitar. And so two notes are played that are very similar, but their frequencies are a bit off, and therefore you hear a new frequency, which is called the beat frequency. For example, a pure frequency might sound like doom, and then the person plays another frequency just like that, but a little bit different, and then a new frequency comes in between them. So they play the first one, doom, the second one, doom, and then they hear a new frequency, doom, and it is that new frequency between the two frequencies which represents the beat frequency. And in order to calculate that frequency, that new one which is oscillating, one just looks at the difference in frequencies. And sometimes on the MCAT exam, the question will be that simple. They'll give you two different frequencies and they'll ask you what the beat frequency is. You either understand it or you don't. But now you should. The next equation that must be memorized is the following. V equals lambda frequency. V is the velocity of a wave, is equal to lambda, the wavelength, times f, the frequency of the wave. Now, I must say that there is a special case of this equation, and that's for light, because light has a constant velocity, and that velocity is c, and that's given by 3 times 10 to the 8 meters per second. And that's the velocity of light. So that's a special case for this equation. But this equation, V equals lambda frequency, which is lambda, which is the wavelength, this equation can be used in any type of wave. So if you wanted to calculate the wave that's being propagated in the water, or a sound wave, or if you go to the stadium and you're watching an NFL game and you want to calculate the frequency of the wave that people are doing, you just measure the wavelength, and then you can measure the velocity of the wave, and then you can calculate the frequency or whatever variable happens to be missing. And then the final equation to do with waves, which must be memorized, very important equation, is E is equal to hf, where E is the energy of the wave, which is equal to h, Planck's constant, obviously constant value, and you do not need to memorize the value of this constant, times f, which is the frequency of the wave. A classic question which they can ask you on the MCAT exam is, what would happen to the energy of the wave if the wavelength is doubled? So if the wavelength is doubled, if there's no other change in the medium, then the velocity would be constant. Because we mentioned that in solids the velocity would be higher, or if there was more kinetic energy or something of that nature. But if the medium is the same, then the velocity of the wave will be unchanged. So if the wavelength doubles, we expect the frequency of the wave will be halved. If the frequency of the wave is halved, and this is a constant, if we have half the frequency of the wave, then we would have half the energy of the wave. This concludes our review of waves. We are now about to begin optics. Now we move on to optics. First, a couple of definitions. A real image. In a real image, light actually passes through the image point. In a virtual image, light behaves as though it diverges from the image point, even though it does not pass through the image point. We will look at clear examples of both real images and virtual images. But first, a couple of equations which certainly must be memorized. The first, which is a derivation of the Lensmaker equation, is 1 over O plus 1 over I is equal to 1 over F, which in turn is equal to 2 over R. O is the object distance, I the image distance, F the focal length, and R the radius of curvature. So you can see that there's this equation. There's also the equation which relates the focal length to the radius of curvature. The next equation you must memorize deals with magnification, where M is equal to negative I over O. M is the magnification, I the image distance, O the object distance. It's very important to recall the negative symbol before I over O. When the magnification is negative, then the object is inverted. When the magnification is positive, then the object is erect. Now that we have some of the basics done, we're going to go on and look at reflection. Now we will begin looking at reflection. The most simple mirror to examine is a plane mirror. A plane mirror is a flat mirror. We say it's plane, P-L-A-N-E, meaning it's flat, not plane as in P-L-A-I-N, which is a regular mirror. It so happens that a plane mirror is a regular mirror. Anyway, So let's imagine that there is an object in front of the mirror. So here's an object in front of the mirror. In optics, whenever we use a capital letter, it refers to the position of something. Small case letters refer to the distance. For example, here is the position of the object, large O, and the distance of the object to the mirror would be small o, which would be the object distance, which is the figure or the number or the variable which we can use in the equation that we saw before. So now, if we were to put an object in front of a mirror, the object would be sending out light rays in an infinite number of directions. Some of these light rays would be coming in the following direction. So in other words, we're going to just look at a subset, a small number of light rays, in order to solve problems. So there would be a light ray coming from the object going directly to the mirror. When this light ray hits the mirror, it will be reflected back towards the object. There will also be light rays that would be going off at various angles. When a light ray comes to the mirror, this light ray which arrives at the mirror would be called the incident ray. Then there will be a light ray that once it hits the mirror would be reflected away. So this light ray would be called the reflected ray. Now, if we were to draw a normal line to the mirror, and a normal line is defined as a perpendicular line. So I will draw here this dotted line, which is a perpendicular line to the mirror. It is such that the incident ray and the reflected ray are related. If we were to draw an angle in here, theta, the angle in here, theta, this angle between the incident ray and the normal line would be called the angle of incidence. This angle between the reflected ray and the normal line would be called the angle of reflection. It is such that the angle of incidence is equal to the angle of reflection always. Now, if you look at the geometry, we have parallel lines here, and we have a line coming across in this manner. So, in high school, we used to say this is called the Z rule, where the inner angles are equivalent. So this would also be equal to theta. Okay, so in summary, we have an object that is sitting in front of a flat or plane mirror. Light rays can hit the mirror and then reflected back towards the object. Other light rays going off at various angles such that the angle of incidence is always equal to the angle of reflection. Well, let us start to examine these lines, and we'll look at the geometry of what has happened. We're going to extrapolate backwards in this manner, following the direction of this line, and we get to a point over here, and this point is called the image point. So a capital I is used because it represents the position of the image. Small I is used here, representing the distance from the image to the mirror. All this within the limits of my ability to draw, of course, which is severely limited. Nonetheless, this gives you the general idea. Couple of points. The first thing they're going to want to know is this image virtual or real? I will show you why this is a virtual image, and there are three important reasons. The first reason is our definition. We said that in a real image, light actually passes through the image point. Clearly, if this is a mirror and the object is in front of the mirror, well then light is not passing behind the mirror. So this image point must be virtual. And in fact, our definition of a virtual image is that light behaves as though it diverges from the image point, even though it does not pass through the image point. So it fits within our definition. The other point is that when we have a positive value, the image is real, and we have a negative value, the image is virtual. So here, clearly, the object being in front of the mirror has a positive value, which is the distance to the mirror, but the image is in the opposite direction. It's in the other direction, and therefore will have a negative value. So here, I don't know what the value of the O is, the object distance. I don't know what the value of I is, the image distance. But I know that I is going to equal negative O. In other words, I is going to have a negative value because it's in the opposite direction of the object distance. So here is the second reason why I would be virtual. And then the third reason is your intuition. Consider this. If this was indeed a mirror and I was standing in front of the mirror, then I would be seeing my image reflected off the mirror coming back towards me. And when I look at the mirror, it would appear as though the image of myself in the mirror is behind the mirror. So I'm the object in front of the mirror, and I see my image behind the mirror. And it appears as though the image of myself is as far behind the mirror as I am in front of the mirror. The translation of that in mathematics is I is equal to negative O. However, if I'm standing in front of the mirror, and let's say that behind this mirror is a hallway, well then clearly my image is not in the hallway behind the mirror. It's a virtual image. It is not actually there. There is not light rays that are actually passing through that point in the hallway. And if you were to go around this mirror and look in the hallway looking for the image, well then I guess that would be a bit silly, or counterintuitive at least. So here are three reasons why in front of the plane mirror the image is virtual. Now let us look at a spherical mirror. This is a plane mirror. We will look at a spherical mirror, and in a spherical mirror it is curved. So we're looking at a spherical mirror. Now we have an object here. That's the object point in front of the spherical mirror. And let's draw an axis to the mirror. When we draw an axis from our object to a spherical mirror, the intersection with the mirror is called the vertex V. So this is the vertex V, which is just the intersection of the axis which we draw from the object to the mirror. Well, this kind of mirror is concave. And you may remember from high school hearing that if it goes in like a cave, it's concave. And then, of course, convex would be the opposite. So, emanating from this object is an infinite number of light rays. It so happens that concave mirrors are converging mirrors. So they converge light. So some light rays coming from this object would be going straight here and hitting the mirror and then going back to the object. The distance between the object and the vertex V would be our object distance, small o. Light rays emanating from the object in various directions may hit the mirror like thus and converge to a point. This point is called the image point. The distance between the image point and the vertex would be small I. Now, a curved mirror must curve around some point. So, in other words, it's just like a circle. A circle has a center, and it has a radius, and then the circle curves around the center. Well, in the same sense, there is a center about which a curved mirror curves. So this point here is the center of curvature. The distance between the center of curvature and the vertex V is the radius of curvature. So now we start to develop many of the terms that we saw in our equation from before. 1 over O plus 1 over I is equal to 1 over F, which is equal to 2 over R. Where here's the radius of curvature. Indeed, we can calculate the focal length from the radius of curvature because 1 over F is equal to 2 over R. And we also have our object distance and our image distance. So, first simple question. Is this image virtual or real? We start with our definition. Our definition of a real image is light actually passes through the image point. Clearly, light reflected from the mirror actually passes through this point. So this is the image point. And you might wonder, well, what does that mean? And there is an experiment in which a stick is placed here, an object is placed here, a curved mirror is placed here. Then you take a screen, just a white screen, and the screen is moved along the stick. And once the screen gets to this point, voila, you have the object in clear focus at this point, the image point, because light actually passes through that point, so you can get the consequences of that light passing through the point right here by placing, for example, a screen. And there you can calculate the image distance. You know where you put the object, so that's the object distance. Therefore, you can calculate either the radius of curvature or the focal length of the lens. So here we have a real image and obviously a real object placed before the mirror. So the next question that they can ask, besides the issue of real or virtual, they can ask you whether or not the image is erect or inverted. In other words, if the object was an arrow pointing up, over here, would the arrow be pointing up or pointing down once you place the screen there? And for that, we use our magnification equation, where m is equal to negative I over O. Now recall, here we have an object distance before the mirror. Clearly, that's a positive distance. Here we have the image distance in front of the mirror, as opposed to what we saw with the plane mirror. This image is in front of the mirror, so clearly this is a positive image distance. That's another reason why this must be a real image. So we have a positive I and a positive O. Even though we don't know what the values of I and O are, we know that they both must be positive. And if they're both positive, both I and O is positive, that means the magnification would be negative. If the magnification is negative, by our definition, it must be inverted, because we said a positive magnification meant that the image would be erect, and a negative magnification meant that the image would be inverted. The next question that they could ask is the image diminished or enlarged, meaning whatever size you started with as an object, when you examined the image, would the image be smaller or would it be bigger? Well, consider this. If I were to tell you that something had the magnification of 50, that would mean that the image that you're looking at is 50 times larger than the object. So if the magnification was 10 times, then you knew that the image is 10 times larger than the object. And finally, if the magnification was 1/2, well, that would mean that the image is smaller than the object. In other words, if you have a magnification less than 1, it would mean that the image is smaller than the object. And if the magnification is greater than 1, it would mean that the image is larger than the object. So, I don't know what the value of the image distance is, and I don't know what the value of the object distance is. But I do know that the image distance is clearly less than the object distance. So in the magnification equation, if the image distance is less than the object distance, clearly we'll end up with a fraction. And a fraction being less than 1 means that we'll end up having a diminished image. Now that we've examined reflection, we're going to go on to refraction. Now we're going to look at refraction. Now just to compare, in reflection we saw that when the incident ray hit the mirror, it was reflected in such a way that the angle of incidence always equals the angle of reflection. In refraction, we have something different. We have that a light ray that hits a medium which is more dense, for example, a light ray which is traveling in the air hits glass, which is a medium which is more dense. What will happen is that the light ray will bend. And refraction is discussing and looking at what happens when that light ray bends while it's going into this other medium. So, to discuss refraction, we're going to look at thin lenses. So these are thin lenses of glass. So here is a thin lens. This lens is a convex lens, also called a biconvex lens because it's convex on both surfaces. We put in front of the lens our object. Once again, the distance between our object and the lens would be our object distance, small o. Coming from this object would be light rays emanating at an infinite number of different directions. Some of the light rays may come in directions such as this one. So the light ray hits the lens like so. Well, the lens, being a convex lens, converges light. Convex lenses converge light, and concave lenses diverge light. And you can see already there's going to be a difference between reflection and refraction. So the light converges to a point, that point being the image point. So the first question, is this image real or virtual? Well, our definition of a real image is that light actually passes through the image point. So clearly the light ray passes through this point. So this indeed is a real image. The distance between the image point and the lens would be our image distance, small I. What is interesting is that this is a positive distance. The distance between the object and the lens, that's a positive distance O. This distance here is also a positive distance. This is another difference between reflection and refraction. After all, in reflection, because it's a mirror, the only way that the object and the image can both be real is if they're on the same side of the mirror, because the mirror reflects and there is no light passing onto the other side. However, for a lens, light from the object passes through the lens. So to have a real image, it has to be on the other side. And therefore, the distance between the image and the lens has to be positive. So here we have a real object and a real image. And therefore, once again, a simple experiment is by putting an object in front of a thin lens and taking a screen and moving the screen until the object is completely in focus. We would know our image distance, we would have known where we placed the object, and therefore we can calculate the focal length or the radius of curvature of the lens according to the equation we saw, 1 over O plus 1 over I is equal to 2 over R or equal to 1 over F. Let's look at another scenario. Now we will look at a concave thin lens or a biconcave thin lens. We place our object here, and coming from the object are light rays going in innumerable different directions. Some of the light rays will hit the lens like so. Now, when the light ray hits the lens, because this is a concave lens, the light will diverge, because a concave lens diverges light. So the light diverges, but we can extrapolate backwards to a point here, and that will be our image point. Once again, the distance between I and the lens would be our image distance. The distance between O and the lens is our object distance. Now, if we were to look at our definitions, is this a real or virtual image? Clearly, light does not pass through this point. Light behaves as though it diverges from this point, even though it does not pass through this point. That is our definition of a virtual image. So we've seen a real image and a virtual image with lenses, or in the context of refraction, and we've also seen it in the context of reflection. Now there's just a couple of things to memorize in terms of equations. First, we'll look at the power of a lens. There are a couple of equations that you must memorize. The first one has to do with the power of the lens. If you wear glasses or if you have contact lenses, you may have heard your optician refer to the power of your lenses. So first of all, the power of a lens is given in units of diopters. The equation is simply the power of the lens is equal to 1 over f, where f is the focal length of the lens. What is important to remember is that the f is given in units of meters. So when you have to calculate the power of the lens, it is important to convert the focal length to meters, and then you just take the inverse. So the question could be that simple on the MCAT exam. They can give you the focal length in centimeters, for example, and then just ask for the power of the lens. Then you convert to meters, and then you just take the inverse to get the power of the lens. The value may be positive if it is a converging lens, and negative if it's a diverging lens. Next, we're going to look at Snell's law. Snell's law describes mathematically in what way does light bend as it passes from one medium to another. For example, let's imagine there's a surface here, and there's a light ray that's coming and hits the surface. So here is a light ray coming down and hits this surface. Well, different surfaces different media have a different ability to bend light. And so when the light ray hits this medium, we can draw a normal line. And a normal line, as I mentioned earlier, is just a perpendicular line to the surface. So let's draw a perpendicular line to this surface. So we have an incident ray arriving at the surface. Then you can imagine this surface being something like the surface of water, where the incident ray is in the air, and then it comes down, it hits the surface of the water, and then it's going to be bent by the water. So as it comes, it hit this angle here would be, of course, the angle of incidence, which is the angle between the incident ray and the normal line. Once it hits the surface, it will bend. Now, depending on the medium, it may bend towards the normal line, as if it was going into a heavier medium, or it may bend away from the normal line if it were going into a lighter medium. Now, let's look at an example where it's coming from water, for example, and is going into a lighter medium like air. Then it would bend away from the medium, and then this would be the refracted ray, and then we would have another angle here, which would be the angle of refraction. So if we had two different media, one up here and one down here, each medium, as I said before, has a different ability to bend light. Let's say that we call this N1 up here. N1 would represent the index of refraction, or the ability of this substance to bend light. N2 down here, for this medium down here, would be the ability of this medium to be able to bend light. It is such that the higher the index of refraction is, the greater the ability of that substance to bend light. So let's call this angle theta 1, and we'll call this angle theta 2. Well, Snell's law gives us the relationship between these variables, such that N1 sine theta 1 is equal to N2 sine theta 2. And this would certainly be one of the equations to memorize. Now we're going to look at a very important consequence of this relationship, and a special case to develop the idea of the critical angle. Now we're going to look at a special case of Snell's law. Consider the following. Let's pretend we're underwater and we place an object under the water. So water is a more dense medium than air. Water has a higher index of refraction. It has a greater tendency to bend light. So let's put an object under the water, whatever, a brick or something. And coming from this object would be an infinite number of light rays going at various different directions. Some of the light rays would be going straight up and would be transmitted through the surface of the water. There will be light rays that will be going off at various different angles. A light ray coming off at this angle, incident to the surface in this manner. Part of the light ray would be refracted because it's going into a medium which has a smaller index of refraction. Then the angle of refraction will be greater than the angle of incidence, and therefore the refracted ray is refracted away from the normal line. as it's going into the lighter medium. Now note, even though the light ray is being refracted, there's always a portion of the light ray that is being reflected. When a light ray is being transmitted through a surface, there's always going to be part of the light ray that will be reflected back into the medium. It is such that, of course, as we mentioned before, the angle of incidence would always be equal to the angle of reflection. The angle of refraction, which is the angle between the refracted ray and the normal line, can be calculated according to Snell's law, where n1 sine theta 1 is equal to n2 sine theta 2. So this is all a review so far of what we've seen. But let's go further out. The further out we go is the more that the angle of refraction will be increased. And so we have this effect that is starting to occur. Well, there is such a point that if you go far enough out, the angle becomes 90 degrees. In other words, if you were to draw a normal line, you would have theta here, which would be our angle of incidence as the light ray hits the surface. Well, we went out so far that this theta, which should be our angle of refraction, is 90 degrees. So there is no angle of refraction because there is no refracted ray. The ray that should have been refracted is now going into the surface of the medium. The angle such that the ray is no longer refracted and no longer reflected is called theta c, the critical angle. Now, if we were to go beyond theta c, just a little bit more beyond theta c, or much further beyond theta c, all light rays would be reflected back into the medium. That's called total internal reflection. All light rays coming from the object would be reflected if the angle of incidence is greater than the critical angle. So now let's put this in practical terms. Imagine that you had a pool, a large pool, and the pool was empty. There was no water in the pool. You put a brick at the bottom of the pool and you start walking away. Well, once you get to the other end of the pool, you look back and you see the brick. Because the brick, you put the brick right there in the pool and there's no water. That's normal. Now imagine that there is water in the pool and you put the brick at the bottom of the pool. Well, what this is telling us is that you can start walking away, and you look back and you will see the brick. But it gets to a point that you will walk so far away beyond the critical angle where light is coming from the brick, you will walk and you will look back and you cannot see the brick because all the light coming from the brick is being reflected back into the medium, reflected back in the water. It is not being transmitted any longer. So that you look back and where you were before, when there was no water, you clearly saw the brick there. But now that there is water there, and that's a more dense medium with a greater index of refraction, then you can no longer see the brick because you are beyond the critical angle. Furthermore, imagine that you have a friend that's in the water, in the pool, and you're right at the side of the pool and you're looking at your friend, and then you start walking away. As you walk away and you look back at your friend, does their body seem to be more and more elongated or more and more squished together as you're looking at the part of their body under the water? The body becomes more and more squished together. Sorry, there's not a better scientific word for squished. And the reason is that As you're going out, now imagine that the object O here, friend's feet, as you're going away from them and you're looking back, you see this light ray. This light ray makes you think that the image is here, your friend's feet, which actually is a virtual image. So you think that their feet is way up here, but their feet they're really down here. But as you walk away, the feet start to rise because of the refracted ray coming from below the surface of the water. And finally, so how do we calculate the critical angle? Well, it's pretty straightforward. Let us imagine that the index of refraction of the substance below the surface, or water, is N1, and the index of refraction of the substance above, or air, is N2. Then what we get is N1 sine theta 1, which in this case is N1 sine theta c. So we have N1 sine theta c is equal to N2 sine theta 90 degrees, because it's 90-degree angle here. So we get N2 sine 90. And of course, you know that sine 90 is 0. Psych. Sine 90 is 1. And of course, you must know the sine of 0 degrees, 90 degrees, 45 degrees, 60 degrees, and the cosine of these angles as well. We will look at the triangles shortly in order to help you remember the cosines and sines of these various angles. But certainly sine 90 you should recognize as being 1. So sine 90 is 1. So we get that sine theta c is equal to N2 over N1. Clearly, the value of N2 must be less than N1, because sine theta can never be a number more than 1. N2 must be less than N1. Thus, we've completed our review of reflection, refraction, and optics. We are now going to start problem solving. These problems will involve forces, motion, gravitation. Most importantly, we will be resolving forces into their components. These problems are very basic. They're first year college or university level, and these problems are commonly tested on the MCAT exam. Let us look at our first problem. So, at the first year college level, usually complicating factors are eliminated. So this is a pulley system, and what you would be told in the problem is that this is a frictionless pulley, and these are weightless cords. So in this particular example, there are 3 masses, and each of the 3 masses is 10 kilograms. The question is simple. Is this system in motion? Yes or no? I think you should consider pausing right now and consider what you would provide as an answer to this question. Is this system in motion? Yes or no? The correct answer is cannot be determined from the information provided. And here's why. Let us resolve the forces. To begin with, we have a mass here, and the mass will have its weight as a force, and that weight is downwards, and that weight we call mg. This mass will also have a force upwards, which is the string, the tension on the rope or cord or wire. So this tension upwards, which we'll call T. So the mass experiences certain forces, its weight downwards, and the tension on the string. It doesn't matter if this mass is going up or down. Either way, it will always have its weight pointed downwards, which is essentially pointed towards the center of the Earth, because that is where the gravitational force is experienced between the center of masses, of two masses, which is something that we explored earlier. And then there's the tension in the string, which is upwards. And that tension, that force, is upwards no matter if this mass is going up or down. It doesn't matter because there is a string or cord which is there, and there's going to be some force experienced by the mass. The same thing would be felt on the other side. We have downwards mg and upwards the tension. This mass would experience tension in these two directions. Clearly, the tension in the cord would be identical. In other words, the value of the tension, which is experienced by this mass, would be the same tension as in this mass, since the cord is continuous, and this is a frictionless pulley. So here is our system. Why couldn't we just say that clearly there is this is not in motion because it's perfectly balanced? Shouldn't it be not in motion? Not necessarily. All we can say is that the system is not accelerating. Big difference. And the key equation here is Newton's second law. And Newton's second law suggests that the sum of forces is equal to ma, where the sum of forces experienced by the mass is equal to mass times acceleration. Because this system is balanced, equal amount of weight on both sides, therefore there is no net force. And because there is no net force, we know that the acceleration must be 0. But does that mean that the system is not moving? Not necessarily. Because a system which is not accelerating is in a inertial frame of reference. Some people will just call it inertia. And what inertia means is that because there is no net force on the system is either at rest, not moving at all, or it is moving but with constant velocity. Thus, it is either this system is not in motion whatsoever because of its balance, or that at some point in the history of this system, someone just pushed one of these masses, and ever since that point, the system would be slowly moving, or moving at whatever velocity was the initial velocity. Because there's no friction to slow the system down, the system would be moving with that constant velocity. So the only thing that we can say about this system is that there is no acceleration. So now we can write Newton's second law. Sum of forces is equal to ma, which is equal to 0 because there's no acceleration because the system is balanced. The sum of forces experienced by this mass would be, it would experience the tension and the weight mg. The first thing we need to do is to define which direction is positive or negative. It doesn't matter which way you do it. You do it once and then you remain consistent. So we can define downwards as being positive. If we define down as positive, therefore mg, which is down, would be in the positive direction. So we would have mg, positive direction, tension T is in the negative direction, opposite to what we wrote here, minus T is equal to 0. Therefore, the tension is equal to mg. And so this is how we would resolve the forces in this problem, and most importantly are the concepts which I've described. Now let us look at a box. Here is a simple enough problem which reveals many interesting points. This is a box which is just sitting on a table. So we have this mass associated. If we were to start to resolve the forces associated with this mass, we would have, as described before, we would have the weight downwards, mg. So that is the weight of this mass. Well, that brings up some interesting points. First of all, when we have a weight downwards, there must be a counteractive force upwards. Otherwise, there would be a net force downwards, and then this mass would accelerate downwards. So if we were to put this box on a table, the box has a force downwards, which is its weight. The table pushes up on the box with a force which we call N, the force normal. There are a couple of important points about the force normal. To begin with, it is a counteractive force. The force normal always acts perpendicular to the surface of whatever the particular object or mass is on. So if it happens to be on a table, it acts directly upwards. But if it happens to be on an incline, we'll see later that the force normal has to be perpendicular to the incline, perpendicular to whatever surface that the mass is sitting on. So here we have our weight downwards, our force normal upwards, which is our counteractive force. Now, right now you're sitting on a chair, likely, and is the force normal of the chair, which is pushing up on you, because your weight is pushing downwards towards the center of the earth, is the force normal of the chair greater, less than, or equal to your weight? Well, imagine this. If the force normal was greater than your weight, then there would be a net force upwards. Net force means acceleration, Newton's second law. And that means every time you sat down, you would accelerate up to the ceiling. Doesn't happen. If the force normal was less than your weight, then if you were to sit down, because you would have a net force downwards, greater than the force normal of the chair, then you would accelerate downwards. And of course that doesn't happen. So if you are sitting in a chair, in equilibrium, an inertial frame of reference, you're at rest, then the force normal must be exactly equal to your weight. Now let's talk about weight. Some people may ask the question, how much do you weigh? And some people will respond, I weigh 160 pounds. Pounds. Now that's a unit of weight. So we'll look at weight. Pounds. Now, pounds would be a unit of weight in what is called the British system, sometimes called the imperial system. So I'll just write B as for British system. So that's the unit of weight. Now, some people say, if you would like to be more modern about it, someone might ask your weight and you might say 70 kilograms. Now, is 70 kilograms really your weight? Not really. Kilograms is a unit of mass. And kilograms is a unit of mass in the SI system, which stands for Système International, or the International System of Units. So this is kilograms being a unit of mass. So what is the unit of weight in the SI system? It is a Newton. Newtons are the units for weight, which is a unit of force in the SI system. I suppose because the difference between mass and weight is gravity, which is 9.8 meters per second squared, or approximately 10 meters per second squared. So it's 10 times the mass would give you your weight in newtons. I suppose people don't like saying that they weigh 700 newtons. Sounds like a lot. But nonetheless, that would be much more accurate. In the British system, the weight is in pounds. So what is mass in the British system, or the imperial system? The units are slugs. Believe it or not, they can ask a question like this on the MCAT exam. And that would be just asking whether or not you recognize what the different units are for mass and weight, etc. So, and furthermore, you should know the conversion factor between pounds and slugs. After all, it's just G, which is gravity. And G in the British system or imperial system is 32.2 feet per second squared. These are clearly constants which you must memorize. 9.8 meters per second squared for gravity, or approximately 10, and 32.2 feet per second squared, approximately 32 for the British system. When do you use 32.2 or 32 or 9.8 or 10? It depends on the problem. Basically, when you're writing the MCAT exam, you look at the question, you realize that you need to use gravity in it if it's necessary, then you look at the answers. And then by examining the answers and seeing how close the answers are one to another, then you can decide whether or not you can estimate the value of G or whether or not you have to use a precise value of G. It's the only way to know, because you would rather estimate the value of G in order to quicken your calculations. There is one other system of units that you must know, which is the CGS system of units, which stands for centimeter, grams, and seconds. So clearly, centimeter, gram, and second system, the unit of mass must be grams, and the unit of weight or force is a dyne, D-Y-N-E. And the conversion factor you should also be able to determine, because you know this is 9.8 meters per second squared, so the conversion factor to centimeters per second squared, it must be 980 centimeters per second squared. All this we learn from a box which is not even moving. Now let's move the box. Now we're going to move the box. So let us imagine we attach a string over here and we pull on the string in this direction. Well, there will be a force associated with this, and we'll say that it's T, which is the tension on the string or cord. Well, if this box is on a surface, we are now going to get a brand new force, and that is the force of friction. The force of friction is usually symbolized by a small case f. So as we are moving in this direction, there is a new force in the opposite direction. So let's talk about the force of friction. To begin with, the force of friction always acts opposite to the direction of motion, as you can clearly see here. Can we calculate the force of friction? Indeed we can. And the force of friction is given by F max is equal to mu n, where n is the force normal and mu is the coefficient of friction. So the maximal frictional force is given by mu n. Now why would it say maximal frictional force? Well, consider this. Let's say that I had a box right here, and I put the box on a table, and I started pushing the box with the force of 1 Newton, but the box didn't move. So if the box is not moving, that means that there must also be a force going in the opposite direction of my force of exactly 1 Newton. Now that force is the frictional force. Now if I'm pressing on the box with 1 Newton, could the frictional force be more than 1 Newton? Impossible. If it was more than 1 Newton, then the box would accelerate towards me because there'd be a net force. If I'm pressing with 1 Newton and the box is not moving, could the frictional force be less than 1 Newton? Impossible. Because if the frictional force was less than 1 Newton, then the box would accelerate in the direction of my force because there would be a net force. So here's the box again. I'm pressing now with 3 newtons. The same box on the same table, I'm pressing with 3 newtons. The box still doesn't move. Well, that means that the frictional force has changed. It is now 3 newtons. It is now exactly 3 newtons because the box is not moving and there's no net force. Well, it gets to a point that you're pushing so hard on the box that the box just starts to move. The second that box just starts to move, that means that the force you're applying must be greater than mu n. And if you apply a force which is greater than mu n, therefore you must accelerate. If you maintain the force, not only will the object move, but it must accelerate because there's a net force, because you're above the maximal frictional force. One more thing to talk about friction. There's 2 types of friction. There's the friction of something that's not moving, static friction, and the friction of something which is in motion, kinetic friction. Thus, there is a coefficient of friction for both static and kinetic friction. And the coefficient of static friction and coefficient of kinetic friction are related thus. The coefficient of static friction is greater than the coefficient of kinetic friction always. And you may have some experience with this fact. What this is saying is, for example, say that you had a couch to move. And what it is saying is that from your experience, if you had to move a couch or a refrigerator or something very heavy, it is always more difficult to get that thing moving than to keep it moving. Thus, when something is not in motion, it's static, and you have to push on it, that effort is greater than the effort to keep it moving once it's moving. Thus, the friction of, which is the coefficient of static friction, not moving, is greater than the coefficient of kinetic friction when it has already started to move. You are now looking at another classic pulley system. And the question is going to be much the same. My question to you is, given that this is a frictionless surface, frictionless pulley, weightless cord, classic first-year college stuff, is this system in motion? You may want to pause and consider your answer. Well, the correct answer is, because for this mass there will be a force to the right, but there is no force to the left, because there is no frictional force. Usually there would be a frictional force to the left, but if we're given that this is a frictionless plane, there's no force to the left. So therefore, there is a force to the right, because there's a mass here, so there's the tension on the string, or the rope. So we have T here, and so this is going to move to the right. This system has to move. For this mass, it experiences its tension on the string here, and it experiences mg downwards. That's small mg because it experiences its own weight downwards. One more question. Yes, this system is moving because there's no friction. My question to you is this system accelerating? You may want to pause and consider that answer. The correct answer is definitely. And it does not matter what the masses are. It doesn't matter if this is an elephant and this is a feather. Irrelevant. Whatever mass is present here means that there will be a tension on the cord to the right. Because there is no frictional force, nothing holding this mass from moving to the right, but there is a net force to the right, this mass must move. And therefore the system will be in motion as this moves downwards. So the masses will be irrelevant to the fact that the system will not only be in motion, but it must accelerate. So what would be the relevant equations? Well, first, let us define downwards as being positive, which is arbitrary. Then we will write our classic Newton's second law, which is the sum of forces is equal to ma. The sum of forces around this mass would be mg downwards minus T, the tension, is equal to ma. Thus, we have resolved the forces around this mass. To resolve the forces up here, if we were to resolve the forces in this direction, which of course would be considered the y direction, then we would have sum of forces is equal to m, a, large mass m, and in this direction we would get just that the tension T is equal to ma. So whatever question they were to ask you about this problem, you would be able to solve it just understanding these basic concepts. Now we're going to have to look at some basic geometry to remind you of some concepts in order to be able to do other types of problems. Here is a very short math review, just more so as a reminder of some basic concepts that you must be very comfortable with for the MCAT exam. To begin with, some of the right angle triangles. This is the classic 45, 45, 90 triangle, and the relationship of the sides, 1, 1, root 2. Of course, the Pythagorean theorem is fulfilled here, where a squared plus b squared is equal to c squared. And so this is the relationship of this triangle. And then you have the 30, 60, 90 triangle, the relationship of its sides, 1, root 3, and 2. In terms of the functions, you should of course know sine, cosine, and tangent. And also the inverse functions of these are also explained in the book, The Gold Standard. Some students like to have remembered from high school the expression sa ka toa, which stands for sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, tangent is opposite over adjacent, such that the cosine, for example, of 30 degrees being adjacent over hypotenuse, cosine of 30 degrees would be the adjacent side, which is this side, as opposed to the opposite side. The adjacent side of 30 over the hypotenuse, which would be 2. So that would be root 3 over 2. Now, in terms of the basic math for the MCAT exam, you do need to estimate values. And that means you should have memorized root 2 and root 3. Those are the minimum roots that you should have memorized. Of course, root 2 is equal to 1.4 and root 3 is equal to 1.7. Those, of course, are estimations. But nonetheless, these you should memorize. You might be on the MCAT and get something like root 19. Well, basically, if you get a value like this, you just need to estimate. And so you know that the number 19 is between 16 and 25, but closer to 16. You know the root of 16 is 4. You know the root of 25, which is 5. And therefore, the value, the result of root 19 must be somewhere between 4 and 5, but closer to 4. And then you look at the possible answers. And you see whether or not the answers are exactly what you estimated, or if the answers are very close together, very tight. And if they are tight, then you'll need to square the answers to find which answer is closest to 19. But usually they're far enough away from each other that usually, not always, but that they're far enough away from each other on the exam that you will be able to determine whether or not you have been able to hit it right with your estimation. Other things that you should be comfortable knowing is, let's say that they were to say the sine of 48 degrees. Now, the sine of 48 degrees doesn't fit with the triangles, 45, 45, or 36, but clearly the sine of 48 degrees must be pretty close to the sine of 45 degrees. Does it mean that you would be giving a perfectly accurate estimation? But that's not what the MCAT's about. You cannot use your calculator, but you must be comfortable enough to make reasonable estimations. We will now resolve a projectile motion problem. So here is a person with a ball who's launching the ball. The ball is being launched with a speed or velocity of 25 meters per second. It is launched such that it is at an angle of 60 degrees with the horizontal. The person is standing 20 meters from a wall. We can calculate innumerable things regarding this projectile which is being launched. We can calculate its highest point which it will reach. We can calculate where it will hit on the wall. We can calculate with what speed or velocity that it will hit the wall, etc. So these are all things that can be calculated using very basic equations, equations of movement or motion or kinematics. So one of the equations that you need to memorize is the following. VF is equal to VO plus AT. That is, that the final velocity, VF, is equal to the original velocity, VO plus AT. The other equation that must be memorized is delta x is equal to 1/2 AT squared plus VOT. So delta x, which is the displacement, and it does, even though it's an x, this x is actually a capital X and does not indicate whether or not you're looking at the displacement in the y direction or the x direction. All it's saying is that it's displacement, is equal to 1/2 AT squared, acceleration times time squared, plus VOT, the original velocity, times time. So, if we were to launch this projectile, one of the key things in order to solve problems regarding projectiles is time. The reason is that time is the one entity that is shared by the x and y components of this velocity. You see, when something is being launched at different angles, when we have different angles involved, like in projectile motion, like in momentum, like in inclined planes, all these different situations have different angles. These are situations where, if there are different angles, you must resolve them into x and y components. Basically, you're standardizing the problem. But when you resolve this velocity into its x component, which means along this direction, and its y component in this direction, the one thing that the x and y will share, always, is time. That's why it is frequently the first thing you need to calculate in a projectile motion problem. So, let us calculate the time required for this ball to hit the wall. So we want to know the time required. In order to solve this in the most easy fashion, what we do is we examine the x direction. The reason is the following. In the y direction, we have acceleration. The acceleration is, of course, due to gravity. That works in the up and down direction. So we have acceleration in the y direction. In the x direction, of course, first year physics, basic MCAT physics, we're going to neglect air resistance or friction caused by air when the ball is moving in the air. So in the x direction, there is no acceleration. Because there is no acceleration, it really simplifies things. It means that whatever velocity the ball had initially is identical to the final velocity because it never accelerated. Because there's no acceleration, no net force, no acceleration, therefore it remains in an inertial frame. That means it's either at rest or it's moving with constant speed. And clearly, if this leaves with an initial velocity and there's no acceleration, then it will move with constant speed and its velocity at the end will be the velocity at the beginning. That really simplifies things. Because if we know that the velocity in the x direction will be constant, velocity comes in units of meters per second, we know the distance from the person to the wall, which is 20 meters. So we know the meters. We know the meters per second. Well then, if we have meters over meters per second, the meters will cancel and then we'll pop out with seconds. So it's very easy to calculate the time. So what would be the initial velocity in the x direction? Let's call that initial velocity Vox. Thus we determine the original velocity in the x direction with cosine 60, since cosine 60 would give us adjacent over hypotenuse. Thus we have Vox is equal to 25 cosine 60. So to determine the time, we take the 20 meters over 25 cosine 60 meters per second. Thus meters cancel, seconds come up on top. In order to calculate this quickly and efficiently, which is key to the MCAT Physical Sciences section, divide both by 5. We have 5 left here. 5, that goes 4 times. Cosine 60, you quickly look at your triangle and determine that cosine 60 is 1/2. 1/2 in the denominator is like multiplying the top by 2. So we get 8. So the time required to hit the wall is 8 over 5 seconds. Now let's see where the ball would hit the wall. To determine where the ball will hit the wall, we are looking at the displacement along the y direction. So we would use the displacement equation. So we're looking at it along the y direction. So what we get is that the displacement delta x is equal to 1/2 a, which would be the acceleration, and the only acceleration in the y direction is gravity. So if we define downwards as, say, negative, arbitrarily, then we have 1/2 negative 10, more accurately 9.8 meters per second squared, but we'll estimate that as 10. The time squared is 8 over 5 squared plus VOT. VO is the y direction of the velocity, and because it's the y direction here, that would be the opposite, so that would be sine of 60 degrees. So 25 sine 60 times the time t, 8 over 5. So here we can calculate the displacement in the y direction. Note, it is the displacement, meaning the distance from where the ball left the hand to where the ball would hit the wall. If the question was, where did the ball hit the wall compared to the ground, you would have to add the distance between the ground and where the ball left the person's hand, because this is displacement, the difference between the initial position and the final position of the ball. Now we're going to do some work. When you think about work in the context of physics, you should just have a Pavlovian reaction and immediately think of force times distance. So work is equal to force times distance. We're going to have to be a little bit more specific. To begin with, the word distance. It's not really distance, it's displacement. Meaning, It depends on the initial and final position of the object. So this is a very important part of the definition of work. The other thing is force. The force, we have to be a little bit more specific, because work is where the force is in the same direction of the displacement. So sometimes the equation is written as work, W, is equal to FD cosine theta. The cosine theta takes into account that if the force is occurring at a different angle than the displacement, then you have to take the adjacent side in order to resolve the force into its component, which is in accordance with the displacement or distance. So let's look at some of the consequences of this equation. To begin with, let's say that you were in class and you saw an overhead projector. You picked up the overhead projector, you ran around campus with it, you came back to the classroom, and you placed the projector back in the classroom in the same position. How much work was done? 0. Because the initial and final position of the overhead projector was the same. And therefore, because work is force times distance, but really displacement, if the displacement is 0, the work done is 0. So say that you were to go to the Olympics and you saw some Hungarian weightlifter lifting 500 pounds over his head. While the weightlifter was holding the weight over his head, you can go up to him and say, at this moment, you're doing no work. And that is, once again, because if the person is holding something in one position and there is no displacement, there is no work done. Another situation. Imagine there is a beach ball, and the beach ball is on the water say, you're back at Cancun or something, and the beach ball's on the water, and you apply a force downwards like this, and the beach ball moves in this direction. So you're pressing down, and the beach ball moves towards the side. What's the work done? 0. Because the force is being applied in this direction, and the object is moving in that direction, the displacement is at 90 degrees to the force. Cosine 90 is 0. And finally, what about force normal? Force normal is a counteractive force. It does not move an object through a distance, and therefore force normal, being a counteractive force, means that it does no work. Force of friction always acts opposite to the direction of motion. Thus, force of friction being cosine 180 degrees, force of friction does negative work. Now we're going to look at Hooke's law and how that applies to work. Here we have a mass attached to a spring, and the spring is attached to a wall. Now we're going to look at the motion associated with this system. We call this motion periodic motion or simple harmonic motion. Nonetheless, there is work associated with this system. As we have the mass in this position and it moves, it's displaced a distance x, we can calculate the work done by the spring. The work is given by 1/2 kx squared. Work being 1/2 k, the spring constant, x, the displacement, squared. There is also a force associated with the spring. This force is given by Fs, that's the spring force, is equal to negative kx, where k is the spring constant and x is the displacement. Let us examine why there is a negative sign here in front of the kx term. The reason is, I will show that the spring force is always opposite to the direction of displacement. Because they're always opposite, there's a negative sign built into the equation. So here's the spring. Let's say this is the spring's native position. So we just put a spring there, we put the mass there, we haven't pushed or pulled or anything. So the mass is here. Let's say we push like so onto the spring. So we're pushing in this direction, therefore we're displacing it in this direction, squishing the spring. As we push on the mass, squishing the spring, clearly the spring will be pushing in the opposite direction. So we are applying a force in this direction, and as we do so, as we displace in this direction, the spring force is pushing in the opposite direction. Therefore, the spring force is negative kx. Now notice, when you apply a force on the mass, the spring gets smaller, applies its spring force against in the opposite direction like so. When you release, this will push the mass in the other direction, displacing it in the other direction. So in other words, the spring force restores itself. As this moves back and forth, we have energy stored in the spring and it restores its force. Therefore, we call the spring force, Fs, a conservative force because the force is restored. When energy is lost, for example, friction is a force, but friction energy is lost as heat, etc. And therefore, friction would be considered a non-conservative force, as opposed to the spring force, which is a conservative force. Next, we're going to move on to a new topic. And before we begin this topic, I'd like to ask you a question. Is it possible to be moving at constant speed and be accelerating at the same time? Think about it. And indeed, the answer is definitely. You can be moving at constant speed and be accelerating at the same time. And this is shown in circular motion. The concept comes as follows. Speed is a scalar. It has a number and a unit. For example, 55 miles per hour. Velocity is a vector, which means it has a number, a unit, and a direction. 55 miles per hour, northeast. Acceleration is the change in velocity. You can have a constant speed, 55 miles per hour, but if you're changing your direction, then you're changing your velocity. And if you change your velocity, you're creating an acceleration. Now this is a circle, and as best as I can draw it. And a circle, one can imagine, is a series of infinitesimally small lines which are always changing direction. So that if you're moving in constant speed in a circle, your direction is always changing, therefore you have an acceleration. The acceleration we call the centripetal acceleration. We calculate the centripetal acceleration as v squared over r. So v squared, v the velocity squared over r the radius of the circle. The centripetal acceleration is directed towards the center of the circle. So we can draw the vector in this way, and that is the centripetal acceleration. As we talked about in Newton's second law, where there is an acceleration, there must be a force associated with it. So the force associated with the centripetal acceleration is called the centripetal force. And the centripetal force is directed towards the center of the circle in the same direction as the acceleration. However, One might wonder, do I actually feel that acceleration towards the center of a circle every time I go into a circle? Well, consider this. Let's say that you go on an elevator, and the elevator accelerates upwards. Where do you sense the tug or the pull? You sort of feel it dragging yourself downwards. So you feel the tug in the opposite direction of your acceleration. Now let's say you go into one of those bizarre rides at an amusement park or at Disney World or whatever. And one of these amusement parks, you're going into one of these rides in which it's whipping you around at high speed. As you're moving in a circle at high speed, where do you feel the tug or the pull? You feel it towards the outside of the circle. In other words, it's as if you're accelerating towards the center of the circle and you feel the tug towards the outside. Just like when you're in a car and you're turning a corner and you feel the tug or pull towards the outside of the circle. So this is the sense that you have of the acceleration towards the center of the circle. But one important difference. When you're in an elevator and you're accelerating upwards, well, you move upwards. You actually move in the direction of your acceleration. But if you're in one of these weird rides at an amusement park and you're accelerating towards the center of the circle, you don't actually move towards the center of the circle. That actually would be quite a ride if everyone started moving towards the center of the circle. So obviously that doesn't happen. So there must be some counteractive force. It's sort of an imaginary force or a pseudo force to explain the fact that you are not actually moving towards the center of the circle. That force is called the centrifugal force. And the centrifugal force is a pseudo force, and it acts opposite to the direction of the centripetal force. Here is a classic MCAT type problem. A particle is in circular motion in the direction indicated. It is in increasing speed. When the particle arrives at point P, what will be the general direction of its acceleration? You may want to pause and consider your response. Note, it is at ever increasing speed. When it arrives at P, of course, it will have a direction of its acceleration at C. Anytime something is in circular motion, it's going to have a component of its acceleration pointed towards the center of the circle. That's the centripetal acceleration. If it's at constant speed, that's the only acceleration that it has. But this particular situation, it's at increasing speed, so that it'll have a component at C, but because it has an increasing speed, when it is at point P, the direction of its velocity will be tangential to the circle, so it has increasing speed. A component of its velocity will be at E. Therefore, if it's increasing its speed, a component of its acceleration will be at E. So we have a component at C, a component at E, therefore the general direction of its acceleration must be D. It is somewhere between C and E. If they were to ask that it was moving in the same direction, but with ever decreasing speed, therefore, if its speed was ever decreasing, when it was at P, because it's in circular motion, it will still have a component of acceleration at C, centripetal acceleration, but when it is here, it will have negative acceleration, because if something is slowing down, if its velocity is decreasing, therefore it has deceleration, which is the same thing as negative acceleration. So at point P, it will have a component of its acceleration at A. So we would have a component at A and a component at C. Therefore, the general direction of acceleration would be B if it has ever decreasing speed. Now we will look at the work-energy theorem. The work-energy theorem is one of the classic concepts that really helps us solve problems. There are different ways to write the work-energy theorem. The most general way to express it is the following, which is that work is equal to the change in kinetic energy plus the change in potential energy. If there is no potential energy terms in the particular condition or situation that you're looking at, then it ends up being that work is simply the change in kinetic energy. This work-energy theorem can be applied to many different situations. In one of the contexts, we can imagine that the kinetic energy is equal to 1/2 mv squared, 1/2 mv squared, and the potential energy is equal to mgh. So m, of course, being the mass, v the velocity, g gravity, and h is the height. So this is one way of writing the equation, and a change, of course, means the difference between the final situation and the initial situation that the object is in. Now let's look at another application to do with electricity. This is a classic question. Here we have a charge, say a large positive charge here. Here's a distance r and a distance r. We have another charge here, plus q. This is position A, this is position B. Here is the question. What is the work done in order to move the charge plus q from position B over to position A? The answer, 0. The reason is that if the distance r is the same, and it is, r is the same on both sides, then it implies something called equipotential lines. And if you have any charge, around a charge there will be equipotential lines, meaning that anywhere there is something at that same distance around the charge, it would have the same reaction to the charge. In other words, if it's a positive charge and you put another positive charge here, well, like charges repel, so the charges would like to move away from each other. And that same desire to move away, or potential to move away, is the same at the identical distance all around the charge. So that would create an equipotential line around the charge. So the potential will be the same at A or at B. So in other words, there's no change in the potential energy at A or B. What about the kinetic energy? Well, if the charge wasn't moving here and we lifted it up and we put it over here, it wasn't moving there. It's not as if we threw it or anything. We picked it up and we put it to another position. So there's no change in kinetic energy and there's no change in potential energy. Therefore, the work done, it doesn't even matter what path you used to go from here to there, the work done is 0. It's like picking up the overhead projector and running around campus and putting it back in the same position. The displacement in the sense of gravity is 0. And the displacement in the sense of electricity, because of an equipotential line, here is 0, so the work done is 0. Here are two other concepts that are favorites for the MCAT exam. The first is conservation of energy. Conservation of energy states that the energy of any mechanical system is constant. In other words, if you were to look at the total energy of a system, for example, an object in a certain position with a certain kinetic energy and a certain potential energy, and you examine it at some other point, then you can look at its kinetic energy and its potential energy, and it will be the same, because the total energy is constant. So conservation of energy says that the total energy is conserved. Incidentally, conservation of energy applies to systems that are not being acted upon by external forces. If there is an external force, then there will be work associated with it if the object moves through a distance, because force times displacement is work. And if there is work done because there's an external force, then instead of using the conservation of energy, where the total energy is conserved, you would talk about the work-energy theorem, where work is the sum of the kinetic energy and the potential energy changes. Next, the second law of thermodynamics. The second law of thermodynamics states that the entropy or randomness of the universe increases in any real system. So let's look at an example of this. Consider the following question. Let's say you have 2 copper bars. Each copper bar is exactly the same size. One copper bar is 100 degrees Celsius. The other copper bar is 50 degrees Celsius. We put them together in contact in a perfectly isolated system. In the end, the temperature of each copper bar is 75 degrees Celsius. Question: what happened to the randomness of the universe? Does it increase, decrease, or stay the same? You may want to pause and consider your answer. The randomness increases. You may say that the total energy of the system will remain the same, because you started at 100 degrees, one was at 50, you ended up at 75 degrees Celsius for both copper bars. So the total energy of the system remained the same. Nothing was lost or gained by the system. Total energy conserved. Randomness? Well, for one, by definition, the randomness will increase in any real system. But let's look at this more specifically. How could you imagine that the randomness of the universe actually increases if we come to a temperature between the two? Well, imagine if you had a split personality. And in your bedroom, half of your bedroom was beautifully immaculate, and the other half of your bedroom was completely messy, with things randomly all over the room, clothes all over the place, etc. Everything thrown on the ground, garbage, and so on. If someone came into your room, they would see a perfectly clean part of your room and the other part of the room incredibly random. Now, what happens if the randomness on one side of the room went on to the other side? So you spread the randomness around the entire room. Would the overall randomness of the universe increase, decrease, or stay the same? Well, I think you would see that it would increase, because you had so much order in part of the room. But if anybody walked into the room, they're just going to say the room is messy. They're not going to say, oh, the messiness is sort of evenly distributed. They're going to say the room is messy. And in other words, more space has been occupied, and therefore more of the universe is random, and therefore entropy has increased. Momentum. The key concepts behind momentum include that mv is a constant, which is to say that mass times velocity is constant. The other concept is that of impulse. Impulse is defined as the instantaneous change in momentum. When we discuss momentum, usually the problems that they like to give you are problems of collisions. There are 2 types of collisions that they may give you. One is when 2 objects collide and bounce off each other. That would be called an elastic collision. When 2 objects collide and stick to one another, that is called an inelastic collision. So they collide, stick to each other, and then they move off in some direction. Either way, whether elastic or inelastic, the motto for collisions is that the momentum before is going to be equal to the momentum after. Now let's look at what would happen for an elastic collision. So two objects hit each other and then bounce off each other. So because there are two objects, we would have two masses, m1 and m2. Now each of those masses would have a different velocity, v1 and v2. So the momentum before would be based on m1 v1 plus m2 v2, and then they collide. So the momentum before would be m1 v1 plus m2 v2. The momentum afterwards would be the same masses, m1 and m2, and each would have a new velocity, v prime and v double prime. So we would have m1 v prime plus m2 v double prime. The key thing to remember about momentum is that these are vectors, meaning you have to keep into account what directions things are occurring. If things are coming in at different directions, then one would be coming in the positive direction, the other would be in the negative direction. You would just have to define which is positive, and then you remain consistent throughout the problem. If things are coming in to hit each other at various angles, then you would need to resolve the momentum or momenta into their different y and x components. So it's important to remember that these are vectors. We're going to work out a problem that uses both momentum and conservation of energy. Now let's look at a momentum problem. Consider the following. A projectile, in this case a bullet coming from a gun, a projectile is launched. It has a mass small m and a velocity large v. It is launched at a large mass that's hanging from a string or cord. When the bullet is launched at the mass, this is before the collision, then after the collision we will have the mass and the bullet will be embedded in the mass. So we'll have the large mass plus the small mass as the bullet is embedded in the mass. So it'll hit this and then it would move to the left. It will move with a velocity v. So the question would be either they would give you the velocity of this large mass, or they'll give you the velocity of the bullet, and they'll give you a couple of velocities, but there'll be one unknown. Whatever they require of you in terms of an unknown, it'll be a very simple problem. First of all, you would recognize that this is an inelastic collision. It is inelastic because the two masses will stick together. And in order to work out the equations, we just simply say the momentum before the collision is equal to the momentum after the collision. The momentum before the collision would simply be m times v. So before the collision we have m times v. The momentum of the large mass before the collision is 0 because it's m, large m, times its velocity. Well, it's just hanging by a string, so it has no velocity, so it's 0. So we would have mv plus 0 is equal to the momentum after the collision, which is the sum of the masses of the system times its new small velocity. So this would equal m plus large M small v. And with this equation, whatever they provide as an unknown, you would easily be able to calculate. Now, let's complicate matters a little bit. Let's say that the question is not just what the velocity will be, the initial velocity, but let's say we know that when this mass gets hit by the bullet, it will swing. So let's imagine that the mass is swinging. So we'll draw the result here. So the mass swings to the left. Well, its center of mass is going to rise. The center of mass being here, there, so it's going to rise. And it's going to rise, what we'll say is a height, h. So let's say that the question is, after the bullet hits the mass and the mass swings, by what height h will the center of mass rise, or will the mass rise? By what height h? What would be the maximum height? For this, we go to conservation of energy. And conservation of energy would tell us that the total energy down here, once the system was moving all together, once it was all together, the total energy down here would equal the total energy up here. Now the second that it has velocity as a system, soon as it has velocities as a system, therefore it has kinetic energy. Its potential energy at this point, while it's hung by the string, its potential energy is relatively zero. So it has all kinetic energy. When the mass rises to the top, there is an instant when the mass will change directions. In other words, it swings to the top, then it's just about to change directions and start coming down. When it's at its maximum height, for just an instant, it has no velocity, and therefore it has no kinetic energy, because kinetic energy is 1/2 mv squared. So it will have all potential energy, mgh. Therefore, the kinetic energy, once the system starts to move, will be equal to the potential energy when the system is at its highest point. And therefore, we would get the equation using conservation of energy that the kinetic energy down here would be 1/2 m plus m v squared is equal to m plus m gh, which is the potential energy. And of course, these cancel, and we get 1/2 v squared is equal to gh. Once again, you can calculate whatever they provide. By the way, on the MCAT exam, it is quite frequent that they will give you extra data that you don't even need to use for your calculations. That's why it is better to use symbols first before you start plugging in numbers. Reduce to the simplest possible situation before you start plugging in numbers to avoid unnecessary calculations. You could just imagine how messy this could be if you started plugging in masses when you didn't even really need to. One more question. The bullet hits this mass. Everything moves to the left. What work did the bullet do in order to raise the mass a height h? 0. The bullet does no work to raise the mass a height h, because remember, work is force times distance, really displacement, but work is force times distance where the force is in the same direction of the displacement. So this is the force would be acting in this direction, the height h is in that direction, which is 90 degrees, cosine 90 being 0, so the work done would be 0. We are now about to look at the law of torques. I suppose one might say that we're about to do the nuts and bolts of torques. Sorry for that. Anyway, consider this. Here's a nut, And here is my best rendition of a wrench. And I want you to consider the following. Torque forces are turning forces. In fact, if you've had experience turning a nut with a wrench, you'll find that if you tried to turn here, it's very difficult. If you put your hand right there and try to turn, it's very difficult. But as you start moving further from the turning point, because the point about which this whole system turns would be right here, the center of the nut. That's the point about which everything is turning. So that point we call the pivot point. As we go away from the pivot point, along the handle, along the perpendicular distance away from the pivot point, our ability to turn the nut increases. So our turning force increases as we start moving away from the pivot point. Our turning force increases means that our torque force multiplies as we go away from the pivot point. In fact, the torque force is defined as the force applied times the perpendicular distance from the pivot point. So if you maintain the same force, but you start moving away from the pivot point, your torque force increases. Now here's a nut. Let's say that you applied 10,000 newtons of force. 10,000 newtons of force is a tremendous amount of force, and you apply it right at the pivot point. What would the torque force be? 0. Because the torque force is the force applied times the perpendicular distance away from the pivot point. So if you apply all this force at the pivot point, the nut's not going to turn. You might break it, you might cause damage to something, but you're not going to turn it. In order to turn it, you require some distance, torque, some twisting, some turning force, and you have to get away from the pivot point. Otherwise, the torque force would be 0. So now we're going to look at a couple of problems based on torques. We will begin by looking at a simple problem, then we'll look at something more complex. So let's say we have a teeter-totter, and on the teeter-totter we have 3 little children shaped like boxes. And each one of them has a different mass, M1, M2, and M3. So we know what the forces that are here would be, because the force here would be M1G, the weight. The force here would be M2G, and this would be M3G. This is called the fulcrum. It is the point about which the teeter-totter bends in the different directions. The fulcrum is what we would take as our pivot point, the point about which things turn. Now, if this system is at equilibrium, then we say that the sum of clockwise torque forces is equal to the sum of counterclockwise torque forces. So how do we determine when a force is clockwise or counterclockwise? Well, we said that this has a weight, M1G, which points down. This is M2G, that points down. This is M3G, and that points down. So now this, we have to imagine, because it's our pivot point, the point about which things turn, let us imagine this is the center of a clock. And if this were to be the center of a clock, and the clock ticks in this direction, so a clock turns in this direction, therefore only one of these forces is moving in the direction of this marker. Only one force, and that is M3G, is moving in the direction of this marker, which is clockwise. You can clearly see that the other 2 forces M1G and M2G are moving in the opposite direction. So M3G is our clockwise torque force. And that would equal to, moving in the counterclockwise direction, would be this. This being the center of our clock, this is moving in the counterclockwise direction. We have M1G and we have M2G moving in that direction. So we get M1G plus M2G. And this is a system in equilibrium. We have the sum of clockwise torque forces equals the sum of counterclockwise torque forces. Now let's complicate the system a little bit. We are now going to look at a problem with torques such that by solving this problem, you will be able to solve essentially any problem they're going to give you about torque forces. So we have a bench. On the bench is a mass. This mass weighs 500 newtons for this mass. The plank is 100 newtons. It is 4 meters long. The question is, what is the weight supported at A and B? First, we're going to have to draw some arrows on our diagram in order to have clear in our minds where the forces are acting. Well, here we have a mass, and so it has its mg acting downwards, and in this case we know it to be 500 newtons. So this is the number 500. We also have the weight of the plank is going to act downwards. The weight of this plank, which we would have to be given that it's uniform. If we know that this is a uniform plank, means that it's shaped evenly over its distance, then the 100 newtons of weight would act at the center of gravity. And for this means that it would act at its center. If it's 4 meters long, it means that at 2 meters in the center, we have what is essentially the downward force, which is the force of the plank, and that is 100 newtons. So we have 100, which is acting right at the center, 500 newtons, which is acting as a consequence of the box. So these forces are acting downwards. Clearly, in order for this not to fall, there has to be forces acting upwards. Just like we saw before, if there's a net force, there will be acceleration. So if this system is in equilibrium, it's not moving, it's just a bench, well then there has to be forces acting upwards. And these forces must be at A and at B in order to prevent this from accelerating downwards. So there are 2 rules to remember. And with these 2 rules, you can solve any of the torque force problems that they will give you. One rule is translational equilibrium. And the other rule is rotational equilibrium. These 2 rules will permit you to solve any of the problems that they will give you. The first one, translational equilibrium, what that tells us is that if you sum all the upward forces, it will equal the sum of all the downward forces. So what are the upward forces? Well, we have as upward forces B acting upwards, and we have A acting upwards. So the sum of upward forces would be A plus B. And that would equal the sum of the downward forces. And the downward forces would simply be the box, 500 newtons, and the plank, 100 newtons, would be our downward forces. So A plus B is equal to 600. So I don't know what A is, and I don't know what B is, but I do know for this system to be in equilibrium, A plus B must equal 600 newtons. Now rotational equilibrium, which is essentially what we saw when we looked at the teeter-totter. And that is that the sum of clockwise torque forces is equal to the sum of counterclockwise torque forces. One problem. When we looked at the teeter-totter, it was clear where our pivot point was. It was at the fulcrum, where things were turning about. And when we looked at the nuts and the wrench, it's clear where things are turning about. But here, nothing's really turning. So then, in this circumstance, we can choose our pivot point. We can choose any single point along the bench as our pivot point. Then we calculate everything from that point. There are a couple of tricks though. If you have two unknowns, then you should choose one of your unknowns as the pivot point. The reason is that we saw that the torque force at the pivot point is always zero. So if you have two unknowns, if you take one unknown as your pivot point, then the torque force at that point is zero, so it eliminates one of your unknowns. Then you only have to deal with the rest. So in this example, let us take A as our pivot point. That will eliminate A as a torque force. Then we're going to look at everything rotating around A. So A becomes the center of our clock. So everything that's clockwise or counterclockwise depends on A being at the center. So A being in our center of our clock, and we're going to look at what moves in the clockwise direction. A being at the center of the clock. So the forces moving in the clockwise directions, we have the 500, which moves in the clockwise direction. 500 times the distance, because the torque force is the force times the distance. So 500 times 1.5 would be part of our clockwise torque force. 500 by 1.5. Then we have plus, still moving in the clockwise direction, we have 100 times its distance from the pivot point, which would be 2 meters. So we have 100 times 2. And that would equal the sum of our counterclockwise torque forces. Now clearly, still moving in the clockwise direction, B is not in the clockwise direction. It is obviously in the opposite direction. So let's move in the counterclockwise direction around A, and we see that B is indeed in the counterclockwise direction. So the force at B times the distance of B to A, which would be 4. So now we have an equation. So we can solve for B. Once we solve for B, we can solve for A. Just understanding these concepts of translational equilibrium and rotational equilibrium will permit you to solve any of the problems they will give you regarding torque forces. Now let's move on to fluids. Now we will examine fluids. And a fluid is essentially anything that flows. So a fluid may be air, water, or molasses. There are about 5 equations regarding fluids that you absolutely must memorize. Very important equations. The first is that of specific gravity. The specific gravity of a substance is simply the density of that substance over the density of water. Sounds like a simple definition, but this is a commonly used concept on the MCAT exam, that of specific gravity. So it's the density of a substance over the density of water. We will see later why this concept is so important and its application is important. Of course, you should have memorized the density of water, which everyone thinks of 1. But what is the units for that? The units for the density of water is grams per cc, or grams per centimeter cubed, or grams per milliliter. That's all the same. You should also know the density of water in kilograms per meter cubed, because that often commonly comes up on the MCAT exam. You can determine that by dimensional analysis, by looking at the units and converting the units appropriately, or you can memorize that the density of water in kilograms per meter cubed is 1,000 kilograms per meter cubed. The next equation that's very important to memorize is the equation regarding pressure, and that is simply that pressure is force per unit area. So it's the force per unit area. Next, fluids which are static, which means, say that you have a cup of water, or you're looking at a pool or whatever, and you would like to know what is the change of pressure from one position to another position in that fluid. Well, that change in pressure as you go from one spot to another would be dependent upon the density of the fluid, which is symbolized by the Greek letter rho, the density of the fluid, the gravity, because certainly the pressure would be different on Earth as it would be on the moon, so rho g, and on the depth or height that you're moving within the fluid, delta H. Change in pressure is equal to rho g delta H. Very important equation. Next, let us look at the equations of fluids in motion. We will now look at two very important equations that describe fluids in motion. The first is called the continuity equation, and that states that rho V A is constant. That's rho, the density of the fluid, V, the velocity of the fluid, A, the cross-sectional area of the fluid, is a constant. So this is an equation, along with the others, all the others that we've looked at in this series on physics, that must be memorized. Now, it's important to understand this is not the same area as in pressure is force per unit area. This is cross-sectional area. For example, if it was a pipe that we were talking about and fluid that's running through the pipes in your apartment or in your home, the cross-sectional area of a pipe would be a circle. If you were to cut the pipe along its length, you would see a circle. It is important for you to know what the cross-sectional area is. Of course, the area of a circle is given by pi r squared, where r is the radius of the circle, pi being 3.14. That, of course, is a basic equation that you are definitely expected to know. The other high school equation is, of course, the circumference of a circle, which is 2 pi r. That also may come in handy. This is the equation of continuity. The other equation is Bernoulli's equation. Bernoulli's equation says that the pressure plus 1/2 rho v squared plus rho gh is a constant. That's the pressure of the fluid plus 1/2 rho the density, v the velocity of the fluid, squared, plus rho gh, the density, times g, gravity, times h, the height, is a constant. So these two equations are very important to memorize. The Bernoulli's equation is very simple. Sometimes on the MCAT exam they'll actually give you Bernoulli's equation and ask you to manipulate it or work with it. So, but I suggest still that you still memorize the equation, and it's rather simple to memorize. We're talking about fluids, so you know pressure's involved. Then we have a kinetic energy term. Just like 1/2 mv squared, well, this is 1/2 mv squared over volume because we're talking about fluid. So it's 1/2 rho v squared, very similar. Just like we had potential energy, mgh, well, this is essentially mgh over volume because this is mass over volume. So very similar terms. So let's look at a problem or an application of these terms so that you can feel comfortable about using them. Consider this system of pipes with varying diameters. There are three different diameters, A, B, and C. The fluid is moving through this system in what is called streamline flow, as opposed to a lot of turning, which would be turbulent flow. So as this fluid is moving through the system, we have different cross-sectional areas. Now here's the question. In which one of these containers or areas would we have the highest pressure? You may want to pause and consider your response. Well, to begin with, based on the fact that there are different cross-sectional areas, let's see what happens in the place that has the smallest cross-sectional area, right here at B, where we have the smallest cross-sectional area. Based on the continuity equation, smallest cross-sectional area means the highest velocity in order for this to remain constant, as long as the density remains the same throughout, which means a fluid which does not compress, or an incompressible fluid. So we have the lowest cross-sectional area has the highest velocity. So at B, we have the highest velocity. Then we look at Bernoulli's equation. If we have the highest velocity, if density is more or less constant, but we have the highest velocity, that means we would have the lowest pressure. Because the term for height, overall, the height is going to be equal through this system. So that this term is not important. But if we have the highest velocity, which clearly would be here, based on the continuity equation, then we would have the lowest pressure at B. The highest pressure, therefore, would be at A, where the velocity would be lowest. And one more question. Where would the flow be highest? And flow means volume per unit time. Well, the flow throughout this system would be the same. And this is for an incompressible fluid that is moving as shown, which means streamline flow. Then the flow would be the same throughout the system. Volume per unit time. Here, there's a large volume, but it would take a large amount of time to move it. Here's a small volume, which would take a very small amount of time to move, etc. And so the flow throughout the system would be the same. Now let us look at Archimedes' principle. Archimedes' principle states that the buoyancy force on a body immersed in a fluid is equal to the weight in volume of the fluid which is displaced. Now let us apply this information. Let us imagine that there is a glass of water, and in it there is some ice. Well, if you look at a glass of water with some ice, you will notice that the ice not only floats in water, but it actually has a bit of its surface will be above the surface of the liquid water. This is a very unusual feature because most substances, when it goes from liquid to solid, it becomes more dense in the solid form, and therefore it would end up at the bottom. But water is this very unusual substance where when it becomes solid, it actually expands and it actually floats. Now the question is simple. When the ice cube melts, will the surface of the water go up a bit, go down a bit, or remain the same? You may want to consider your response by pausing and then come back. The answer is, it remains the same. And the reason is, this ice cube has a certain weight, and the weight pushes down and pushes aside the liquid water. This ice cube can change shape, become liquid or whatever, but did its weight change? No. And if its weight did not change, then its force to push the liquid water aside cannot increase nor decrease, and therefore the level of the water cannot change. Imagine for a second that you had a bucket of water and you had a big styrofoam thing, and you put this styrofoam thing in your bucket of water. Well, the styrofoam would push aside a certain amount of water. How much water? It could only push aside the amount of water which is equal to the weight of the styrofoam. The styrofoam is applying a force, a weight, and it pushes aside water. It could only push aside the same amount of weight that it has as a force, and then that would be equal to the buoyancy force. Now let's say that we looked at exactly how much water was pushed aside when we put this big styrofoam thing in the water bucket. Now let's say that we took the styrofoam and we squished it and squashed it and squanched it and then put it back in the bucket. Do you think that styrofoam would push aside any more water or any less water? It would be the same amount of water. It doesn't matter that its shape has changed. It will be the same amount of water that will be pushed aside because its weight has not changed. So its ability to push aside water has not changed. There's something else that's important to say, and this brings back the concept of specific gravity. Now, we talked about specific gravity being the density of a substance over the density of water. Well, if you have a specific gravity of 1, then you have the same density as water. So if you had something with a specific gravity of 1 and you put it in water, well then it will go below the surface of the water because it's the same density as water. But if you have a specific gravity of, say, 0.9, then the density of the substance must have been less than the density of water, so therefore it would float, which is the case of an ice cube. Now, if you were to be asked what percentage of the substance is below the surface of the water, well, it would just be 90%. So a specific gravity of 0.9 indicates that 90% of the substance would be below the surface of water. That includes the height of the substance. 90% of the height would be below the surface of water. Specific gravity of 0.6 means 60% of the substance would be below the surface of water.